to welcome you in Ioannina and in our university. Thank you for coming and participating in person in this year's Supersymmetry conference. For almost half a century, supersymmetry and supergravity have shaped the structure of our theories, the quantum field theories. They played a fundamental role in the incorporation of gravity within the unified framework of string theory. Despite the absence of experimental evidence for superpartners, at least at the expected energy scales, we are not ready yet to abandon supersymmetry. We firmly believe that supersymmetry points to the right direction. I am confident that your talks will shed light on many related important issues. I hope that you will enjoy the conference and have an amazing free time in our city with its beautiful surroundings. I wish you a very pleasant stay. At this point, I would like to invite to the podium the mayor of the city, Professor of Medicine, Moses Elisaf, to address the conference. Dear Moise.
Distinguished guests, ladies and gentlemen, it's a great pleasure to welcome you to our city for the 29th Conference on Supersymmetry and Unification of Fundamental Interactions. I would like to congratulate the organizers of this important and prestigious event. On behalf of the city of Ioannina, I would like to especially express our appreciation to the distinguished speakers, as well as all the participants who came from abroad. All these important participants ensure that the conference will be of a very high scientific level. Please allow me to say a few things about our city, since as the mayor of the city, I should not pass the opportunity to present my city to such a prestigious audience. Ioannina, the capital of Epirus, spreads around beautiful Lake Pamvotida. The natural environment, the climate and character of the city are defined by this stretch of water, the area's trademark. The lake and its small island is a natural monument around which the entire area lives and breathes. Ioannina was always multicultural, dominated mainly by Christian, Islamic, and Jewish influences. This coexistence of cultural influences is clearly evident in the historic city center. Throughout the years, Ioannina has been established as a city of progress, of new opportunities, new people, and new ideas. But I'm sure that you know that the best way to get to know Ioannina is by seeing it and experiencing it. I urge you to take advantage of the opportunity of your stay in our city and visit and experience our beautiful, hospitable city. I would like once more to welcome you all and wish you a fruitful and successful conference. Thank you so much.
Thank you very much, Moses. Next, I would like to ask our Dean, Professor George Floudas, to address the conference. This time I will wait. Thank you very much.
Dear Mayor, dear colleagues, dear participants of the conference, members of the organizing committee, and mainly the organizer, George. I would like also to say a few things about, well, the university here. I belong to a different section of physics where a molecule which has 1,000 atoms is considered as a very small molecule. Normally, the molecules that we're considering, they have 1 million atoms. So they're very complex. These are polymers, macromolecules. Yet the foundations of the statistical nature of these objects were set by a theoretical physicist in Cambridge. His name was Sir Sam Edwards, who set the foundations for what we know today as conformational properties or statistical properties of macromolecules. His ideas about path integrals and how to use path integrals to calculate the paths of individual molecules gave the first Nobel Prize in 91 to Dezen, to a French scientist, and later on in 97 to Stephen True from Stanford, when he calculated the motion of peptides and proteins in a flow field. Later on, he had the idea he considered statistical systems which are intrinsically disordered, like spin classes. And he had the idea of the partition function and to use a replica of the partition function to calculate the free energy. That led to progress in spin classes, which gave last year's Nobel Prize in Physics to Giorgio Parisi. So why I'm saying this? I'm saying this because there are no boundaries, as you know, between physics in different sectors, and I'm pretty sure you know this very well, and any progress in a given field depends on progress in other fields as well, and I see that here you're discussing beyond the standard model, and so on. I would like also to say a few things about the group of the physics, which hosts the small group, but very dynamic on theoretical physics. It's a very small group, but it has set very high standards over the years. I see here people that have really set very high standards in this field, and also shaped the physics department in a way. Okay, without further saying, I would like to welcome you also to Ioannina. Please also take a moment, few maybe days, to explore the environment, as Professor Elisaf just mentioned. It's very special for Greece. You're in a very special region of Greece. Only people who know very well Greece know this part of the area. And I wish you a very fruitful meeting with many new ideas, because the success of any meeting is based on the ideas that is born, and especially for the young people, that they can remember the meeting based on the ideas they have received from this meeting. Thank you.
The rector would like also to address the conference. However, his busy schedule prevents him from being here in person. Here is his message. So, thank you very much. And I would like now to ask John to come and take over.
So thank you, George, for asking me to chair the first session. So they say that hope springs eternal. And I think the fact that we're here physically together is an illustration of that. After 3 years when we couldn't all meet together in conferences, here we all are. And I see lots of happy, smiling faces. Even the older people look happy for once. And talking of hope springs eternal, of course, we also hope that supersymmetry will finally show up. Maybe it hasn't quite shown up yet, or maybe it's just, coming up over the horizon. We will discuss that during the course of the week. So I think we're all looking forward to a very exciting conference, and the opportunity will come later on, again, to thank the local organizers, but already George et al., thanks very much for bringing us all here. So I was tasked with chairing the first session, which doesn't explicitly mention anything about supersymmetry, but maybe we'll come to that later. So without ado, the first speaker is Jeff Dandoy, who's going to tell us about searches for long-lived particles.
All right, thank you so much. I'm Jeff, I'm very happy to be here. For me, this is actually my first in-person conference in quite some time. So I'm happy to see all your faces. And it's my pleasure to present highlights of searches for long-lived particles at the LHC, and I will mention quite a bit about supersymmetry. So this is on behalf of the Atlas CMS and LHCb collaborations. They have extensive search programs for new physics, but these are typically focused on just a few prompt standard model particles. Now, there's still a lot of wide open phase space to look for those and new interesting models that I'm sure we'll hear about throughout this week. But there are still a lot of open questions with the standard model and a growing number of anomalies as well. But no recent discoveries yet, so it does require us to reimagine a bit what our searches should look like to make sure we don't miss things like this, a possible long-lived particle that decays after some time into a displaced electron, and which would be very hard to see given all this prompt activity. So we want to make sure we're not missing things like this. And there's actually been an explosion of interest in LLPs in the last decade. I give an example here of a plot I took from Inspire of all papers with long-lived in the title. And you can see last year was the most productive year yet with almost 70 papers. And I also found this interesting that the very first one of this count was a result from the BNL Cosmotron on the discovery of a V-shaped particle, which turned out to be a long-lived K-long. So we were off to a very good start in our long-lived particle search. And there's great motivation to look for long-lived particles, including the fact that the standard model is full of them. You can see this very nice summary plot of particle mass against the lifetime on the x-axis. And this white strip refers to roughly the size of the detectors we use. And you can see quite a few standard model particles that decay within our detector. And there are a number of things that keep these particles being long-lived, primarily by keeping the width small. And one is a small coupling. And I give an example here of the expected decay of a muon to a photon and electron, which is kept small in the Dirac model by the fact that the mixing of the muon to electron neutrinos is quite small. And that suppresses this decay and allows the muon to be long-lived. Another is a small matrix element of the process, typically because the masses of the particles involved are quite a bit smaller than some new scale intermediating it, such as the decay of a pion requiring a heavy W boson to be off-shell. Or there can be limited phase space for the decay, such as when a K-long has to decay to 3 pions, but there's only a very small mass difference relatively between the K-long and its decay products. SUSY models often predict these same features: small couplings, hierarchies of scale, and compressed mass spectra. And I'll show an example of some benchmark models that I'll be discussing in the searches today. These can produce displaced or emerging jets, such as through R-parity violating SUSY with the small decay couplings, or split SUSY, where this gluino only decays after some long time, or even other exotic models, such as heavy scalars connected to the hidden sector, such as a Higgs or some other scalar, which decay to these long-lived scalars. Or they can produce displaced leptons or photons or vertices of multiple tracks that we can see, such as in GMSB, where we get this lepton appearing because of the small coupling of this lepton to a gravitino, or exotic models of heavy neutral leptons, where we see this displaced vertex because of the small coupling of some heavy neutral lepton to the neutrino sector. And finally, these can also create disappearing tracked charged particles we first see but then disappear, such as in compressed SUSY, where of course we have a small mass splitting between the chargino and the neutralino. So all three collaborations are doing some new things to try and target these. The first is expanding the tracking. So I give an example of Atlas, but this is common to most collaborations, that Atlas's track reconstruction is not designed for long-lived particles. And you can see this blue area here is the phase space we're nominally sensitive to, and of course the obligatory banana for scale. But we wouldn't see long-lived particles like this. So they've developed a new large radius tracking to vastly expand the phase space into this purple box, allowing us to see particles like this. And like this one. And they do this in a very busy environment with lots of hits in the tracker from prompt tracks or noise. And so they first perform regular tracking to find all the hits associated with prompt material quickly, and then they can remove those hits and they have a much cleaner environment for which to track long-lived particles. And you can see they get great efficiency out to even 300 millimeters before the semiconductor tracker. And the efficiency is this purple color, and you can see it picks up very early. Prompt tracking barely fills that first bin. CMS uses a similar iterative tracking strategy, but they also benefit from an all-silicon tracker seen here, which allows them to extend their tracking out a bit farther to 600 millimeters. And you can see this plot of tracking efficiency for TT bar events, where they have similar efficiency as Atlas out to 300 millimeters, but then they extend a little bit more efficiency all the way out to 600. And finally, LHCb, which is a little bit different. It's not hermetic like these. It is a forward tracker, but it's really meant to see some long-lived decays, such as from B mesons. And the LHCb forward detector has, therefore, excellent vertexing from this vertex locator out to about 600 millimeters. But they also have several later tracking stages meant to follow charged particles. And recent studies shown up here have shown that they could actually extend their tracking coarsely out to more than 2 meters, which would be very powerful for long-lived searches. So I'll give an example of how all these collaborations are using it. One is looking for heavy neutral leptons. Here, this heavy sterile neutrino lives quite some time before decaying to a standard model neutrino and a Z boson, which decays to 2 electron or muon opposite sign leptons, therefore has a displaced vertex. And this lifetime is given by the strength of the mixing between this H and L and the standard model neutrinos, as well as the mass of it. And so they therefore search for masses in around 2 to 15 GeV, which would give a decay within the inner tracker, just like this. Atlas and CMS both have recent results here. Atlas searches in terms of the mass of the heavy neutral lepton, and so you can see that distribution here, where it's small masses is the signal region where they would see these being long-lived. And they can use higher masses as a control region because any new physics would be prompt here and therefore wouldn't come within their search. CMS does a somewhat different approach, looking in a 2D space based on the displacement of the vertex, which is shown on this x-axis, in different bins of the mass of that displaced vertex, so the 2 leptons. They both have similar backgrounds they have to deal with. One of the biggest one are hadrons that can actually decay to multiple soft leptons after some time. So Atlas rejects these in a broad window based on mass versus displacement, while CMS takes a more targeted approach, vetoing B jets that can produce, a cascade of 2 leptons that look like a long-lived particle, and also narrow hadron mass windows, which you can see here. And this allows them to retain some sensitivity down to even small H and L masses. Ultimately, they need to use data-driven backgrounds, as pretty much every long-lived particle search needs to do. And these include random track crossings, where you happen to have 2 charged particles from different vertices that happen to cross and look like they're coming from a displaced vertex. And so here you can see limits for both. They set limits in terms of Majorana or Dirac models, and also various lepton flavor mixings, either to electrons, muons, or tau. And here I show an example of the Majorana with the muon decay. And here you can see that mixing angle to the muon, where if you have a larger mixing angle, it becomes a prompt decay and wouldn't be seen by these searches. And a smaller one, it starts to escape the detector or be too rare to produce. You can see CMS is actually able to extend to this region in the top left, not only thanks to their narrower mass vetoes, but also they have a continuous tracking between prompt and long-lived, where for Atlas, this area is covered by separate prompt searches. But Atlas does look for a brand new model for 2 quasi-degenerate H&Ls, so possible mixing to multiple of these. And LHCb also has older results on here that are complementary that you can find at this link. LHCb does have another recent result targeting neutralino that decays into two quarks and a muon that lives after some time. And they're actually able to target very small masses. So this comes pair-produced from a Higgs decay, so they go quite low. And they can do this thanks to their low PT muon trigger, which goes down to 10 GeV, the best of the three collaborations. And they also have excellent resolution for boosted vertices, allowing this to be quite small mass. So here you can see an example of the distance this travels in the transverse direction and their sensitivity to it. They have several vetoes of phase space where there's material that could produce some displaced vertex. You can see an example of that here. And then otherwise, they build an MVA to discriminate against the dominant heavy flavor background, this BB bar. And you can see actually they have a great agreement with data, even given this complex shape due to material and other things. Ultimately, they get very good sensitivity, even at low masses. This is for 20 GeV neutralino, typically very hard to look for. And they can set limits to cross-sections below picobarn for various lifetimes of the LLP. But expanding tracking is only one way to look for these. We're also looking into novel ways to use our tracker, including looking for large ionization loss within these, such as from a long-lived chargino that maybe moves a bit slower and therefore deposits more energy in the inner tracker than the typical particle. Usually we expect about 20,000 electrons worth of charge deposited, but we're sensitive to 30,000 or more, and we could tell if some heavy particle is decaying, 100,000 or so. And so we see this through really large and long signals from clusters of sensors, not just one, but clusters nearby. And they can use a MET trigger because this particle will either decay and go missing, or it just loses a lot of energy, and therefore it appears as missing energy. And so they can use these clusters of sensors to measure the ionization loss in the pixel tracker, which they can then calculate the relativistic speed of these particles according to the Bethe-Bloch relation. And they calibrate this for the Atlas detector and its amount of material using standard model particles. And you can see that example here of ionization loss versus relativistic speed. You can see the protons in blue and deuterons in green leave quite a large ionization loss, but are well modeled by this. And then because they're tracking, they know the momentum of the particle, and they can therefore get the mass of the track and the LLP. So they have control regions at low ionization loss and low missing energy to build this track mass template from data, and you can see a validation region on the right where this mass template agrees quite well with data. When they look in the search regions, the medium ionization loss, they see good agreement between data and expected background, but they actually see a fairly significant excess in the higher ionization loss region above 1 TeV, and this corresponds to a 3.3 sigma global excess. So it's quite interesting. However, these particles are also seen in the calorimeter and muon spectrometer, so it's not decaying into a neutralino. And independent results there give it a speed near that of the speed of light. So it's inconsistent with the signal model, but still very interesting events, and you can learn a lot more about these in the talk Friday by Leonardo. Ultimately, they set limits on various SUSY models. You can see in the orange here for gluinos and here for charginos. As a function of the mass they exclude on the y-axis and the lifetime of the particle on the x. And it's actually very complementary with other searches, particularly because they can go far out, because they don't actually care how long-lived it is. As long as they see it, it doesn't matter where it decays. So it's very complementary. And this is actually a big focus of the LLP community right now. Not only to have these summary plots within an experiment, but to unify them across all experiments so we can see the full picture. A similar search from Atlas recently also looks for ionization loss from slow particles, but which might have multiple units of charge. And so not only can they use a MET trigger, but they also use a muon trigger because they expect to see this charge track all the way through to the muon spectrometer. However, the typical muon trigger only works for relatively fast particles. So they developed a brand new slow muon trigger, which checks for muons in the next bunch crossing, so actually 25 nanoseconds later. And that can get them down to 40% of the speed of light. They target pretty heavy masses, and they have two regions, one for 2 units of charge and one for 3 or more. And for the 2 units of charge, we should still be able to measure the amount of energy deposited in the trackers. So they look in terms of significance of several ones. And so here you can see for the pixel tracker, the significance, where standard model processes like zeta mu mu, you can reject most of them by doing this 13 sigma rejection while keeping a lot of that signal. When you get to heavier charges, it actually overwhelms the pixel tracker. So they look for saturated signals in the transition radiation tracker and also look for very significant ionization loss in the muon system. So of course they have to use a data-driven ABCD method to help calibrate for this in data. And so here you can see the significance for the Muon system versus the TRT system. Data generally prefers low significance, but might go above these lines for one or the other, but it's not correlated, while signal prefers this region in the top right. They see 4 observed events and 0 observed events, which agree pretty well with standard model expectations. So they set mass limits versus charge. Here's the mass and the color are different units of charge. And their expected results you can see for 7 units past the theoretical prediction right at about 1.6 TeV. But we don't even need to use the tracker to see some of these long-lived particles. And I'll show 2 results from CMS where they rely only on the Muon system. One is looking for a di-muon vertex, for instance, coming from a dark photon due to the connection of the Higgs to the hidden sector. And this allows them, by only using the Muon system, to really target lengths out to 4 meters. And they get to use the nominal di-muon trigger because it doesn't actually have tracker constraints, so they can get a lot of data. But if you use muons with tracker plus muon system information, you can only go out to about 50 centimeters before you lose events. So they also build muons uniquely just using muon system info, and that allows them to go all the way out to 400 centimeters. They look in terms of this displacement of this vertex away from the center of the detector, as well as the closest approach of these tracks of the muons, the impact parameter, to the vertices in the center. And the main backgrounds, and here you can see the sort of significance of this impact parameter. And so the signals peak quite high up in this top right region, while the backgrounds, standard model backgrounds, Drell-Yan and muons coming from QCD, either from a B hadron, both of them from the same place, or from independent vertices, are measured according to their kinematics. So they can look at low signal regions, such as when the angle between the muons is quite large, or when they're same sign, which the signal model doesn't predict. CMS also has a second result using data scaling, and this is actually where you only save a very small fraction of the event, which allows you to bypass the nominal trigger and record much more data, here by a factor of about 3. It does require 2 hits in the pixel tracker, so it limits them to about 11 centimeter displacement, but they get a lot more data doing this. So they look for displaced muons based on missing pixel hits and large significances. And on the bottom left, you can see the data they collect here. The main backgrounds are material interactions, so they veto regions of known material, as well as standard model resonances. So you can see here on this di-muon mass plot, they veto regions where resonances, known resonances are. And this gives them a smooth background that they can parameterize with a sliding window fit. And you should be able to see some narrow resonance appearing here, such as here for this model. Ultimately, limits are set according to the mass, the lifetimes, and the branching fractions of particles to the LLPs, including dark photons or just simplified scalars, or even scalars coming from a B hadron decay that are quite light, but then decay directly to 2 muons. And here you can see an example of that model up to about 5 GeV, where the CMS results in black are quite competitive compared to LHCb results, which are really dedicated to looking for these B hadrons decaying. But you can see at very high masses and for long-lived particles, this is 100 millimeter distances, they do quite well. There's also complementarity between that di-muon and the data scouting result, which you can see here in the CMS summary plot, where together the two of them set very strong limits going from just 0.1 millimeter all the way out to models with 1,000 meter average lifetimes. Finally, you don't need to even use the muon system. You can also use the calorimeters, which is a bit tricky, but Atlas has a few recent examples where they do this. One looks for a hidden sector via heavy neutral scalar. And the main background here for looking for a particle like this are just QCD jets. But these tend to have associated tracks to them in the inner tracker, or a small fraction of energy in the or a large fraction of energy in the EM calorimeter for QCD jets, or very wide showers due to the long evolution here. These LLP particles will be a bit different. They'll be much narrower, they'll have no tracks, and they might have little or no energy in the EM calorimeter. So this allows them to look for decays about 2 to 4 meters in this region. It's very tough, so they have to use advanced machine learning techniques to really tease out the signal versus background from QCD, particularly if they have some neutral particles that live for some time, or beam-induced backgrounds that come into the calorimeters from the side and can look like this. And so they feed these models plus low-level tracking calo info to create an adversarial neural network where you can see for the per displaced object, they have very good separation between the signal and these two backgrounds. They then feed in those per jet objects into a per event BDT, including more high-level jet and event info, and they have a data-driven calibration of this using an ABCD method. They see slight excesses in both search regions, a high mass and a low mass one, equivalent to a p-value of about 0.08. And if you want to learn more about the techniques used here and these events, there's a talk later today by Jackson on this. Ultimately, their exclusions are parameterized by lifetime, the production and branching fraction cross-sections, and the mass of the two scalars. And here you can see limits assuming the Higgs decays to two scalars, and you can see the limits go down to about 1% branching fraction for lifetimes of about 0.1 to 10 meters. A second result looks for a similar model, but it really targets much lighter dark photons of order even down to MeV. And so these have very small mass, they have a lot of boost, and so they're very collimated decays. So the focus here is really on reconstructing the unique displaced objects you see here. They have two strategies, one looking for two quarks or two electrons in the calorimeter system, and so they use, again, jets with low fraction of energy in the EM calorimeter. And they use a CNN based on cluster kinematics to really discriminate powerfully against QCD and beam-induced backgrounds. But they also look for decays into just two muons by actually looking for muon segments not associated to muons in the inner tracker and doing jet-style clustering of these. And they build a deep neural network that can discriminate against the primary background of cosmics using distance in the z direction parameters, or the timing of these muon segments, or also kinematic information. The search regions cover one or two displaced objects and actually do a very good job at covering the gap for this dark photon mass versus this coupling of the dark photon to decay. That goes nicely between the prompt and monojet results. Here you can see theirs are in blue for different branching ratio assumptions. And these are actually also the very first limits in the fully electron decay, which allows them to go much lower than twice the muon mass. And so we have some of the first results down to even 17 MeV thanks to this. And again, you can learn a lot more about this interesting result from Jackson. And the last search I want to mention is the non-pointing photon result, where actually you can have long-lived SUSY particles that decay into a photon in the LSP later in your detector. These come from a Higgs, produced in association with a Z boson, so you can actually see this vertex here with two leptons. And they can actually use the unique depth information of the Atlas EM calorimeter to point back and see whether that photon agrees with the primary vertex in the Z axis. You can see an example of this photon pointing here out to 2 meters, where the standard model background is here in the black points, and we have good separation with the supersymmetry signals in these colored lines going well out farther. And the resolution they can get with this pointing is actually pretty impressive, 15 millimeters at 100 GeV photon energies. And they also use timing resolution as well, which is quite powerful, and they have resolution of about 200 picoseconds. The search regions are based on the mass splitting between the next to latest SUSY particle and the LSP, whether there's one or two displaced photons, and then in the plane of Z displacement versus timing difference. And you can see an example of that here, where you can see quite strong separation of the signal at high timing compared to the standard model background in blue. This is, of course, data-driven and based on templates from prompt photons from FSR radiation of a Z, as well as misidentified electrons and jets, which can have a weird timing signature and are taken by inverting the photon ID. So limits are set on the branching ratio of Higgs to this NLSP for various lifetimes, as you can see down here, as well as different masses in these different colored lines. And so they get down to nearly 1% branching ratio of Higgs to NLSP. And you can learn more about this from a talk today from Dev. So that's only the previous results. There's actually a lot new developments in Run 3 that are exciting. I give just a selection from the 3 collaborations. CMS is actually introducing segmentation to their hadromic calorimeter. You can see that by the different colors. And this will allow for new timing and depth signatures. Atlas is re-optimizing its large radius tracking. And this will allow for 50% less CPU use and 20 times fewer fake tracks, which will allow them to process all data. Previously, they only were able to process 10% of the data. And here you can see a nice example of this performance here, looking for k-shorts out to long radius. And this actually shows data versus Monte Carlo and shows the excellent agreement with the brand new minimum bias model that Atlas is adopting for Run 3. LHCb is also using brand new tracking, which will improve their precision and allow for full detector readout, removing their first level trigger. And all three are looking into brand new triggers targeting LLPs, including for disappearing tracks, displaced leptons, and delayed jets. And finally, I only covered recent results from Atlas CMS and LHCb, but there is a much larger community. There's the LLP working group that has a lot of interest and holds bi-yearly LLP workshops, not only to interpret the current results, but also propose brand new strategies. And LLPs are a large focus at SNOMAS and for future detector design. And you can actually see quite a few exciting new experiments now, either reimagining how to use them or brand new ones targeting just LLPs. So we should have a lot of exciting results coming online in the next few years. Thank you.
Okay, thanks, Jeff, very much for taking us through all that, and precisely on time. Thank you very much. You didn't even have to see the numbers that I was trying to flash at you. Okay, so plenty of time for some questions. Yeah, Carlos.
So this 3.3 sigma excess that you see, that I understand that is inconsistent with the signal of a 2 TeV particle, something like this. So because of the speed of light that you detect, a speed close to the speed of light, if I understand correctly, that is a problem with excess. But do you have any alternative interpretation of this, or by now you assume that is a statistical fluctuation?
There are some other possible interpretations of this. I think Leonardo will hopefully go into quite a few of them. At the last LLP workshop, this was also very exciting, so there were some dedicated talks to that. I personally can't speak to any one of them, but I can say we don't think it's just a statistical excess yet. There are models that would still agree with this. For instance, you can see even the next one covering multi-charge particles. Something like this can leave a heavier ionization loss without decaying and without requiring it to move really slowly.
Okay, I think next is Subir.
You said LHCb removed their first level trigger and get better tracking. How do they cope?
So this is
swamped?
for Run 3, and you would think they would be swamped, but the new electronics, they completely redid everything, right? So this wasn't designed maybe a few decades ago. This is all newer electronics that allow them to read out much quicker.
I see. Impressive.
Yeah.
So I don't see any hands up right now, so perhaps I can ask a question.
Okay.
So when you were mentioning this Atlas LLP quote-unquote signal, you said that the measurements in the calorimeter and the tracking in Muon system are consistent with beta equal to 1. But what is the uncertainty in that? Because I've looked in your publications and your presentations, I never see a statement about what range of beta is allowed by the calorimeter in the Muon system.
Okay, that's a very good question and not one I'm prepared to answer right now. Of course, if it's not in the publication, I'll have to talk with the team to see how accurate that is.
I'll keep on trying. Any more questions, comments? Okay, if not, thanks again, Jeff, for a very clear presentation.
Thank you. Remember, talk on Friday dedicated to this, so it should be exciting.
Okay. So next we have another talk on BSM searches. I hope I got the name right, Kostas Theophilatos. Yes. Ah.
All right. So for me, it's both a pleasure and a honor being here, talking to you about some of the most recent beyond the standard model searches on behalf of Atlas and CMS. I will only focus on analysis that don't involve long-lived particles, that those you heard from Jeff. Although you don't see the word supersymmetry being explicit in my title, I promise that it will be on my summary. So let's move on. I don't know if you have already previously appreciated the rate of interesting signals we get at the LHC. We have about 1 Higgs boson produced every second, and the natural question is, what else might be going on and evading our attention so far? So we have observed all main production and decay modes of the Higgs boson. We have measured its mass and the couplings of it with some of the standard model particles. From all what we know, Higgs appears to be a light CP-even fundamental scalar, which, by the way, is just like supersymmetry predicted some decades ago. Now, there is no doubt that standard model is not the final word. However, and so far, we haven't found any new physics. Atlas and CMS routinely experiencing 3 and 4 sigmas that come and go, which is directly proportional to the number of analyses and the number of signal regions we have. On the other hand, we have some long-standing reports for tensions with the standard model. This comes from LHCb and the G-2 experiments that for many are already indirectly to BSM, indirectly pointing to BSM. So that brings me to the first topic of my talk, which is the lepton-flavored universality. Charged leptons have the same interaction strength in standard model, but from effects arising due to their mass differences. No charged lepton flavor violating decays have been observed so far, or have they? Here we can see one of the famous plots from LHCb that has been published in Nature, where the RK variable is compared. The theory is where we expect at 1, and where the measurement stands, it's at 3.1 sigma. And RK tests the electron muon universality. Now, there are other LHCb analyses testing also the tau muon and the tau electron universality that sees also 2 or 3 sigma tensions, but I'm going to focus more on the RK. So the RK is made by studying the decays of a B plus to a K plus and a dilepton system. In essence, what we try to do is to measure how often these 2 leptons are of electron or of muon flavor and compare with what we expect. In order to do that and take into account the different efficiencies of the detector in triggering and constructing the muons and the electrons, we also divide by the corresponding ratio for when the B plus decay proceeds via resonant J psi, which we know that is flavor universal. Now, because this is both loop suppressed and Cabibbo suppressed, it's quite rare, and other effects like the presence of a leptoquark can compete with that and be visible. So this provides a very nice observable that is both precisely theoretically and experimentally. And what CMS and Atlas is doing, so Atlas and CMS try to provide also independent measurements for the RK, but unfortunately I don't have results yet to show. We are facing, both experiments are facing the challenge to trigger low PT electrons. Special triggers for this analysis have been deployed already from 2018 and are now improved for run 3. But to make the long story short, we cannot do yet a competitive measurement with run 2 data alone, and we will have to wait a little bit more hearing about this very interesting topic. However, there are other analyses on studies of big hadron that are coming in the time scale of 1-2 weeks, and so that there will be some interest in that. Now, what we can do while we haven't yet managed to measure directly the RK, what we do is to try to test other physics models that can accommodate the LHCb flavor anomalies and have implications on high PT final states, like this CMS analysis doing, where it selects in 3 bit sets 0, 1, or 2 taus plus some missing ET. Here the model involved is a vector like lepton that it is produced in neutral Drell-Yan and further decays later on to a lepton quark and third generation quark and leptons. The signal is tiny, and in order to have sensitivity on it, 2 neural networks have been trained to discriminate the signal against the QCD and the TT bar, receiving in the input normal things like the rapidity and azimuthal angle PT of the BZs, taus, and so on and so forth. None of the mass range is tested here so far for the vector lepton covering this region. Is excluded, and is, funnily enough, the analysis also see a 2.8 sigma excess. Of course, we should not get very much excited because there are other analyses that try to do similar work and don't see anything. This is not exactly precisely the same. It's a different physics model that is targeted. It's an atlas analysis trying to search again for a signal that could explain the lepton flavor universality tension on the LHCb RK, let's say, results. The final state here is the 1 lepton plus 4 jets plus missing ET. And we have scalar and vector lepton quarks of third generation that allow to decay to quarks and leptons on the first and the second generation. Here again, neural networks are used to entrain for the various signal hypotheses, getting 15 physics in the input, 15 physics observables in the input. Unfortunately, there is no excess observed so far in any of the signal models, and limits as placed as a function of the lepton quark mass and the brushing ratio. You will hear more on Patrick's talk about this in the parallel sessions. Now, another one of my favorites, actually, atlas analysis, although I'm a CMS member, is this one. We have also the possibility to search for lepton flavor violating Z boson decays for when the Z boson decays to an electron and a muon. This is actually quite challenging work to do. The analysis uses a boosted decision tree to discriminate the signal. You could see the signal shape down here from the background, and one of the main backgrounds comes from dileptonic tau decays for when the taus decaying to electrons and muons. You can see how large it is, and the shapes are not very different. So this is quite a challenging analysis. But we have also the handle, fortunately, of the invariant mass of the electron and muon, for where we expect the signal to form a resonant peak around the 90 GeV, while the background will more be a steeply folding continuum. In standard model, the rate of this process is 0, essentially, and the strongest limits today are from Atlas and are at the level of 2.6 10 to the minus 7. Now this brings me now to the other topic that puts pressures on the universality topic, is the Z-2 results. As we all, I guess, know, there have been some new measurement from Z-2 with a precision of a half part per million. It comes in a tension of 4.2 sigma with respect to the standard model. And again, there are thoughts that might be going on due to heavier particles contributing at loop level to the magnetic moment of the muon. Of course, at the LHC, again, we cannot measure this thing directly, but however, what we could do is to try to test in high PT final states what would be the implications of it with some models, like this Atlas SUSY analysis is doing, where we search for a dileptonic, supersymmetric dileptonic process that it is barely produced and further decays to a lepton and a neutrino. The model here assumes a compressed spectrum where the mass splitting between the supersymmetric version of the muon and the neutralino is of the order of MW. And a robust background estimation from the electron muon data is available here. The analysis managed to exclude a very tricky region of the space which is down here, where the mass of the muon is not very far away of the mass of the neutralino. Again, here you will have the opportunity to get more details in Daniela's talk. Moving forward now to resonances, perhaps this is the queen of the excesses we have, or at least I know so far. This is the first pair digit mass search at the LHC. The analysis searches, well, it selects in 4 jets in the final state, like you see an event display here, and then tries to pair the 2 jets in pairs, assuming that the 2 jets come up from a heavier resonance X, which in turn it also produced barely from the decay of the Y. And it looks in 2 dimensions. We have the mass of the digit system that matters, and the 4-jet mass that is related to Y if this decay is there. And interestingly enough, the analysis also sees an excess at the very high end of part of the tail at around 8 eV. And well, we'll have to wait the run 3 to know if more events, when we add more statistics, the more events will add filling up the gap or accumulate near the resonant peak. This is, again, something not to be very, very excited right now, but to have in mind in view of the run 3 updates. Other analysis like this one search again for resonant peaks on the mass spectrum of jets. Here we have the assumption that the new resonance X decays to 2 vector bosons or a vector boson and a Higgs, and this happens in a boosted regime because of the mass of the X, and we can apply standard jet tagging to identify the vector bosons and the Higgs and do the analysis. It's quite actually involved how to do the fit, and it's done on using 3-dimensional fit on MJJ, MJ1, and MJ2 templates. Again, now here, no striking evidence for anything new has been found, and limits are placed for masses below 4.8 and 1.4 TeV for the heavy brothers of W and Z, so W and Z prime, or the random syndrome gravitons. Now moving to supersymmetry. One of my favorite analyses is the dileptonic plus Z plus missing ET. Actually, this paper here from Atlas features 3 different analyses. One is targeting strongly produced supersymmetry, for where we have 2 gluinos produced and decaying to a neutralino and a Z, or leptons and neutralino. While we have also the electroweak version of the analysis, where we have 2 searches targeting to direct a neutralino production to a J-zino and a Higgs or Z. These are Gates-mediated inspired scenarios, as well as the Chargino and a second neutralino decaying to a Z for when the 2 offset Z for when the 2 leptons will come from this decay. Here, one of the analyses used the so-called recursive jigsaw reconstruction technique to define the same signal region they had in an earlier analysis and follow up on an excess seen at 36 inverse femtobarn. In order to get a feeling of the amount of signal regions, here we see the different signal regions in different beams and the total uncertainty on the background prediction on the 3 different analyses. The background prediction is quite precise in many cases. It ranges, let's say, from 10 to 30%, for example, here. Dominant uncertainty is on the theory prediction, while the data-driven background estimate is quite small, is at the level of 3%. This is typical in the leptonic analysis for when the electron muon sample is used as a control sample for the data-driven background estimation. Now, going back to what I said as a follow-up of the excess was in 36 femtobarn. You could see here the event yields on the electron signal region and the muon signal region for two different event selections. The one was involving also an ISRZ. In parentheses, you could see also the background. Unfortunately, when topping out with more data, the excess, the observed events in these two signal regions start to agreeing with the data, and the conclusion made that, the excess seems to get to be gone when topping up. Limits then have been placed, excluding up to 0.9 TeV electroglucinos, up to 1.6 TeV for squarks, and 2.2 TeV for gluinos. But of course, these limits are better visualized in the two-dimensional plane for when we have also the information on the gluino mass and the LSPs, or the LSP and the brushing ratio to the Higgs boson and the gravitino. Now, I will try to move on now to one lepton plus Z plus missing ED final state, trying to compare two analyses, one from ATLAS and CMS. It's not easy to compare two experimental analyses, especially if those come also from different experiments. The similar point is that they both select on exactly one lepton and veto on the presence of a second. And there is where the similarities stop and we start with the differences. The ATLAS analysis targets for a more compressed region of the phase space, going lower on the PT of the lepton and on the number of jets, while CMS use a different trigger strategy at the level of they start from 25 GeV and target more jets in the final state, and they also utilize top W and Z tagging on fat jets. Now, these are the pre-selections. There are a fairly big amount of signal regions in both analyses. In ATLAS is 26, in CMS is around 100. The two analyses use different control regions to estimate the background and define also very different signal regions to do the analysis. Mainly also as a result of assuming different signal models in mind at the design phase of the analysis. The ATLAS analysis used the effective mass of the event and the transverse mass of the lepton. The effective mass is the PT sum of the leptons, jets, and missing ET, while CMS tries to use the angular correlation with respect to the hypothetical W that is present in the event and the lepton, which is fairly correlate for the background. The direction of the two is fairly correlated for background events, while for signal we expect that this is decorrelated because of the two neutralinos in the final state. The CMS analysis use this variable and the Z multiplicity to be in the phase space in signal and control regions to estimate the background. Which is a completely, let's say, different strategy from what the ATLAS have been doing. Now, going in comparing the results, we have here, by chance, a very good opportunity to see how the two compare when they interpret the results under the same model. And they do that in the case of the gluinos, when we have gluino pair production, to Chargino and a W. So we have 4 jets plus 2 Ws in the final state, or one of the Ws decays leptonically. Here, the maximum exclusion rates for the gluino mass is at the order of 2.2 and 2.3 for Atlas and CMS, and they better agree on the LSP, which is they go up to 1.2. Now, considering the amount of differences I showed you before for the 2 analyses, I find pretty remarkable that in the end we get something that doesn't look so far away, and this gives only confidence. Okay, if we move to other examples, like for example, this Atlas model that has been used only in Atlas for interpretation, which has a squark pair produced decaying to a W and a neutralino. The limit to the LSP mass halves from 1.2 to 0.6. And this is actually one of the things I want to point to make, that, that in other words, different models, we should always keep in mind, cannot be compared, and you know, making generic statements on the exclusion mass range for the particles cannot be done without also detailing the fine prints of the models involved. Now going to more 1 lepton plus Z plus missing ET. Actually, this is an analysis released or to be released today or tomorrow. It's approved last week in CMS. It targets and you will hear more in the Egos talk, it targets a compressed scenario where it's cosmologically favored, and the mass of the top quark is very close to the mass of the neutralino, smaller than the mass of the W. Because of the small mass splitting here, the final state involves soft particles, and the analysis needs to start very low in PT, like 3.5 GeV for the muons and 5 GeV for the electrons. In order to have sensitivity in such soft signals, multiple BTTs have been trained for different signal points in a simulated grid of events that ranges from 250 and 800 GeV, and for the mass of the stop quark, and binned in mass splittings between 10 and 80 GeV in units of 10. And what is also special here is that the training also involves it is binned also per data taking years to maximize the sensitivity. Now, if you consider the number of Monte Carlo events we need to do this job, you will ask yourself how this is actually possible. Well, in order to make this possible, some physics ideas need to be put in place. The analysis, what the analysis did, is to group similar signal points and use them for the training. You could see here how the distribution of the PT of the lepton, the missing ET, and the jet multiplicity for different signals with the same mass splitting. So the different colors are the different mass splitting, and the green and the blue here is the main background colors. So the main kinematic difference is for signals that have different delta time, while if we group them all together, let's say select on the same mass splitting and compare different models that have different masses for the neutralino and the stop quark, the kinematics are fairly similar, and exploiting this give us the handle to make this analysis possible. Here we could see the results, again being comparing the data with the background prediction for different signal regions. These are the signal regions, and this is the mass splitting that each signal region has. The analysis excludes top quark masses up to 480 and 700 GeV for a mass splitting of 10 and 80 GeV respectively. Interestingly enough, again, there is some small excess observed, which is, however, mainly located on the 2018 analysis and is not that prominent on the 2017, although the amount of statistics are not so much different. This is 40 femtobar, this is 60 femtobar. Okay. If you wonder where is the 2016 data here, those are in a different publication that have been made earlier from CMS. If one includes those in the results, the significance, the local significance will drop from 2.9 to 2.5 sigma. Again, this is nothing to be very excited with, but something to keep an eye on in view of the run 3. Now, as we all know, in MSSM, we expect multi-resonance structure with contribution from 3 neutral Higgs. Here, Higgs is assumed to be the 125 GeV, and we could search for it. The analysis uses 2 tau leptonic, 2 taus in the final state, and there are 3 analysis branches, one targeting a model-independent interpretation, one vector quark, leptoquark, and one from MSSM. We could see here the exclusion limit placed from the analysis in terms of MA and tangents beta. Again, here, one of the interesting things just to report quickly is that the analysis again sees a small excess at the level of 3 sigma local for masses of 100 GeV and 1.2 TeV. What is actually quite interesting is that the excess, if we see here that the lepton invariant mass is located across all different tau decay modes, that makes it also is what we would expect from the signal. But since the overall significance is not yet above 5, again, this is nothing to get super excited on. Now moving to the remaining time, and then I close to some things for the future. Atlas and CMS both participated in the snow mass exercise, and here I just give you a very quick snapshot of some of the things I selected. The study of the Higgs-F coupling in di-Higgs final state is promising at the level of 4 sigma, and well, the exclusion of the MSSM in terms of the MA and tan beta with the additional luminosity we expect will get will wipe out much larger part of the parameter space. There is also interesting ideas for all hadronic electroweak SUSY, and there is even a dedicated talk for run 2 results in the parallel session. Here, we search for electroweak SUSY, but using all hadronic final states, searching for the case of WZ and Higgs, using a boosted regime where we have 2 fat jets of high PT and large missing ET. Again, here the additional luminosity will drive the exclusion contours from here up to here. And then last but not least, last week we got also a new analysis result on exploring the top corridor via spin colorations. I find this quite interesting to note down because it's one of the analyses also trying to get access on the spin nature of the Stokes quark via the correlations implied due to that on the di-lepton final state. So that brings me to the summary. There is some tension on the lepton flavors. Well, this we cannot be yet sure. We need to wait a little bit more to have Atlas and CMS result, and we will have some of them soon, not for the RK. Standard model, it's fairly fair to say that stands all experimental tests, despite Atlas and CMS have many 3 sigma channels that are routinely routine for large experiments. And I think there are exciting days ahead for run 3, and following up on some of the things we see exciting we see some excess today, and not only, but we have also the high luminosity latency coming and the detector grade, so that we have still a lot of data to look at. And in my view, SUSY possibly still waits for us, and we should not overinterpret the present exclusion limits exaggerating on the mass range of the particles we exclude, and forgetting about the fine prints of the simplified models used to make the interpretation. So that brings me to the end, and thank you very much.
Okay, thanks very much, Kostas. So some questions? Yeah.
Nice talk. I have a comment and a question. The comment is you highlight the di-Higgs at evidence at 4 sigma at the end of high Lumi in the standard model. But I would say that that is the way I would like to see it is the glass half full instead of half empty. And I think that if there is any other resonant or non-resonant production, then one could expect to see something in run free, given so where you are going to be at the end of high Lumi.
Yeah, this is the most pessimistic. It's just the standard model prediction,
Yeah.
And actually the 4 sigma, if we see it in terms of uncertainty, is about signal strength with 50% uncertainty, like saying 1 plus minus 0.5. So, okay, but it's a channel where it can receive a large enhancement from BSM. So it's actually one of the.
It's still already testing a lot of interesting scenarios at the level that is now. And then I have a question, if I may, about the di-Higgs pairs. And you showed that there are 2 events at 8 TeV. Approx.
Di-Higgs or di-jets?
Di-jet, sorry. I misspoke. Yeah, there. So, and with a 3.9 sigma local. But as far as I understand, the second event was found by looking already in this around 8 TeV region. And so I was wondering what that means when you interpret the 3.9 sigma local, if you were already, you are not looking in all area when they found the second one, but they were kind of zooming into the Forsett invariant mass of 8 TeV.
I'm not sure I understand whether you mean they looked on the second one later on.
They found the second, they found first the first event, and then they found a second event, correct? You have 2 events there, as far as I see, around.
Well, the analysis was blind at the high mass part, and
for the second, when they did the analysis for the second event as well, when they found the second event as well.
I don't have this information that it was a progressively time I mean, we start looking one by one and trying then to search for another. I don't have this information. I think it's pretty standard that we blind the analysis and then we unblind only in the very end. Although I was not part of the analysis team, I would bet that this has been done rigorously and following standard procedures, otherwise wouldn't be approved and being public, right?
Okay.
So,
I mean, yeah.
Sorry, perhaps Carlos, if you just permit, because I have another question about this plot. So, what is the mass resolution for the di-jets around 2 TeV? So I noticed that in the 4-jet mass, the 2 masses are exactly the same, but they're not quite the same in the 2-jet direction. Do you know what the mass resolution is around 2 TeV? You understand what I'm saying, right?
Yeah, I understand. Well, I don't have an answer now. Maybe it is on the publication, some more information on this. I mean, we need. Okay. I don't know. We need to see the di-jet of a signal model to take a sense, but relate it. Yeah, no. unfortunately, I cannot give an answer on this. These events are very energetic, and to my view, they are at our limit of kinematic acceptance because they are very, very heavy. So, yeah, we have to see.
Sorry, Carlos.
Yes, I have a question about the Higgs search analysis, the heavy Higgs going to tau tau. Okay, yes. Could you show this? So, in this plot first, you see the blue area seems to be displaced by 2 sigma with respect to the expected region, but then you say that there is an excess at 1.2 TeV, and I wonder why that excess is not visible in the plot as a localized excess, and why is the whole thing is due to, yes.
Okay, you are very careful on seeing this. Yeah, actually this exclusion, I mean, what you say is because the expected is higher than the observed, there's something going on, yes.
Yes.
The answer here is that there are actually 3 analyses doing looking independently on the same data and detailed in the paper. The one from MSSM uses a neural network to do the analysis, and this plot comes from a neural network analysis. The other one that used the model independent has, let's say, a fairly nice observable of the invariant mass of the taus, where we could enjoy a little bit more looking mass distributions. Well, it splits them also in the tau decay mode. So I prefer to choose this way to visualize the analysis and just advertise it so that people can go later on and read the publication.
The obvious follow-up question is, could you remind me what does Atlas see in these regions, or there is no dedicated analysis?
I don't have information, so this should be on the Higgs EXO, because I don't know how the group is on the Atlas EXO or on the Higgs for them. I don't know. From the Atlas EXO, I know that there is some work on the digits, on the digits on this one. I think they will try to cross-check. For the Higgs, I'm not sure if it is inside the plans to make a cross-check. I mean, from Atlas. I don't have this information.
Okay, Nick Mavromatos over there.
Hello. Thank you for the nice talk. I have 2 questions. One concerns the G-2 that you have shown. In the models that you use indirectly so as to verify this result, do people do also, like in the good old days, cosmological dark matter searches to see what your results and how they constrain the dark matter content? Because G-2 was very important for constraining, as you know, the dark matter content, the masses of the... So do you do these analysis or... That's my question. Because the models, okay, you can fit some models, but they may be excluded cosmologically if you fit them in supergravity, for instance.
I think this one still survives the cosmological limits, and that's why it's let's say, in the highlights. But
right.
Making a more generic statement on what else is done, I wouldn't want to.
And my second question is, if I may...
I can
yes,
just confirm that, because we looked at that when we wrote a paper about this a while back.
Right.
And in fact, you naturally get the right cosmological density along that sort of narrow strip there.
Nice. Okay. So, nice. And now, my second question about R-parity violating models, which you haven't mentioned yet. I mean, what is... They still... Probably their parameter space, their available parameter space is bigger than the... minimal supersymmetric standard model, am I right? Or
again, here is nothing that I can say because I didn't review the RPV at all because it was somehow, outside what I've been asked to summarize. So for the RPV, the latest things, I don't have them.
Thank you.
Sorry for not having more information.
No problem. Thank you.
See any more urgent questions? So thanks very much. So one organizer asked me to tell you that something they call coffee will be served downstairs. And then we have another announcement.
Yeah, good morning also from me. For logistic purposes for the conference, could you please sign up for the conference banquet on Wednesday?
session. So this session is a little bit more in the theory side. And we're going to begin with Kumran Baffa about the swampland.
Okay, thank you for inviting me to this conference and in this beautiful setting. I should say that this is my maybe second or third trip to Greece, and each time I come here, I'm quite moved by the Greek symbols for wherever I see, and so I always try to associate them automatically with some things we think about in physics. So as soon as I saw Ioannina, I immediately thought about neutrinos, which is related to some of the things I'm going to talk about. Sorry about that change. So this is based on work with Miguel Montero and Irene Valenzuela in a work which appeared a month ago. And so the basic gist of the main motivation is that consistent theories of quantum gravity are very, very rare and very restrictive. And consistency of quantum field theory by itself is not enough to guarantee consistency of it with coupling to gravity. In fact, far from it. Essentially, every quantum field theory that you can think of, when you couple to gravity, is inconsistent. Now, this may appear as a surprise, but it is true in all the known, and we have a lot of reasons to believe this from string theory, and the ones that do appear to be consistent are very rare and form a measure zero set of possibly consistent theories. So if you just start around writing an effective field theory and think this is okay, it is not okay when it comes to gravity. So one has to be very careful. And it's a very different kind of a logic than from what we are familiar with from quantum field theory. So when it fails, therefore, we have limited tools to replace the notion of naturalness. And the swampland program aims to find these criteria to distinguish consistent versus inconsistent quantum gravity theories. And this should be a replacement for the notion of naturalness that we have in the context of quantum field theories. So the aim of this talk is to combine swampland criteria together with observations in the context of the cosmological hierarchy problem. We have heard a lot about the hierarchy problem in the context of the electroweak theories, electroweak hierarchy, but more impressive is the dark energy being so small, and that's the ultimate hierarchy question, and what we call the cosmological hierarchy problem. Why the cosmological constant in Planck units is something of the order of 10 to the minus 122. So using this, try to argue that we live in a very specific corner of a consistent quantum gravity landscape. So in other words, part of what I'm going to use is consistency argument, parts of observations, which I don't know how a priori is realized in landscape, but if you take these together, the things that you're going to conclude from these put together. So the plan for my talk is, I first talk about some of these swampland criteria, which is relevant for my talk, and in particular, the distance or duality conjecture, which plays a key role in my discussion today. And then I talk about the application to the observed universe. And then I talk about phenomenological aspects and a unification of hierarchies. And in particular, the existence of a single mesoscopic dimension. I talk about the relation to neutrino masses, the Higgs mass, and the prediction of a new ultraviolet scale. So what is distance conjecture or duality conjecture? This is a conjecture we made with Uguri in 2006, and some extension of it, in the generalized version of it, with Lust and Palti in 2019. This is a statement that if you go far away in field space, in consistent theory of quantum gravity, you always get a breakdown of effective field theory. And the way the effective field theory breaks down is that you get a tower of light modes. And what are these tower of light modes good for? The tower of light modes gives you a dual description of the theory. In other words, the statement that far enough distances in field space, you get a dual description is encoded in terms of the duality or distance conjecture by the statement that this tower of states that you get light have masses go exponentially down with the field value. So this is quite bizarre from the viewpoint of quantum field theory, but it is true from the examples we have learned in string theory, and this is the distance or duality conjecture. A deep explanation of why this is true, we don't have. We don't have a deep fundamental derivation, but this is something that we believe is true. More than that, in fact, by LLW's reasoning and in fact the examples, we have seen that the tower of light state is either a tower of light KK modes, as you would get when you have one dimension or more than one dimension decompactifying, or a tower of light string state, as we see in fundamental strings, when you have weak coupling. So you either have a tower of strings or a tower of KK modes. This is sometimes called the string emergence proposal. So that's it, basically. From all these dualities, we have learned this fact. Now, most of this evidence, and this probably is a good tie-in with this conference at hand, comes from supersymmetry. Most of these reasonings we have learned in the context of supersymmetric theories. And so, but it seems to apply to much broader set of classes, even to non-supersymmetric ones. So I should pause and say, how do I know that applies to broader examples in string theory than supersymmetry does? Well, the reason is that we do have examples in string theory which are not supersymmetric, and even in those cases they apply. So therefore, even though the more limited set of examples that we have for string landscape, which are non-supersymmetric, the same reasonings work. So in other words, these principles are not driven by supersymmetry, but supersymmetry gives you a nice class of examples where we can study it in detail. In the context of the de Sitter or anti-de Sitter space, the cosmological constant plays the role of an effective field, or effective parameter, which you can parameterize by exponential of a field. And this you can view it because in the metric space, the distance can be viewed as a distance in metric space, and this gives you this kind of behavior, like log lambda behaves like a field. And therefore, the distance conjecture tells you that if lambda gets very small, if phi gets very large, you should expect to get a tower of states which go like powers of lambda. So the fact that you should get some powers of cosmological constant playing the role of mass scale is automatic from this distance conjecture in the extreme limits of small lambda. Well, how do we know this is true? Well, distance conjecture suggests it's true, but we actually have a lot of evidence for it in the context of negative values of lambda. This is in the context of holography. When lambda is negative, we have ADS-CFT holography, and exactly in these cases, we do know, this actually does happen, that as lambda goes to 0, you get a tower of light state, which go like lambda to the 1/2, in fact. And essentially all the examples we know of, in that context is in the context of supersymmetric examples, and we have these, observe these, and power 1/2 there would give rise to the dual CFT having operators of dimension order 1, for example, so it's not exotic. So this is an example. And for the case of positive cosmological constant, we expect, again, the same behavior, but now we have a bound for the range of alphas, that alpha should be between 1/2 and 1 over the dimension of the de Sitter. The fact that it should be less than 1/2 follows from the Higuchi bound, because these tower of states will have higher than will include spin 2 particles. Whether it's KK mode or whether it's string mode, you will have a massive spin 2 particle, and Higuchi puts a bound on it. So you find that alpha should be less than 1/2. But you expect it to be bigger than 1 over d, because if it was less than 1 over d, that means there should have been a cancellation all the way up to the next factor, which means that you would have something like a supersymmetry, which we don't in general in the context of de Sitter. So there's no reason to have been smaller than 1 over d, and there are other arguments suggesting that this is the bound. So I'm going to take this distance conjecture in the context of de Sitter to imply that there's a tower of states whose exponent goes between either 1/2 all the way to 1 over d. Note that this is a surprising result from the effective field theory. Why do light towers alone dictate what lambda is? You see, this is very strange, because it's telling you the light tower has something directly to say about lambda, and in particular, the lowest end, alpha, being 1 over d, is the same as what you would expect for particles of mass d to contribute, namely m to the d will be a contribution by one loop diagrams to the dark energy. You would think this would suggest that as if the light particles alone dictate the value of the cosmological constant, the lightest particles, which is very bizarre because you have all these tower of particles and you would think each one of them contributes. The Higgs particle, the quarks, the heavier ones. Why only the lightest will dictate the value of the dark energy. Now, what is the evidence for such a dramatic statement? After all, this is the holy grail of physics, the dark energy. Why is it so small? It's related to this question. So let me give you some examples why we think this is true. And the simplest example is non-supersymmetric compactification of string theory. In all of these cases, when you take this string coupling to be small, the vacuum energy, first of all, at 3 level is 0. At 3 level, it's 0, even though it didn't have to be 0. The vacuum energy may have been some value, but vacuum energy in every string theory starts being 0. Why? Not because of supersymmetry. You might have thought it might be because of supersymmetry, but it's not. In fact, bosonic string theory, which has a tachyon, at 3 level has 0 vacuum energy. Why does it have 0 vacuum energy? Well, the diagram gives you 0, and this was famously pointed out, in fact, in the 80s by Witten, the reason for it being the fact that the sphere has SL2C symmetry, so if you divide by symmetry, volume of the symmetry group, which is 1 over infinity, you get 0. And therefore, bosonic string has 0 energy to begin with. And the loop diagrams of string theory give you vacuum energy contribution, which scales like string states, like string coupling, like a string mass scale, and they scale as weak coupling. They are much lighter in Planck units than Planck scale, and therefore they are very light. So strings should be viewed as very light in the limit as G string goes to 0, and therefore this fact that the vacuum energy goes like some power of string scale to the power of D is what we will have in every compactification of these non-supersymmetric theories. So already we have a lot of these kind of examples. Now, this is related to the fact, you might say, why? How is it that a more massive guy doesn't contribute? Even in string theory, the one loop, we say, well, string is nothing but the excitations of these massive modes. Why doesn't these other modes contribute if you do the loop diagram? What happens? In that case, it's modular invariance, which kills contribution of those. In other words, if you try writing down the contribution in one loop, you get some parameters like the Schwinger type computation with a cutoff. And this cutoff, usually you put the UV cutoff. If you put this Planck scale cutoff, you would indeed get the usual cosmological constant problem. However, the cutoff in string theory is dictated by modular invariance to be get string scale. The modular invariance of string theory cuts it off at the string scale, not the Planck scale. And in the limit as G string goes to 0, this is very, very light state indeed, compared to the Planck scale. So this is an example of how this works. And it's miraculous from the viewpoint of field theory. The modular invariance excludes these contributions. It tells you, but in the bottom line of it, it tells you that these are redundant contributions. You have already included it. It is as if it's saying these more massive stuff should be viewed as composite. They are not fundamental. The only fundamental entities are these light modes, which describe the theory. It's like trying to put the monopoles in the loop. You don't put monopoles in the loop when you're talking about weak coupling gauge theory. These are already contributed by the diagrams from field theory. So this is somehow similar to that. So now I come to applications to our universe. Lambda is 10 to the minus 122. This is extremely small. And therefore, we are in the limit of large distance, so we can apply the distance conjecture and get the light tower. So as I just already said, we expect the mass of the tower to go like lambda to the alpha, where alpha is between a 1/2 and a 1/4. Okay. So that's it. From the swampland, I want to get to here, and from here on, we have no choice. As I'm going to explain to you, everything I'm going to say follows from here. And we get to a unique corner of the string landscape. So first of all, if you get the tower of these light states, this in particular means the gravity gets modified because at this tower you have either a string tower or KK tower, which means gravity should be modified. You should see definite corrections to the naive Newtonian gravity. And so you find that the fact that we haven't seen any correction to gravity up to around scales which have to do with the distance of like 30, 40 micron, it already tells you that the only choice with the exponent is the lower end, which is 1/4. So therefore, we expect the mass of this tower to go like lambda to the 1/4 with some coefficient. And the coefficient, if the coefficient was strictly 1, this would give you the mass inverse scale to be 88 microns, which is already ruled out. In fact, it's already known that up to about 30 micron, there is no deviation of Newtonian gravity. So therefore, it's important to know what is the scale for lambda and how small could it be. And we estimate that lambda could be something in the range between 0.1 to 10 to the minus 3. And why is the reason for that? Well, first of all, at large, if you think about this as some scale in your theory, like a length of the scale related to the mass inverse of the particle, there would be a contribution to the vacuum energy having to do with the one loop diagrams, for example. So far enough in the limit as m goes to 0, which means large L, you get the contribution which goes like m to the d, and we expect it to be positive because somehow we are ending up with a positive cosmological constant, so you're ending up somewhere here. But we do know that we want to get some kind of a metastable or at best some kind of a quasi-de Sitter vacuum that we live in. Therefore, it should deviate and bring it down. The fact that it doesn't go asymptotically like this should come down somewhere already tells you that lambda is less than 1. So that's that already. But lambda cannot be too low, and the reason is that if lambda were too low, the exponent will change from 1/4 to some other power. So for the exponent not to change, it gives you a lower bound, 10 to the minus 3. And so this is a rough estimate of how it could be. So this gives you a mass range, or mass inverse range between 0.1 to 10 micron. So then we use the string emergence proposal, which is what is this light tower? Is it a string tower or KK tower? Cannot be a string tower, because if it were a string tower, this scale of energies around the electron volt, we would be saying that there is electron volt string scale, and that would have a dramatic modification, not just to gravity, but gravity will become strong at that scale, and we have no evidence for that. So it cannot be a string tower. It is a KK tower. So it has to be a KK tower, Kaluza-Klein tower, in this scale. How many dimensions are opening up? Well, that's the last thing we need to figure out to find which kind of corner we have. If there are small n extra dimensions opening up, getting bigger and bigger, you expect that the higher dimensional Planck scale to be given by the mass scale that we have to the power of n over n plus 2 in Planck units. So this is the higher dimensional Planck compared to the Planck scale that we are viewing in our dimension. For n bigger than 2, if you have more than 2 extra dimensions, this gives you that the higher dimensional Planck scale is less than TeV, and that is ruled out because we have already checked that in experiments, in LHC in particular. There is no evidence for that. And therefore, the only possibility left is n is 1 or n is 2. Now, n is equal to 1 is not, n is equal to 2 is not possible, and the reason it's not possible is that there are bounds coming from the fact that if there are 2 extra dimensions of the order of the micron, you get 2 quick cooling of proton-neutron star, early neutron stars, and this is not compatible with the observations. In fact, with 2 extra dimensions, to be compatible with the observations, the length scale associated with the extra 2 dimensions should be less than 0.00016 micron, and that is not what we are having here. It should be of the order between 0.1 and 1. So 2 extra dimensions is ruled out. The only option is single extra dimension. And for the single extra dimension, these coolings give you the length scale less than 44 micron. So again, consistent with the bounds that we are proposing. So we are really limited to one choice, therefore, from all of these observations, to one mesoscopic dimension in the length scale between 0.1 and 10 micron. Now, this also leads to a fundamental new scale in physics, which means the Planck scale in this extra dimension. And this you can just compute it easily, and you find that the extra dimension, the higher dimensional Planck scale is in the scale of 10 to the 9, 10 to the 10 GeV. Now, you can ask, well, how does this compare to the large extra dimension scenarios, which Antoniadis and others had studied a while back? And the motivation there was a little different, and in particular, the motivation there was to bring down the Planck scale to the electroweak scale to try to explain the hierarchy, electroweak hierarchy. And in that case, now, for example, in that scenario, we know that if you want to go there, for example, in ADD scenario, the number of extra dimension is 4 or more, and their size is the length scale is 10 to the minus 12 meters or less. So this gives you both a different motivation and a very different parameter range. Whereas for us, our motivation is not to solve the electroweak hierarchy, but the cosmological hierarchy, and we get and consistency of quantum gravity, which is based on swampland ideas, and this gives you one extra mesoscopic dimension of micron range. And so you can basically imagine some kind of grand unified brane, which has to be localized, otherwise it cannot be extended, the extra brane that we live in the whole dimension, because if it were, the coupling constant will be super weak for the GOT model, which is not. So it should be on a brane which is localized inside this extra dimension which is long. Now, it turns out that neutrinos give you an interesting picture, and this is the kind of ideas that people had explored in the context of large extra dimension, whether or not the neutrinos, the right-handed neutrinos, could come from some fermions in the bulk. And indeed, in this scenario is very natural in the context that we are doing, and similar idea was explored in the paper by Karina et al. And you can compute, you can estimate the mass of the corresponding neutrinos if you couple the neutrino to these right-handed fermions in the bulk. Now, the fact that there should be fermions right-handed in the bulk, there should be fermions in the bulk is natural because the cosmological constant is positive, and the sign of the vacuum energy is positive for fermions. So you have to have more imbalance of fermions. So there should be fermions in the bulk of the theory because of positivity of cosmological constant. And so from this you can estimate the masses of the neutrinos, and you get a formula which is similar to the seesaw mechanism, except that what usually is m got here is replaced by m hat, and the coupling constant here, y squared, is the coupling of these modes to this, which if you put it in the range 10 to the minus 2, 10 to the minus 3, you get a reasonable mass for the neutrinos. So not very unreasonable that this is the way that you get the neutrinos explained. In fact, it is more than that. You will have these bulk modes, fermions, which are sterile neutrinos. So you have a whole tower of these sterile neutrinos in the bulk, whose energies are electron volt automatically because they are having a micron scale. And you could ask, what is the hierarchy between these sterile neutrino masses and active neutrino masses? Well, there could be very different scales. But if you insist that the hierarchy is not huge, they're roughly of the same order, it will fix the Higgs wave. So if for some reason the bulk dynamics drives the dynamics of our brane and thus impacting the Higgs potential to set the Higgs wave, it will fix the Higgs wave in terms of parameters of our theory, in terms of the dark energy itself. You find that the Higgs wave will scale like the 1/6 power of the dark energy, and with the corresponding couplings of order 1, gives you roughly the right range for the Higgs wave. In other words, this is relating the Higgs hierarchy to the dark energy hierarchy. Now, there's instability in Higgs potential based on what we know from the standard model and observation at the scale size of about 10 to the 11 GeV. And it's interesting, or it's natural to speculate whether or not this is related to the higher dimensional Planck scale we are having, which is 10 to the 10 GeV. So by the time you get to 10 GeV, you have this higher dimensional Planck scale, and you will have extra charged states in addition to higher dimensional objects that we haven't talked about, and therefore it will modify the effective potential for the Higgs, in particular, perhaps by restoring supersymmetry at that scale and so forth. So it might be naturally related to this instability that has been observed in the Higgs sector. So there are other phenomenological aspects of this theory. I'm beginning to run out of time, but one aspect is neutrino oscillations. Could it be related to short baseline anomalies? That's one idea around for explaining them involves electron volt sterile neutrinos. So there are some ideas along these lines, and we will hear more about these kind of ideas in this conference. So this is automatically given for us. We are already having this without working. It's already part of the scenario without us requiring it. Could it also have some impact or relation with ultra-high energy cosmic rays? There is a cutoff, which is around the 10 to the 10 GeV that we are talking about. As is well known, these cosmic ray energies fall off near that range. And there's an explanation by the GZK mechanism, the GZK limit, having to do with the interaction of these cosmic rays with the cosmic microwave background and the attenuation of the beam. But it was pointed out that right after our paper that this, in principle, if this happens within the sphere in which this beam is not attenuated, there must have some other origins for this attenuation, which may be this extra-dimensional Planck scale effect, the fact that gravity gets more strongly coupled. And this should know much more data about this in the next couple of years. Could be related to H-naught tension, because many of these early dark energy scenarios involve injection of energy at the EV scale again, which is the scale having to do with this extra dimension. So if the dilaton of this extra dimension plays a role in injection of energy, which is natural to expect of the settling of this extra dimension, this could be related to this. And there could be also some wider options for dark matter, for example, for primordial black holes, as was explored in a recent paper in this scenario. So let me summarize. I've run out of time. So the idea that swampland, and in particular the dark energy, gives you a unified picture about all these hierarchies, quite tantalizing. It gives you a realization, a potential realization of Dirac's dream of unification of hierarchies, the fact that things seem to be related by powers. And for example, the macroscopic size of our universe, the Hubble length, is lambda to the -1/2. The mesoscopic dimension will be lambda to the -1/4. The neutrino scale is lambda to the 1/4. The Higgs scale is lambda to the 1/6. And the extra higher dimensional Planck scale is lambda to 1/12. So it's a very natural connection between putting all of these together in the context of a single parameter, which we still haven't explained why it's small. I didn't explain why lambda is small, but it unifies all of them together into one question, one possible hierarchy, in this case, the cosmological hierarchy. So I should say that it was tempting to call this extra dimension Omicron, but we decided not to do that. Actually, it's more than you think. Omicron has a given length scale. It's 0.1 micron. So there is more than one reason to have called it Omicron, but we decided not to. And anyhow, I will stop here. Thank you.
Okay, so CBS, the first person I saw.
Discussion was predicated on the assumption that there is a lambda of order 10 to the -122 in natural units. How would your discussion be altered if it turned out to be 0?
Well, if it's 0, I have nothing to say.
Thank you.
Yeah.
What are the implications for inflation models, and in particular, if you measure, the tensor modes, et cetera, how does that fit in with this story?
Right, so that's a very good question. It's not specific about the talk I'm giving, but the swampland condition do say a number of things about inflation, and in fact, issues or restrictions that you could potentially have inflation. So inflation has difficulties being realized in string theory context, and so there are other possible scenarios that people are talking about in the context of early universe and how the early universe came about. So for example, in one of these models, the tensor mode does not even exist. So the question of what are the alternatives you would come to. But in the context of inflation, if you strictly take the inflation itself and try to say, okay, are there possible realization of them? They are very extreme limited possibilities left over, which all give you extremely small values for R. And so I think, and then they will have highly fine-tuned initial conditions and all that. So I think I would say that if either we should say inflation is not consistent with these, or if it is, it's extremely fine-tuned, one or the other. There's one question here also.
Oh, sorry.
Oh, yeah, no, okay.
Maybe I can answer this first.
Thank you for the talk.
Thank you.
When you wrote the mass matrix for the neutrino, you assume that the neutrino that is in the bulk has also Yukawa coupling
with Higgs and the left-handed neutrino in order to write?
Yes. So what we assumed is that there was this bulk fermion, and its wave function is dictated by the usual 1/√r, and that overlap with the gut brane gives you the coupling up to order 1 factor, which we called y.
But then the mass of this neutrino is Majorana type, you wrote? In the,
the one we took was we wrote the Dirac one, but either version one can try to do the Majorana version as well.
Mm-hmm.
Thanks for the very nice talk. You mentioned, I think briefly, that if you assume the active and sterile neutrinos are around the same mass, it helps with the Higgs. Is there anything in the model that predicts that, or is that just an assumption you made? And is there any issue with results from Microboon and others today? So,
as you can see, I have used some things from observation. So the question is, which ones am I going to use from observation? So from the observations, we already know that we can already predict, if you assume you know the Higgs wave, which we cannot derive, that you get the right scale for the active neutrinos from this model. Namely, we needed a coupling as order 10 to the minus 2 or 10 to the minus 3, which is, we didn't derive it, but it's not unreasonable. Now, when I said we can derive this connection, was not to use the fact that we know the Higgs wave. If we did not know the Higgs wave, this is very ambitious, I want to derive the Higgs wave, all I had to say is that the sterile neutrino and active neutrino have similar mass scale. One is eV, one is milli-electron volts, and one is the electron volt range. So if you assume they are in the same range, you get the right Higgs wave.
Thank you for these very nice ideas and talk. I have a question which is related to Shubias. If the lambda is 0 and somehow arises dynamically through some phase transition, still your distance conjecture should be valid.
Oh, yes, yes. No, I think he was talking about this actually 0, not in the IR.
No, that's what I'm saying. But if it is dynamical...
No, if it arises one way or the other, if the infrared value that people have measured of lambda is correct, if the measurements are saying lambda is not 0 and they are correct, then this applies.
And also, suppose that it is actually 0 and what we see as Shubias says is through some specific place in the universe. There may be another scale which could lead to your distance conjecture, which we don't know yet in quantum gravity, in the sense that it may not be the lambda, but they may be something else. Am I right? Or
well, depends on what else is true. I mean, I'm only talking about the conventional explanation of what we know of dark energy.
That's right. That's right.
Yeah.
But there might be another scale in the theory which could still...
Depends on what are the scenarios, yes.
Sure.
If you have extreme small parameter,
right.
We should have an extreme small parameter. The reason is that the size of our universe
That's right.
is much, much bigger than Planck. So there's some extremeness somewhere.
That's
so
right.
However, the strategy is going to have some distance conjecture apply. So basically this theory, this idea is telling you, if you have one extreme, namely the size of our current universe, there must be another extreme explaining it. That's the size of the mesoscopic dimension. They are not uncorrelated. You cannot have one thing large and the other one to be all Planckian. And of course, we don't explain why we are large, but we say, if this is large, then that's large. But why one of them large, we didn't explain.
Thank you.
Okay, this should be the last one, I think, in the interest of time.
Do you have any explanation of charged fermion mass hierarchies?
There are a number of ideas in the context of F-theory GOT models where we wrote papers about it, and the idea was relatively simple. This is the idea, and this could apply also to these models. And the idea was that the fermion mass hierarchy naively should be related to have that the rank of the mass matrix should be in some approximation just rank 1. So in some approximation, only the top one would have mass. Now, there's correction to it, and the correction to it gives you an approximate local symmetries on these branes which are touching each other. So, and the reason the rank was 1, which had to do with the fact that branes touch at one point. It's a very simple idea. And the fact that there are corrections to it is very much like Frogat-Nielsen mechanism in the context of the branes, which give you certain powers of these symmetries. So we got a hierarchy which, to a very reasonable degree, works. So there are some explanations in these kind of models.
Okay, so I think we should move on, so thank you very much.
Thank you.
Okay, so apologies for the delay. Next speaker is Claudia Duram about UV and IR.
Okay, thank you very much. Thank you very much for the organization and for the invitation. And I have to apologize in advance. There's going to be no SUSY in this talk, so feel free to leave already if you're not interested. So the spirit of this talk will be quite similar to what we just heard about, although the implementations will be quite different. So I'll explain a little bit the difference. But the overall philosophy is to try to understand when we have a low-energy effective field theory, and I'll be mainly interested in gravitational ones, but a lot of what I'll be talking about apply to any effective field theory at low energy, how we can make communication back to the UV, or how we can use constraints from a potential embedding within a high-energy completion in the Wilsonian sense without being specific to a particular UV completion. So I like to remain as agnostic as possible from the UV completion. So of course, ideally, I'll have my favorite model of quantum gravity, which we know is consistent and unique and leads to a unique model of the realization in the low energy world. But unfortunately, that's not the situation. Even if I start from a potential high energy completion, there's a whole landscape of low energy effective field theories, and I need to find some different ways to segregate between these different type of models. So of course we could just leave observations and experiments dictates which one out of this low energy framework seems to be consistent and model for the world, for nature in itself. But we can also, in parallel, use some theoretical bounds, some theoretical priors, in trying to segregate between these different type of effective field theories. And so within this framework, we do come across some low energy descriptions of the world, and this is for anything that you want. They can be for the standard model, it can be for beyond the standard model, it can be for cosmology, or it can be for gravitational frameworks. We may have some model of the world which may seem to be completely consistent with observation and experiments, and also self-consistent in the sense that it satisfies all the conditions at low energy that you want it to satisfy, for instance, stability. But we know that for some of those models, they will never be able to be embeddable within a standard high energy completion within some type of assumptions that I'm going to ask at high energy, and I'll be quite specific in the type of assumptions that I have at high energy. So it's irrespectively of what we have at low energy, some of them will see that no matter what I like to have at high energy, and it can be string theory, or it can be other type of completion which we haven't even come up with, so long as it satisfies some specific criteria, which I'll argue are relatively natural, although we can argue against that, we know that some of those models will never be embeddable within that ultimate framework. So a lot of what I'm mentioning here seems to be quite similar to what we just talked about within the Swampland conjecture. However, it's kind of two different complementary approaches, I would say. And in the era of assumptions that I'm imposing on myself for what my high energy completion should satisfy, I'm not entirely sure how to compare the type of assumption I'm going to be using here and those applied for the Swampland conjecture, which are much more gravitational involved type of conjecture. But what I'll be considering is using some scattering amplitude, the notion of unitarity, locality, Poincaré invariance, and causality as my fundamental assumptions for what physics should satisfy at high energy, independently of what the precise realization is at high energy. And based on those assumptions, I'm going to cascade down to some bounds that the amplitude of a low energy effective field theory should satisfy to be ultimately embeddable within a high energy completion. And I'll be working with those assumptions. If we wanted to, we can make more and more assumptions, and we could go to specific string theory compactifications if we wanted to, but I don't want to at this level. But all of those assumptions, particularly that of locality, will be the level of locality that I'm going to require for myself will be implemented within string theory. Okay. So within a low-energy effective field theory, you may consider a low-energy scattering amplitude. For instance, there may not be the best example in posterior, but for instance, I can consider a photon scattering amplitude, and everything I'll be talking about here will be 2-to-2 scattering amplitude, elastic. And I can consider what this scattering amplitude is within a low-energy effective field theory point of view. So if I'm in the Mandelstam complex plane, I'll be here. S is the center of mass energy square, and I can analytically continue the scattering amplitude in the complex plane and know that I have pole associated with the particles that I know exist within my low energy framework, and then there's branch cuts associated with the loops of the light fields, and then the heavy fields which I don't even know about. So within some region of validity of the low-energy effective field theory, here, for instance, within the regime of validity of QED, I can compute my low-energy scattering amplitude, and it is trustable within this low-energy effective field theory. Beyond this low-energy effective field theory, the notion of amplitude still exists. I simply cannot use the model at low energy to compute it and trust it, but the amplitude itself still exists, and I simply need to implement new layers of physics, new states, for instance, or new physics, to understand how the scattering amplitude behaves at higher and higher energies. And then maybe an infinite number of layers of energy all the way up to an ultimate UV completion, if there is even such a thing. And a priori, the decoupling of scales that occurs between the low-energy effective field theory and the ultimate high-energy completion tells me that I should be able to live my life at low energy without needing to be too sensitive with what's happened at high energy. But the statement of causality, in this sense, implements itself or encodes itself within a statement of analyticity of the scattering amplitude in the complex energy square plane, and it is this statement of analyticity that directly relates some properties of the amplitude at high energy with properties of the amplitude of, at low energy. And so it is this notion of causality which allows me to make the communication between high energy physics and low energy physics, in the same sense that we know that having superluminality at low energy typically implies a violation of causality. This implementation is really done at the level of analyticity, in this case of the refractive index, but it's this very same type of conditions. So now that I have this connection between what the amplitude could be at high energy and what it is at low energy, I can impose some conditions that I would like my amplitude to satisfy, I would like physics to satisfy at high energy. In particular, it seems reasonable, no matter what the ultimate high energy completion of everything is, for V6 to remain unitary, and in this sense it manifests itself through the optical theorem, requiring that the imaginary part of the amplitude should remain positive, definite. And typically, we write it as the imaginary part is really the discontinuity of the amplitude through the real axis, but that's not so relevant for here. Now the question of causality tells me, from analyticity, tells me that I can relate what happens at low energy with what happens at high energy. You can do this specifically through our Cauchy integration formula. And if I further require a statement of locality, which in here really requires the statement of the Froissart band being satisfied, or Froissart-like band being satisfied. So this is probably the weakest of all the assumptions. Or by weakest, I mean the less well-motivated assumption, but in non-gravitational effective field theory, this is well-motivated. Then I can directly relate this unitarity, the positivity of the amplitude along the branch cut, with the positivity of the amplitude when computed within the low-energy region of the validity of the effective field theory. So for any effective field theory to be ultimately embeddable within a standard high-energy completion satisfying those properties, I need, for instance, some elements of this amplitude to be positive definite at low energy. And this we understand quite well. We understand that no matter what happens at high energy, you integrate out modes which contribution to the spectral representations are always going to be positive definite from the optical theorem, from unitarity. And so as you cascade down to low and low energies, all you can do is add up those modes and leads to a contribution at low energy, which is all the more positive. So a violation of this condition will directly imply a violation of one of these assumptions within the high energy completion. So within non-gravitational effective field theories, all of this is pretty well understood. And we get actually an infinite number of positivity bound at low energy. I just represented one of them here for illustration purposes. But this is very well understood. And it's through those type of positivity bounds, for instance, that we can make the connection between subliminality and causality within a low energy effective field theory. So what I'm interested in now is trying to, before I go to gravitational effective field theories, let me just say that we can apply that just, for instance, for physics beyond the standard model. I can consider, just as of illustration purposes, the operators beyond the standard model. So for the SMEFT, the standard model effective field theory, for W and Z bosons operators, coming for dimension 8 operators. The dimension 6 operators are less constraints at this level. This is not meant to be read. It's just to show you that there's lots of operators that you can write down. And then in the region of parameter space, so in this axis are the coefficients, the Wilson coefficients of these operators for dimension 8 W boson operators. You can see that one would expect from experiments to be able to constraints in being in this type of region of parameter space in blue, whereas remaining within the region of parameter space, which would be consistent with having a standard high energy completion, is actually quite a complementary region. And this is quite old. This comes from a few years already. It's evolving quite rapidly. By now, we actually have compact bounds on those type of effective field theories, and so this is making a lot of progress. So I don't have any pictures for that at the moment, but it is very much a work in progress. And so you can apply those type of considerations directly for the SMEFT, if you're interested in. But what I'll be interested in is applying them for gravitational effective field theories, where the connection between these assumptions and the implications within the low energy effective field theories are much more murky, even putting aside the fact that some of those assumptions may be a little bit less justified within the gravitational framework. So even though they may be a little bit less justified, particularly that of locality or satisfy the Froissart bound, we do assume, one can show that when expected to satisfy the Froissart bound for gravitational amplitude in more than 4 dimensions, and in 4 dimensions, I'm going to take it as an assumption, take into account that whatever bounds are obtained from a low energy effective field point of view, if I see observationally that I violate them, then that may indicate that there's a violation of the Froissart bound from a gravitational effective field theory point of view. I'm not going to talk about the rest here today, but that also leads to subtle relations with how causality is implemented within low energy effective field theories, which may be relevant for other type of constraints on gravitational framework. But the reason why applying this type of considerations within low energy effective field theory that include gravity, even if you may not be interested in gravity per se, you may just be interested in some, I don't know, fermion scatterings, which a priori doesn't include gravity per se. If gravity is part of the game at some extent, you can't prevent from having it playing along and to also include a gravitational exchange amplitude that will come into the scattering amplitude. And the issue with gravity, as we all know, also related to the fact that it's non-renormalizable, is the presence of gravitons which saturates the Froissart band. So it leads to a graviton exchange pole, a T-channel pole, which residue grows like R squared that precisely saturates the Froissart band and therefore compromises the direct application of the positivity bounds. So we have poles like that for any exchange of massless particles, for the photon as well, but for the photon it will grow like S, and so it will satisfy the Froissart bound, whereas for the graviton is the first instance where this type of relation occur, and this is all related to all the complications we know about gravity in a standard effective field theory sense. So with this in mind, we know by now that if you're considering a gravitational amplitude, where in the absence of gravity, let me send m plane to infinity, you would be able to infer that the Wilson coefficients that appear and then related to the coefficient in the amplitude here, I call it C, should be positive. when you switch gravity on, actually no longer needs to be positive definite. There's a mild level of negativity that can be present, and that is manifested typically in nature. And this is relevant, for instance, if trying to use those type of positivity bounds to prove the weak gravity conjecture that tells you that gravity should be the weakest force compared to electromagnetism is obvious, but compared to any other U1 force as well. And you can relate those type of arguments with causality considerations as well. So now I'll try to use this logic in an inverse way, and I'll try to see instances where these coefficients actually do appear to be negative, and try to understand how I can use that argument to learn about some of the properties of the physics at high energy, really at very high energy. So the logic is actually very simple. As I mentioned before, you know that typically when you integrate out modes, you'd expect to have a more and more positive contribution coming in, just because the spectral representation is positive. And so if in the gravitational setup you end up with having a quantity which is negative at low energy, it must mean that it was very negative to start with at high energy, and very negative by an amount which knows about the infrared. And so this is this simple logic that I'm going to be using here. But I'll see how this gets implemented directly at the level of some constraints on the radio behavior for any amplitude, including a gravitational amplitude. So we have the amplitude at low energy, or any energy really, can be written as your dispersion relation, so integrating out all the modes, and this is all positive definite for T positive, and then some residues and stuff. This is not the T-channel pole, it's just the residues in S, which are all under control. So if you write the amplitude through this dispersion relation, you may ask yourself where the T-channel pole, in this case, is hidden. And the only place it can be hidden is actually in this dispersion relation. So this dispersion relation converges for S for T negative, but as T crosses 0, it is what it leads to the T channel pole through some type of radialization of the amplitude. So to understand how this T channel pole is hidden in here, what we need to have is that this integration, this dispersion integral, should converge for T negative, and so that will be the case assuming the Foucault bound. So we'll have the imaginary part should behave at large energy as a power of the energy going like alpha smaller than 2. And as T crosses to 0, we should start seeing this divergence occurring, building up to the T channel pole, and that tells us the coefficient in this power law should become slightly larger than 2 as you cross 0. And so this gives you the well-known Bezier type behavior. The coefficient of the behavior of the amplitude for large S, for large energy, should start at 2 and then have a positive contribution in T, so that you have this divergence occurring as you cross T to 0. The issue of a lot of what we want to say is that the positivity of the amplitude is proven for T positive and not for T negative, and so we really need to go through this divergent part to being able to use any type of positivity as we like it. But that's okay, because, and I should say, this type of radio behavior we know is typically expected to happen in string theory, but here we can prove it. We can prove the existence of this behavior without any notion of string theory. This is completely universal for any gravitational effective field theory if you assume a Foucault bound. So if you assume this, you're starting with this type of bound. Okay, so what I'll do is I use this knowledge that the amplitude should behave like this radio behavior at sufficiently high energy. How high, I don't know, but sufficiently high energy, it should behave like this radio behavior, to being able to integrate it out and match out with the pole, strip-sacked it out, and then the remainder of the amplitude should match out precisely what I have from the remainder of the radio behavior. So I think I have enough equations so far. I'm not going to go through that all in details. I can talk about it later if you want to. But really what happens is that you can consider this amplitude, separate out the dispersion relation going all the way up to when the kick-in of the radio behavior, and then from the radio behavior onwards, I can assume the radio behavior, integrate it out, subtract it out, part of it removes the pole, and the other part of it is what I have here. So I end up with a relation relating part of the amplitude at low energy, which is simply the amplitude subtracted out this G-channel pole, so this is completely finite at T0. Some dispersion relation, which are all finite and well-defined. This is also finite at T0, and I can bring it back to T positive, and then the remainder of the radio behavior. So that will allow me to relate the radio behavior at high energy with some properties of the amplitude at low energy. So all of this is finite at low energy, and I can use this to make a transition between negative T to positive T, where now the imaginary part of the amplitude is positive. So one of the things is we'd expect the behavior of the radio behavior, the radio scale that enters here, to depend on high energy physics, thank you, much higher than whatever happens at low energy. And so the expectation would be that we have a positive contribution here for the radio behavior that scales like whatever energy comes in at high energy. Maybe that's a string scale, maybe that's another scale of quantum gravity, I don't know. And that has to be smaller, because this is positive, to the contribution at low energy, which scales like the mass of the lightest field that comes in at low energy. And so this expectation seems to make complete sense. It's the same thing as what I explained before. You start with something relatively small and positive at high energy, and you integrate things out all the way down to low energy, and you get more and more contribution, so you have a larger contribution at low energy. Okay, so this seems to make sense, aside from the fact that when you compute things explicitly, as I mentioned before, you do end up with some slight level of negativity at low energy. And so this slight level of negativity at low energy has to be mapped back into the scaling of the radio behavior at very large energy. And so there's an IR-UV mixing that occurs. And we can do that explicitly, for instance, looking, for instance, at graviton-photon scattering using loops from standard model particles. I'll save you some of the details. What you can do is take some specific indefinite scattering amplitude for graviton-photon scattering, and you see that the remaining, so the T-channel pole subtracted amplitude is negative, it's actually negative definite, and carries the scale, unsurprisingly, of the lightest mode that is present in the low-energy effective field theory. If this was positive, again, those expectations would make complete sense, because you would have expected this contribution to be larger than that one. The key issue here is that you have some negativity. Of course, it's suppressed by the Planck scale, so none of that occurs when the Planck scales go to infinity, but it is still present and still carried to some extent by the mass of the electron. And so for this to make sense, this expectation cannot be the real story. What should happen is that this contribution here has to be negative, but not slightly negative, actually sufficiently negative from the outset so as to being able to carry out the level of negativity that you have from electron loops in this particular setup. So the negativity or the amplitude of whatever characterizes the radio behavior at high energy should be carrying out the mass of the electron. And in this case, because we're computing photon graviton scattering, you also have the charge of the electron coming in. But actually, the same thing occurs in other gravitational amplitude. You can do that for just pure gravitational amplitude, and you see the same type of thing occurring where now the lightest massive mode that we know so far is the neutrino, so this will come in at the very least. If you consider axions, you would have even a lower effect. I'm finishing now. So what happens is that the light loops from the low energy do contribute to the radio behavior to a large extent. And since I'm being flagged with my, with my red flag, let me just summarize here. I'll just leave that as a conclusion side. But really, we do see some type of UV-IR mixing that has to occur within those logic, at the very least, if you're assuming a Froissart-like band, which then leads to a radio-like behavior that has to be controlled to some extent by the mass of the lightest fields that exist in nature. Thank you.
I have a question. In the context of gravity, we expect the effective field theories to be so limited that are rather striking, and it's more than just restriction to a positive regime or negative regime of parameter space. It's like measure zero set. Do you see any evidence or how such a thing could arise in this context?
Yeah, I mean, I think that's very interesting, and this is precisely this type of arguments which is used when you're trying to use that for the weak gravity conjecture. You'd expect everything to come in from the trivial string contributions, and here we see that this argumentation is not true. You really, the loops from the light mode will start dominating, and so that is really what will dominate at high energy.
Maybe I didn't explain my question clearly. So the weak gravity already looks like an inequality. So similar in some sense to the effective field theories. No, I'm talking about more dramatic ones. Like, for example, we expect the n equals to 4 Yang-Mills with rank bigger than, I don't know, 22, 23, to not have any completion in quantum gravity. So it's all of them are ruled out. It's not just the parameter space, the whole thing is ruled out. Do you see anything which along these lines will tell you, oh, this is going to rule out all of those?
Not at the moment, yeah. I have to say this is still very early days. We're finding new rules on maybe not a daily basis, but on a monthly basis. The application of that for gravitational, as soon as you apply gravity, is very, very much work in progress. But at the moment, it's not that dramatic, no.
Hi. So I have two small curiosities. So one of the points I want to ask is that, so your scattering amplitude calculations are all done in Minkowski space, or do you do them in Euclidean space and then analytically contribute to Minkowski space?
Yeah, so that's a very good question. At the moment, this is all in Minkowski, and we need to, there's a big level of Poincare invariance, so we need to assume. So if you, as soon as you try to apply those type of bounds to, what were you interested in actually?
No, I'm not asking that if you go from Minkowski space to Euclidean space, do you?
Euclidean, yeah, no, sorry, Euclidean space, yeah, no, you can do it in Euclidean, you can do it in, no, yeah, that makes no difference,
so,
yeah, that's
so
fine.
all your results are valid directly in the Minkowski space?
Yeah, you assume them in Minkowski space, but you can do it in Euclidean and analytically continue. That is okay.
And with all these terms, okay.
Yeah. But it's all Minkowski. Yeah.
Okay. Thank you.
Yeah. So you need the Lorentz group, but you can, if you want to, you can just compute them in Euclidean and analytically continue. That's all fine.
Maybe a related question. In some scattering process, the T-channel. The parameter cannot be positive, okay, kinematically. Do you assume some analytic continuation there? So this is, you get elastic scattering, you can have up to 0. You can't make it positive. At least you make some analytic continuation. I'm saying just phase space.
Yeah. I'm assuming from the statement of causality, I am assuming analytic continuation. But are you talking about the Euclidean amplitude not being positive?
I'm talking that if I do such kind of amplitude, if you like to calculate the phase space, you find that the T is at most negative. Okay, so there is no positive contribution physically. There is no physical support to that amplitude.
Yeah, so that is okay. Yeah.
Yeah, but you can't. I mean, you cannot physically continue. You have to make an analytic continuation in your description there.
When you compute it in Euclidean?
No, not Euclidean. You assume that you are not going to the Euclidean. So if you are staying in the Minkowski space and you are doing a phase space integral, so as you do any experimentalist, you will find that there is no positive T-channel support for that kind of amplitude. Okay, so that's one thing. The other thing is, okay, we can discuss later. So the other thing is, at least you have other type of scattering amplitudes you may have, but for that kind of elastic, no. So the other thing is, of course, all this for a sub-bound and the double subtractions you are doing. People have done that in the past, in the Higgs case and so on. And it seems to me that it boils down that then you have all these criteria, that your theory is automatically renormalizable. Is that because you do no more than 2 subtractions, right? Your dispersion relation is no more than 2 subtractions.
No, it doesn't mean that your low-energy effective field theory is renormalizable.
But your dispersion relation can have more than 2 subtractions. That's the question.
Your dispersion relation could have more than 2 subtractions.
In your analysis there, because so far you
so
consider only
that's fine.
2.
If it has more than 2 subtractions, it's even better. But you don't assume that it is renormalizable, and actually that's the very reason why we can act it on gravity at low energy, right? So the low energy EFT, it's an EFT. By no means is it.
Yeah, I understand. But the point is, if your theory for every loop is you can do up to 2 subtractions, so you know this tells you there is a cross indication, strong indication that the theory is renormalizable. That's what happened, at least as far as I remember, from my works with Papavasiliou in 1996, 95.
Yeah, no. So when you apply it to the other operators, there's no notion that it's renormalizable. No, you apply it for the SMEFT operators, then by no means renormalizable. And it doesn't push you in a region of parameter space where it's renormalizable. No.
A very quick question, which I should have asked long ago. Very nice talk, first of all. You assumed that quantum gravity, in a sense, is a unitary theory where the scattering matrix is well defined. Am I right?
Yeah.
Now, what about if it is not?
Yes. Yeah.
Because it doesn't have to be local, all right?
Yeah. The level of locality that I'm imposing is as I send S to infinity for finite t. So if this is violated, you can tell me maybe it's violated by a little bit, and I can still apply 3 subtractions, and so we have things to say, and they are bounds in these cases, a little bit weaker, but I can't say anything about the radio behavior in that case. If you want a more dramatic violation of causality than that, yes, you can't say anything. This is one of the assumptions. But then you can turn the story around, right? You can start with those assumptions and let nature decide where we are. If you really violate those bounds, then that's your proof that
It could be non-local,
yes, so I mean, the level of non-locality that you have in string theory will still be sufficient in here. Yes, absolutely. So this is for those classes of effective field of ultimate completion that satisfy that level of no, absolutely. Then there are some work, there's some very nice work that parameterize the departure from locality and try to put that back into some relaxed bounds at low energy. So you can start playing.
You make a boundary state in the quantum gravity which could affect.
So any type of resonances, all of those.
That's what I'm saying. Goes beyond the effective field theory.
So now any type of resonances or black holes, all of those, that is all fine. Okay.
These are fine. These are not my boundary state, but it could not go beyond the effective field.
Yes, absolutely. So.
Yeah. Okay, I think maybe we have to stop there because we're running out of time. So thank you very much.
So it's 25 minutes for the talk, right?
So can you then do 25?
I'm going to make sure that you give me 20.
So I'll use that. When this gets to 25, I'll get you down to that. You have 5 more minutes. If you choose to go over, it eats into question. Okay, so straight on with Ruth Gregory about that whole.
Thanks. And I've got my own timer as well. So this is definitely something completely different from the other talks this morning because I'm someone who's very gravitational and so tends to think quite geometrically. So in this case, I just want to tell you about some work that I've been doing over the past several years now, which revisits some old ideas about vacuum decay, but adds a new twist in the sense of adding in black holes and gives a very different answer. So have to stay near here because I've been hearing all the other slight odd things with the sound. So the background of this is really talking about the possible metastability of the Higgs vacuum In other words, this was already referenced in Kumran's talk about the fact that at high energies, the Higgs coupling, if you run it just within the standard model, becomes negative. And therefore, it opens the possibility of our universe being metastable. However, I should say that some reanalysis by both ATLAS and CMS 3 years ago now seemed to be giving a slightly different picture, pushing the top mass down. Nonetheless, I'm going to proceed saying, what if our vacuum is metastable, and what are the consequences? And standard calculations, our gold standard of the sort of Coleman-de Lucia type of calculation, give an insanely long half-life for the universe. However, those calculations are extremely idealized, and if you just take back one message from this talk, it's the fact that black holes change the picture completely, turn it on its head. So, in brief outline, I'll first review the Coleman method, trying to focus in on the essence of it rather than going into it in detail. I'll then talk about what changes when you have a black hole, and then I'll compare to black hole evaporation and kind of give the headline result. So, our picture about quantum tunneling was developed really in the 70s by Coleman and others, and it's sort of telling us how we describe vacuum decay in quantum field theory. And so our vacuum is understood as an effective state. It's something where the Higgs field sort of sits at a minimum, potentially. But of course we know that our potential is only effective. It depends on temperature and scale. And just for some nomenclature, if we live in a local but not a global minimum, we call it the false vacuum, whereas a global minimum is referred to as the true vacuum. And so the idea is, if there's a barrier in between, like so, that we can have tunneling from this false to the true vacuum. And so this gives us a first-order phase transition because our order parameter is discontinuous, and therefore we expect some sort of bubbling of our vacuum. So the key ingredient of the standard methods of computing amplitudes for tunneling decay are to Wick rotate to Euclidean time and then solve equations of motion. So we get a sort of saddle point for the path integral. And then we calculate the action of this solution by looking at the difference between the solution with a bubble and a solution without a bubble. And this gives us a leading order exponent of the amplitude for decay. A slightly more intuitive way of computing this, and this was emphasized by Coleman in his papers, is what I like to call the Goldilocks bubble, which is the just right bubble. Because you can imagine a bubble of true vacuum forming inside the false vacuum just by quantum uncertainty. If it's too small, then it's going to recollapse, because forming a bubble, it costs energy to make the wall, but we gain the vacuum energy from the difference in energy from the interior. So if it's too small, there's too much surface area, too much cost, and if it's too big, it just tends to be too expensive to form. So there's a just right size where the bubble is just big enough not to recollapse. And so that's our Goldilocks bubble. And we can get a good back-of-the-envelope calculation as to what the action of this is, because we look at the cost of forming the wall, which is the area times the wall energy per unit area, which is here sigma. And of course, this is a four-dimensional. We're in Euclidean dimensions, so this is our area of a sphere. And then we have an energy gain because we've gone to the false vacuum inside, so that's the volume times. This epsilon is the difference in vacuum energies. We make the solution stationary with respect to the radius of the bubble. We get a value for that just right bubble radius, plug it back into the action to give us the leading order approximation to the amplitude for decay. So I should just emphasize here, for the purposes of this talk, I'm just going to say I'm tunneling from a positive energy to zero energy. That's a matter of convenience because it's just easier to draw the pictures, as you'll see. But the same sort of arguments work whether you're going from de Sitter to anti-de Sitter, between vacuum to anti-de Sitter, de Sitter, de Sitter, etc., etc. It's all the same sort of principle. This is just for convenience. And so that was a Euclidean sort of argument, but does it mean anything real? If I rotate Euclidean solutions back to time, back to real time, then something which is a bubble or a ball, when analytically rotated back, becomes a hyperboloid, because our ball is just r squared plus tau squared is a constant, and so that gives me r squared minus t squared is a constant. So that's a hyperboloid. And so the real-time picture is we have our bubble fluctuating into existence, and then it starts to expand, and it rapidly approaches the speed of light. So it looks like the Euclidean picture has some validity. So this is probably a familiar story to many, but I think people take this Euclidean picture very seriously as a result. Whereas I do regard it as a tool. So, of course, I'm talking about vacuum energies, so therefore I should really be thinking about gravity because energy gravitates. And so if I have a positive cosmological constant, I'm in de Sitter space-time. So here is a de Sitter space-time. De Sitter can be represented as a hyperboloid in one dimension up, so that's hence those hyperboloids. And the various sort of drawings on them represent different coordinate systems. So I'm going to talk here, this is the sort of, again, I'm giving a fairly sort of standard methodological approach, but here if we want to think about tunneling with gravity, we're sort of thinking about quantum effects with gravity, whereas I'm going to be very agnostic about what a theory of quantum gravity is. We don't necessarily know that, although some would beg to differ, but what we do feel confident about is how we calculate quantum effects within gravity below the Planck scale. So below the Planck scale, at some level, what we do is we assume space-time is some sort of background, essentially classical, and then we quantize around it. We use this when we do inflationary perturbation theory. We use it or these ideas when we do black hole thermodynamics. And in this case, this is using it for looking at non-perturbative solutions in field theory with gravity. So it's all a fairly well-trodden path. And it's simply this idea of a sort of semi-classical Euclidean partition function approach that was pioneered by Gibbons and Hawking in the 70s. And so we have our Einstein-Hilbert action, our standard model action, and this is, we simply have this as our overall action for our full theory. Saddle points should be unambiguous, but of course fluctuations have to be taken with a bit of a pinch of salt. So it's that kind of approach. So if I go back to that picture of de Sitter space, or my ball and my hyperboloid, if I ask what is de Sitter space-time, well, I just said it was representable as a hyperboloid in one extra dimension. And similarly, if I Wick rotate to Euclidean time, de Sitter space is represented as a ball in one extra dimension. So it's an S4. And if I have an instanton, then I might expect that I have a bubble. I have a bubble inside my sphere which is flat because I'm going from positive to zero vacuum energy. So my instanton should look like a sphere with its nose cut off. And so I replace my false with true vacuum. So it looks like this over here in the left-hand corner. So this was what Coleman and De Lucia computed in the early 80s. They showed how to do this. They didn't take quite this approach. What they did was they looked at the Euclidean Einstein equations, and they solved those for a thin wall. So I should emphasize that this is, again, I want to be able to draw pictures and give the essence of the calculation without getting into the deep and dirty details. And this is easiest if I assume I have two very closely separated vacua with a significant barrier in between. So I have a very thin wall. And this was what Coleman de Lucia did. And you can do this in Einstein gravity by what's called the Israel formalism, where you pretend you've got a thin shell. And so here, this is the pictorial way of doing it. This is my de Sitter space. This is my instanton bubble. So I should calculate these two actions and subtract to get my overall amplitude. I can play the same Goldilocks bubble trick. I compare my cost of the wall, which is pretty much the same, and then I look at the energy that I've gained by going from false to true vacuum. And this is now more complicated because the volume of the tip of the sphere that's been cut off is no longer just a flat interior of a sphere. So it's a bit more complicated, but it's the same idea. And you get the same answer, which was the Coleman de Lucia result. So this is this action down here. And so this was what was used to kind of estimate the probability of standard model metastability of vacuum decay. And of course, it gives that insanely long half-life of 10 to the 140 or so years. So it seems like, well, essentially there was no reason to try and have another lawsuit to stop the LHC switching on. However, one of the things that strikes you when you're looking at those Coleman bubbles is how idealized they are. You have absolutely nothing in your de Sitter space. Everything is maximally symmetric and it's all very smooth. Whereas in nature, first-order phase transitions almost never take place in that way. They're always dirty, messy, and often seeded by impurities or some sort of catalyst. And so this really resulted, or this work resulted from thinking about what if you throw in a gravitational impurity. And so the idea there is to tweak Coleman de Lucia and put in a black hole. So this actually was explored back not long after Coleman and de Lucia got their result, but when it was first looked at, people did not compute the Euclidean action properly, so that's the real difference here. And so it turns out this is adding a black hole. It's not making the situation maximally messy. It's saying, can we move away from that extremely symmetric Coleman case, add in something that breaks the symmetry, but not so much that you don't still have good calculational control. So here you're just going from O4 to SO3, and you still got enough symmetry to be able to sort of do an awful lot with pen and paper until almost right at the end. So here I'm still staying within the context of a thin wall bubble, which is not actually what the standard model instanton is, but I'll get to that at the end. And you can prove that the exact solution is something like Schwarzschild or Schwarzschild-de Sitter or anti-de Sitter. In other words, you have a space-time with one cosmological constant, lambda plus, and an effective black hole mass, m plus, on the outside, and a different one on the inside. So just to stress, when I say it's a black hole mass m plus on the outside, it's not to say that the black hole is there in that bubble. It's simply that the local tidal forces are that of an m plus black hole. And the interpretation is m plus is the seed. There's a seed mass, seed black hole m plus inside, let's say de Sitter, and that is then catalyzing the decay. So you can play a similar Goldilocks type of game. Now, before, we just had two cosmological constants in the radius of the bubble, and so we sort of had one parameter to maximize. Here, we have two black hole masses in addition, and so for any given m+, there's a family or a range of remnant masses, m-, that give you one of these instanton bubbles, but there's only going to be one that has the lowest action. And so that is the instanton that mediates decay. In general, solutions depend on Euclidean time, but it turns out that this lowest action bubble has a very specific format. If the black hole is really small, then the bubble depends on Euclidean time, but has no remnant, so it goes from a black hole to no black hole. If the black hole mass is larger, then the bubble, the lowest energy bubble, does not depend on Euclidean time, but there is a remnant black hole. And it turns out that this last case is the one that's relevant for standard model decay. So you can think about, I mean, obviously in the end you actually go ahead and crank the handle and do the hard work of solving the Euclidean equations, but you can also sort of see how this is going to change that balance for the Goldilocks bubble. Black holes have periodic time. That was what was shown by Gibbons and Hawking in their papers of the 70s. In essence, you can think of that as corresponding to the temperature of the black hole. And so you can think about this change of balance as coming from this periodic time. And then if you do the calculation, you know, you really roll your sleeves up, what you find is for the static bubbles, the action for the decay is simply the difference in area of the two black holes, the seed and the remnant. And this actually feeds in very nicely with a sort of Boltzmann suppression. If the black hole becomes lighter, its area goes down. That corresponds to a drop in entropy. Drops in entropy should be exponentially suppressed. So this all kind of fits very nicely together with sort of thermodynamic intuition. But what happens, or what we see, is that seeded tunneling is much more likely than Coleman-de Lucia tunneling. However, that's not to say that the black hole will definitely catalyze vacuum decay, because black holes also evaporate, the same rules of that semi-classical quantum gravity game. So what we have to do is to compare the two rates, the rate of black hole evaporation to the rate of tunneling, or the tunneling half-life. Now, black holes have a temperature inversely proportional to mass, and their overall lifetime is therefore a power law dependence on the black hole mass, whereas our tunneling rate, we're sort of thinking, is somehow exponential. So you might think evaporation wins, except the prefactor, so our lifetime instantaneous evaporation rate is going like 1 on m cubed, whereas the prefactor is very small. Now, if we ask what is this exponential factor for decay, it's this difference in area, so our seed area versus the remnant area. And if I want to just again do a back of the envelope calculation, I'm going to replace an area with 2m, not quite right, but it's close enough. And then what we notice when we did the full Monty, the full calculation, we found that the seed and the remnant masses were very close together. And again, that makes sense because the actual standard model bubble is just a sort of Higgs profile or Higgs cloud around the black hole. And that's relatively, if you think of how weak gravitational coupling is, that's going to change the mass, but not by order 1 in Planck units. So delta M is quite small, and it's also relatively invariant as you go change your seed mass. So roughly speaking, again, this is just to get the sort of shape, your tunneling decay goes roughly like exponential of minus m delta m. And so if you plot that branching ratio, you see that you get curves of this sort of general scale, and I can see you can't In fact, I'm not even sure I can see the scale on the bottom. So here, this is the branching ratio of how much tunneling is preferred. On the bottom line, you're looking at the seed masses in Planck units. So here, this is delta M of 10 to the minus 3, so that would be sort of 10 to the 15 or so GeV scales, 14, 13. And here on the bottom, 10 to the 3, 10 to the 4, 10 to the 5, and 10 to the 6 Planck mass black holes. So you're looking at sort of kilogram to ton range in this particular case. So this was just very quick and dirty, but it's proof of principle that you can, in fact, get tunneling to happen preferentially. What we, of course, did in reality was a full numerical calculation looking at a profile. The standard model bubble is very thick. And so if you want to make a thin wall, you have to add a sort of ad hoc phi to the 6th term to the potential. And so here, these are those curves for an actual bubble for the thin wall here and gradually switching off, going to a standard model thick bubble. And what we actually did was sort of fitted the potential. We did a sort of 3-parameter fit to the full full running standard model potential so that we could easily sort of fiddle around and go through, have a little wander through parameter space. This is a sort of standard model region, and you're sort of heading in that direction as the top mass goes down. So essentially, you know, more or less, what you find is that the black hole becomes preferential seeding decay. Here you're sort of up at around a ton at least for some of these. However, what you've got to bear in mind is by the time you get to a black hole of mass a ton, it has a very short lifetime, so this means that the decay is almost instantaneous. And what's this referring to? Well, to get to that size of black hole, it has to be a primordial black hole that's just evaporating now. And so in essence, what you're doing is you're kind of co-constraining the running of the Higgs coupling versus populations of primordial black holes. So just to wrap up, just the last couple of slides to put a pitch. This is really, I always view the Euclidean method as a tool. I don't necessarily think it represents something real, and therefore, how much do we trust it? I know people are coming back and asking questions and saying, oh, the Euclidean method's wrong. I wouldn't say it's wrong, it's just a tool, and it seems to give an answer that is reasonable. But can you actually test some of these ideas? Obviously, quantum mechanical tunneling is well tested, but field theory tunneling not so much. And so I'm now involved in a quantum technologies consortium, quantum simulators for fundamental physics, which plans to test precisely that and some other interesting fundamental physics in analog systems in the lab. And so there's a false vacuum decay work package, which is going to actually look at relativistic vacuum decay via sort of Bose-Einstein condensates, putting atoms in a trap where their effective field theory is like a relativistic vacuum. So this is sort of our consortium, which is funded by a quantum technologies program by STFC. And so you can see we're sort of scattered throughout the UK. It's not just cosmologists or people doing gravity. We've got cold atoms theorists as well as experimentalists. So we've got quite a range of people. So it's kind of quite fun to sort of be, they're trying to send me back to my grad school days and getting me to do data analysis. So there you go. I'll finish on that. Vacuum decay is a good example of quantum effects in action with gravity. And my message is that black holes can really change the picture. Oh, here it goes. There we go.
Thank you very much for that wonderful talk. Do we have some questions?
Bet we don't, because it's so different. Oh, well. I was just going to say it's so different. Nobody likes it.
Hi, nice talk. So I have one curiosity. So is the computation of tunneling rate has any issue with gauge dependence in your cases? Like Are all the analysis done in a gauge invariant manner?
Which are you talking about?
The tunneling rate.
Right, but which gauge? Are you talking about coordinate invariance or are you talking about gauge fields?
Gauge fields.
Okay, so in this case, no, it's purely a Higgs bubble.
Okay. I see. So then, if you involve some gauge fields, then do you? Does you remain? So can you comment on what do you expect if you involve some Young-Mills fields, let's say?
So we haven't sort of added in gauge fields. I'm not really sure how they would contribute, what sort of profile you might expect to have. Generally speaking, though, the result for the static bubble being the difference in entropy of the black holes, that result holds for whatever matter source you have. So that is a robust result.
I see. Thank you.
I have two questions. The first one is, if you add the conformal coupling to the Higgs, I would expect it could change the calculation quite a bit. Has this been done?
So no, our approach is simply to say, if the vacuum is metastable, how does a black hole affect the tunneling amplitude? So we're not actually going and in essence, we're coming and saying, guys, if there's either we've got no primordial black holes or there's physics beyond the standard model, I know which I'd put my money on. I'm fairly certain that the vacuum probably isn't metastable, but I think this is perhaps one of the reasons why I would say you really don't want a metastable vacuum. So, yep.
Okay, and if, in fact, the types of black holes we are discussing are the black holes that make dark matter, what would that estimate be?
Okay, so if you want primordial black holes as dark matter, that means they're still black holes. So that's not a problem, at least as far as we're concerned, because, if they're currently in their state as, if the black hole mass is above about, I guess, 10 to the 16, then in essence they're not going to be evaporating now, so they're not in contradiction. Of course, we're sort of gaily mortgaging our descendants' futures because eventually they'll come into this danger range, but there's absolutely no inconsistency with dark matter primordial black hole models.
I think one comment, I don't know, maybe you'd like to comment on that. All this calculation is done by assuming there is no Planck scale suppressed operators. Is that correct? Because the presence of these operators, as you already know from arguments, may change considerably, drastically the properties of the vacuum, and may actually be so catastrophic that you may face a vacuum decay even as we speak.
Yeah, so I guess what we've looked at is just looking at some sort of running of the quartic coupling, and our Higgs, I guess, probably remains 5 or 6 orders below the Planck scale. Don't know if that... Yeah, so I think we just, in terms of the sort of main result at the end, we just had the sort of standard one. When we were looking at making thin walls and going between thin and thick walls, then we did have a 5 to the 6 operator, but I think we were just trying to stick with it, not trying to put in a lot of ad hoc terms. And again, this result about the difference in seed and remnant masses, it doesn't matter what extra you add, as long as you're interpolating between one vacuum and a lower vacuum, you still get that difference in entropy. That's for the static bubble. That result is sort of really holds.
Thank you for the talk.
So by demanding that the vacuum is stable in the early universe, can you set constraint on the distribution of primordial black holes evaporating at early time?
So for this doesn't so much apply to the early universe, because in essence when we're doing these tunneling calculations we're assuming that we're at a sort of relatively low background temperature, so the only hot thing, if you like, that we have is very localized. It's the black hole. We're not in some sort of ambient thermal bath. So I would not want to apply these calculations to the early universe at high temperature.
Thank you.
Well, I want to make the obvious comment that all these calculations apply for the present case in which there is no new physics affecting the Higgs from here to 10 to the 10 GeV, right?
Absolutely,
That is most likely not the case.
I would agree with you, absolutely. In fact, this conference, I think everyone would want to agree. Yeah, no, absolutely. But I think this is another reason why we want VSM physics. So it's a good point.
Okay, so let's leave it there. Thank you very much again. Okay, sorry. Now you can hear me? Yes. Okay, very good. So which is the bottom is this one. So we learned in the previous talks, and we all know that the vacuum energy plays an important role in the history of our universe, and so it's very important to control its value, and to what I will discuss in this talk is precisely the how and why the vacuum energy takes a finite value in string theory compactifications or in string theory in 10 dimensions. It's not obvious that it's finite in string theory because you have an exponentially growing number of states, and sometimes can appear tachyons in the spectrum, so you want to find which are the conditions under which the vacuum energy is finite when you compute it in your, at least at one loop. So in the mid-90s, Kit Dean has started to look at this problem, and he conjectured actually that when you break supersymmetry and you want to keep the vacuum energy finite, then, which means the spectrum does not have to contain tachyons, so that you are free. I mean, we learned from the talk by Vafa this morning that in string theory you are protected in the ultraviolet, but still you can have divergences which come from the infrared, and these occur whenever tachyons are present in the spectrum. So the absence of tachyons, actually, he conjectured it was actually due to the presence of a hidden kind of supersymmetry, which he called misaligned supersymmetry, which somehow dictates the full spectrum of excitations of the string theory, which now is not paired anymore at each mass level, as in any supersymmetric theory, where you have the same number of bosonic and fermionic degrees of freedom, but actually starts oscillating with a pattern which is given, which is plotted here in this figure. So you have some, say, start with some fermions at lower mass, then you have more bosons and fermions and so on and so forth. And despite you have an exponential growth here, I'm plotting the number of degrees of freedom in a logarithmic scale. Although you have an exponential growth in the number of degrees of freedom at each mass level, then the fact that you have this misalignment can guarantee that there are no, the vacuum energy that you compute is finite, at least for closed strings. So I will talk, I will focus in this talk in the case of closed strings. So nothing to say about open strings. Now let's try to give a more quantitative look at the conditions under which tachyons are absent in the spectrum, or if you like, under which the vacuum energy can be finite. You can have this pattern. So normally the partition function is what determines, its integral is what determines the vacuum energy, and the partition function itself is a combination of states from the left movers, from the right movers and the left movers. And the way you pair these states, which are characters in the rational conformal field theory, and I will stick to rational conformal field theories for simplicity. The way these are paired is via a matrix. Nij is a matrix of signed integers, positive for bosons and negative for fermions, and these are highly constrained by modular invariance. So you cannot just pick up, pair the states from the left movers and the right movers of your strings at your will, but you have to really impose very stringent constraints which select only a finite number of possibilities, which means finite number of string vacua in any given dimension. Now, when you expand this partition function in terms of powers of Q, so this is a generating function for the degeneracies, and then you find this expansion in the argument of the characters with some powers, and the coefficients are precisely some integers, and when you impose level matching, so you take the same energy, if you like, for the right movers and for the left movers, then when you impose this level matching, the A and N are precisely the number, the sign number of degrees of freedom that you have at the nth mass level. So it is the dot is here, I can't see it. So these are precisely the log of those coefficients are precisely what I'm plotting here. So then, you can wonder, you can ask how the states, these coefficients, grow. So how they behave. I mean, what is the number of degrees of freedom that you have in a given sector of your theory? So when you pair a right mover oscillator, let's say, with the left mover once, then at a given mass level, and then you can show that actually these degrees of freedom, the degrees of freedom in this sector grow exponentially with n, and the growth is dictated by the degrees of freedom that you have on your worksheet. So the C total here is the sum of the contribution from the left movers and the contribution from the right movers, and as I said, is related to the square root of the central charge for the left degrees of freedom and for the right degrees of freedom which live on the worksheet. So this is, these are encoded in the conformal field theory that you study. Then Keith Dines proved that actually whenever tachyons are absent, then so the fact that the power expansion here that I reported here doesn't have negative powers of Q, so it means that you don't have negative masses, then implies that actually the effective growing of what is called the sector average degrees of freedom, so when you sum overall the states in your string theory, with the matrix Nij, which is the one that enforces the GSO projection, which gives you a given string vacuum in a given dimension. The growth actually is smaller, must be smaller than the one dictated by the degrees of freedom, the central charges of the conformal field theory. And so the C effective, this has to grow with the same power square root of n. There is still an exponential growth of states, but with a coefficient which is smaller than the C total, which I introduced before. Then he conjectured that actually C effective, because he didn't have a control, of course, you can just prove that C effective has to be smaller than C total, but he couldn't compute effectively what C effective is, and then he conjectured that C effective actually should be equal to 0 in, when tachyons are absent. Then we have this, he argued, even further in the paper, that actually was precisely that whenever C effective is smaller than C total, then you have absence of tachyons and oscillations in the spectrum, which is you have misaligned supersymmetry. So we have in his paper, he put out 3 conditions, oscillations, misaligned supersymmetry, or C effective is less than C total, or even a conjecture that C effective is equal to 0. So now the natural question is, which, of course, how somehow these conditions are related to each other, and actually which one of these is really the signature for the absence of tachyons in the spectrum, and which one is the condition which guarantees you that the vacuum energy that you compute at one loop is actually finite and not diverging. So in the recent years, so this paper by Keith is from mid-90s, but in the recent years there has been quite an activity in studying non-supersymmetric constructions, and actually there has been some work where it was shown that indeed you have, whenever you break supersymmetry and you are away from a tachyonic region, then you have a pattern of degrees of freedom which follow. You have degrees of freedom which follow this pattern, and then the C effective is actually smaller than C total. So the question is now. We try we ask ourselves the question whether this is enough in order to have absence of tachyons, where these oscillations are really a signature for the absence of tachyons, which means cancellations of various states in the computation of the free energy. So here you can see when you compute the free energy, you have positive contribution, negative, positive, negative, and then you can hope that there is a cancellation among these states in order to give you a finite value for the cosmological constant. And so we started to analyze actually the full sector, the full spectrum of the full ensemble of string theories that you can have in 10 dimensions, in the lower dimensions, and both, whenever, of course, supersymmetry is broken, and actually we studied both the tachyonic and non-tachyonic one to see whether, some of the properties are really related to the non-tachyonic theories, or they exist also when tachyons are present in the spectrum. So in 10 dimensions already, you have a lot of theories of consistent string theory vacua. There are the 4 supersymmetric ones, at least for close-oriented strings, which are the type 2A, 2B, and the 2 heterotic strings, which gauge groups SO8, SO32, and E8 cross E8. But then there are also a lot of the non-supersymmetric vacua, which are associated to consistent GSO projections of the spectrum. And out of these 8 non-supersymmetric vacua, actually only one, which was also discussed in his talk by Kumrum Vafa this morning, is tachyon-free, which is the SO16 cross SO16 theory, whose spectrum is encoded in these partition functions. These are the characters of the conformal field theory that you have in 10 dimensions, which indeed encode all the excitations of the left movers and the right movers. But there are plenty of tachyonic theories. And in particular, you have 0A and 0B theories, which are purely bosonic, and I will not talk about them at least in the first part of the talk. But then you have at least 5 you have 5 tachyonic, non-supersymmetric heterotic strings, which have a gauge group SO32 or SO24 cross 08, SU2 squared E7 squared, SO16 E8 or SU16 cross U1. So the idea was to study all these theories and to see what happens in the distribution of degrees of freedom and what happens to the growth of states for all these kind of constructions. So in this talk, I will just focus on the non-tachyonic tachyon-free O16 cross O16 theory, and to one of the 5 tachyonic ones, in particular the simplest, but we did the analysis for all the models that are discussed here. So, of course, in this case, there are no tachyons in the spectrum. The tachyon could emerge from this sector here, but actually level matching tells you that there are only massive states which come from this sector, whereas for the SO32 tachyonic theory, then you do have a tachyon which is in the fundamental representation of the SO32, which is in the 32-dimensional representation, which obviously would lead to a divergent free energy, so vacuum energy. So let's start from a simple, let's say, qualitative analysis. So from these partition functions, you can then expand the partition functions in powers of q. You can see how many states you have at each mass level. And then you find that in both cases, you have a pattern which resembles the one which was proposed and studied by Keith Dines, where you have indeed misaligned supersymmetry. You have an alternation between bosonic and fermionic excitations with an envelope which is symmetric with respect to let's say, the horizontal axis. Although in this case you don't have any tachyon, the theory is tachyon-free, and in this other case there are tachyons which are present in the spectrum. Then you can do a more quantitative analysis, and for this, you have to see how the characters actually, how the exponential growth of degrees of freedom for each character, for each sector of the theory emerges. So in general, the character can be written as this Taylor expansion with some coefficients, A and I, which tells you for the ith sector of the theory how many degrees of freedom you have at a given mass level, which is given by n plus HA, and HI is related to what is called the conformal weight of the character, which is the little h, minus C over 24, which is related to the central charge of your theory. Now you can apply the circle method of R.D. Ramanujan in order to get an estimate, which is the growth of these coefficients as n goes to infinity. And the expression is quite cumbersome, but it can be derived, and it was studied by Kani and Vafa in the 90s. And so I just want to focus on a couple of things in this equation. So first of all, the coefficient, the growth of the coefficient depends on many contributions from many of all the characters of your theory. These gammas are the representation of some suitable SL2Z transformations when acting on the set of characters of your rational conformal field theory. Here you have some phases, and the most important thing is that you have the contribution which depends on n and depends on the HI, so this object here, or the various characters, which are the argument of a Bessel function. Now, this is a Bessel J, so in principle you would say, okay, then the growth of these coefficients is just polynomial. However, whenever HI is negative, and this occurs whenever you have this little h is smaller than C minus 24, you have that the Bessel J, of course, becomes a Bessel I, and then this gives you the exponential growth of the various degrees of freedom. So the exponential growth is essentially associated to those states, those characters, which have a negative which have a weight which is smaller than C over 24, which means a negative HI. And now every theory and every string theory has such a state, because this is precisely represents the identity of the conformal field theory. And therefore, every state has an exponential growth. But what is important is that there may be more than one state which is negative h. Okay? So, as I said here, the most negative one of these of the characters, so the characters with the most negative hi, plays the role of the identity, and then its contribution to each character is universal, simply because for this kind of states, the gamma here, it's just the S matrix transformations, the representation of the S-matrix transformation, the one which sends tau in -1 over tau, and then this says that the identity goes to contributes equally to all the characters and then to all the coefficients A and I for each sector I. Therefore, so if you take into account this fact, then you can say that these coefficients have a universal growth, which is the most effective one, where you have an exponential square root of h, the minimum h, the absolute value of the minimum h times n, but then you can have subleading contributions, and this subleading contribution can be of different type, can be due to the other states, other characters, which have a negative hj, which is, however, in absolute value smaller than h, actually, in absolute value is larger than it's smaller than H minimum. But then there can be other contributions which are related, oh sorry, it's, you see here you have a sum over several terms, and the Bessel I would be given by its, there are several contributions which go like 1 over L, where L is an integer that you have to sum up to the square root of n. So there can be a lot of contributions, and the important thing for us is that the coefficients of these terms, not of these ones, but the coefficients of these terms, this P, I, L, N, which depends of course on the integer n and on the level you are interested in, on the masses of the states, these are periodic functions of L. So both the Pi and the Pij are periodic functions of L. And they satisfy a very interesting property, is that if you now sum over all the integer n which run into within a period, so from 0 to L minus 1, these coefficients are equal to 0. Okay? And this is crucial in order for what I'm going to say later. As I said, and stress once more, the contribution of the identity is actually universal. So, because the contribution of the identity is universal, then for any string theory, which is described by this kind of spectrum, so for a fixed Nij, then you can see that the vector, the sector average number of degrees of freedom, which is you sum over all the sectors, and you look at what happens when n goes to infinity, takes this universal form. So there is the universal contribution from the right movers, or the left movers in this case, sorry, and the universal contributions from the universal growth rate from the right movers, and these are weighted by this Nij. Now, of course, these, as I said, do not depend on the sector I and j, because the growing rate is universal, and therefore, when you sum over all the sectors, whenever the Nij, the matrix, the GSO matrix, is such that, okay, Nij is equal to 0, then C effective is smaller than C total, because these, the H left and the H right, are precisely related to the central charges of the theory, and so since this term cancel, and all the other states grow with a smaller, have a smaller growth rate, then automatically C effective is equal to C total. Now, so this is this cancellation is not really related to the absence of tachyons, because actually, aside from the 0A and 0B theory, which are purely bosonic in 10 dimensions, then all the non-supersymmetric heterotic theories, both the non-tachyonic one and the tachyonic ones, have precisely bosons and fermions in the spectrum, and they satisfy this condition that the sum of the Nij is equal to 0. So for all this theory, independently whether you have a tachyon or not, then C effective is smaller than C total. So the condition for the finiteness of the vacuum energy actually cannot be just this property, or simply the oscillations of the spectrum of the degrees of freedom, because these are common features both for tachyonic and non-tachyonic theories. Now, what about the subleading exponentials? Now, it was proven last year by Kribiori, Parameshwaran, Vrase, and the fourth author, which I never remember actually, is a student of them, I apologize. But they proved that actually, because of the property of these P's, that if you compute the sum over all the periods is equal to 0, then in the SO16, SO16 theory, so when tachyons are absent, then indeed there are cancellations. And the cancellations are quite subtle because what you have to consider, the way you have to proceed in order to prove that C effective is equal to 0, is that for each L, for each different n within defined modulo L, then you consider the different trajectories for each of these different classes of states, let's say, and when you sum over all these classes of states, and by populating also some points where effectively there are no degrees of freedom, then you can prove that actually their contribution, because like for here for instance, the P3 this would be for L equal to 3, so P1 equal minus 1, P2 is equal to plus 2, P3 equal minus 1, so when you sum the various contributions, they add up to 0, and then effectively C effective is equal to 0. Okay, so I will run over time, so thank you very much. So what happens instead when you have the non-tachyonic theories? Well, when you have non-tachyonic theories, the thing's complicated. It gets complicated because now you have actually these cancellations are much harder to be achieved, and indeed there is a leftover exponential growth which is smaller than, of course, the behavior, the exponent is smaller than C total, is because the C total I showed you before that actually vanishes, and these are related to the subleading contributions which are given by these various terms. So indeed, it seems that the condition for the C effective in this case is different than 0, is equal to this number, which is smaller than C total, but it is different than 0. So the condition for the cancellation of the various contributions to the vacuum energy, so for the finiteness of the vacuum energy, is the requirement that C effective must be equal to 0, which means that overall there is just an exponential growth of bosonic and fermionic degrees of freedom. So we repeated the analysis in the last 1 minute. Also, whenever you go in 9 lower dimensions and you construct non-supersymmetric theories in lower dimensions, and there is a very nice way to build some non-supersymmetric theories in lower dimensions, which goes under the Scherz-Schwarz construction. And for instance, these models are interpolating model because supersymmetry is broken spontaneously, and they interpolate between supersymmetric vacua and non-supersymmetric ones. For instance, in this case, you interpolate between the two supersymmetric vacua when R, the radius, goes to both to 0 and infinity. And, normally what happens is that there are regions in modular space where tachyons occur. So it is interesting to see what happens to the various degrees of freedom and to various growth rates when you move in modular space, or when you move with R. And okay, so a similar pattern occurs. You always see the oscillation. We did it for various values of the radius within. So this is for the SO16, and so these are the behavior of the degrees of freedom, and you see always the various oscillations. Here you can recognize the contribution of the Kaluza-Klein states in these sector years. And this is for the SO32. So the OC-synchronous OC16 without turning on Wilson lines is always non-tachyonic for any value of R, whereas in this case there is a window where you have tachyons, and precisely these two values of the radius, there are tachyons, and here is tachyon free. But you still find the same pattern, and you can repeat the analysis of the previous analysis, and then you realize that indeed in the tachyonic region, whenever there are tachyons, then the degrees of freedom change, and they organize such that the C effective is no more equal to 0 when you are in the tachyonic, when the tachyon appears. And therefore, this is a signature, actually, the fact that C effective is different than 0, of the presence of tachyons, and therefore it is C effective equal to 0 that actually guarantees should guarantee the cancellation of the degrees of freedom. So here it doesn't matter, it's just to show that there are plenty of tachyonic states when you go in lower dimension, the analysis becomes more complicated. So I come to the conclusions, and then it seems that the oscillations, so the degrees of freedom in the spectrum, so misaligned supersymmetry, is actually a universal feature of generic string vacua. Whenever this matrix Nij adds up to 0, the entries of the matrix add up to 0. The absence of tachyons actually are related to the fact that the growth, the overall growth of the degrees of freedom of the spectrum of any theory must be at most polynomial, so cannot grow exponentially. And of course, these are, if you like, experimental evidences in a way of coming from an analysis, detailed analysis of all the various tachyonic and non-tachyonic vacua, but would be nice to connect these results to some more, I would say, rigorous derivations, which were done by Kutasov and Seiberg in the early 90s, and by myself together with these people in not 91, but 2001, okay, 10 years later, where indeed you can see, that you can show that when you sum over all the degrees of freedom of a string theory, signed number of degrees of freedom, then these are, okay, have some related to the value of the cosmological constant and to the zeros of the Riemann zeta functions, which gives you the error, and when you sum over just the states up to a given cutoff, and then these give you precisely the oscillations of the spectrum. So it would be nice to make this last connection. Hopefully we'll come back later, and thank you very much, and sorry for...
I guess you mean Zay-Gear as well. I guess you forgot Zay-Gear in this. Okay, so do you have questions?
Thank you. Thanks for a nice talk. So this misaligned supersymmetry, as you mentioned it, to try to say that the boson-fermion degeneracies alternate, I think that phenomena by itself just follows from Bekenstein-Hawking entropy. You don't need the deep fact about string theory, and the reason for that is that for large, and if you're interested in large degeneracies, you can count the degeneracy of states at high energy or high mass using Bekenstein-Hawking formula, and if you change the spin of particle by 1/2,
okay,
it barely changes the leading term.
Okay.
And that's a state. That's the reason that the boson-fermion oscillate. The numbers are more or less equal. And this would match why you see it in string theory by string correspondence principle, because string excitations become black holes. So therefore, it should be like that. And so therefore, that argument is more general, explains the string result. So that's one thing.
Okay.
Secondly, the fact that they alternate does not explain why the dark energy should have vanished a priori. Because even if there's one mismatch at higher scale, it will give you a contribution which is huge. The fact that it doesn't is because in string theory, this would be redundant. By modular invariance, we don't include them in the count. So in other words, the cutoff that we get by modular invariance to the fundamental region is the reason we don't get it in string theory. Whereas if we included their contributions, we would have gotten infinity times the constant. In other words, it's more than just the fact that the boson-Zahn fermions becoming... In the O16 cross O16, for example, if you did the naive field theory computation, you get infinity for the dark energy, not finite. The reason we get finite is because of repetition we cancel out. We throw away. So we regularize it somehow in string theory by saying that these are already accounted for, these high energy ones. We will be recounting them. So the reason that it's not just because the sum is equal number.
I'm not sure, but okay.
No, I mean, that's the fundamental domain is what it does, right?
Yeah, sure.
And the third thing is that the connection that you're mentioning between the tachyon and finiteness is in some sense automatic because by modular invariance, if you have no contribution here and there. So I think the results you're mentioning could have been anticipated without using any sophisticated modular invariance techniques, I think. Rational conformity technique. It's more general.
Okay,
it just has to do with the fact that there's no tachyon.
Yeah, can I answer?
As you correctly said.
If I can give an answer. So it's a long question, so a long answer. So the last point is indeed the absence of tachyons and the fact that you have a modular invariance, so you're doing closed strings and then you're protecting in ultraviolet. automatically implies that you don't have, the vacuum energy is finite. I agree with this. And the question is, what does this imply at the level, okay, if you just want to compute the vacuum energy, then you're happy and you can stop there. But then the question is actually how the absence of tachyons, because you know very well that the spectrum of the string theory, the tachyon is related also to how the states grow by modular invariance. So the infrared and the ultraviolet are related to one with the other. So that you can ask yourself how the absence of the tachyons reflects in the high states, high mass states, and this reflects actually in precisely in the fact that you must have these oscillations, and it looks like that it has to, the oscillations are not enough, but you must have that the C effective is equal to 0, so when you compute all the states, then let's say the oscillations, the envelope of the bosonic state, the degrees of freedom, must precisely cancel the envelope of the fermionic ones, and you can have at most a polynomial growth, but not a residual exponential growth. So if you just want to compute a number, you know that there are no tachyons, you are sure that the fact that the vacuum energy is finite, this I agree, and then the question is if you want to have a deeper understanding how the modular invariance relates it. Then can I, to the other question, which I'm not sure I remember all of them. One was the first one.
I'm trying to say that the motivation for DNS is not strong enough to explain why the dark energy would be finite, cosmological constant. Namely, even if C effective is exactly 0, you get infinity. Because you get infinite contribution.
Modular invariance.
No. I'm saying there are infinitely many states.
Yes.
C effective being 0 means the leading one does not grow within, but you get a contribution for each one of them.
Yeah, but there are cancellations. There are cancellations because bosons would contribute with a positive sign.
You would get infinite times constant. In other words, if you did the field theory computation, you get integrate not over the fundamental region, but over the whole strip.
Yes.
And the answer will be infinite.
Absolutely.
So the field theory answer, even if DNS et al. DNS prediction was correct, will give you infinity.
Yeah. But you are not doing a field theory.
So I'm just saying the motivation.
I'm doing a string theory computation.
Right. My point
so
is
I know that I'm protecting the ultraviolet.
You need more than C effective being 0. It has to do with the fact that these high energy ones are redundant degrees of freedom. It's more than they just magically align. It's more than that. I'm just trying to say. That's needed, but that's necessary, but not sufficient.
There's a lot to unpack there.
Yeah, I think we can discuss later because, I mean, precisely with this, thanks to a Zagier Rankin-Selberg theorem, then you can really take, these are the degrees of freedom of all the physical states, and you can map there is a condition modular invariance, closed string theory. This is the vacuum. This is the result of the integral of the functional integral of the one loop partition function, which is finite. And then this is actually related to a would-be field theory computation because you are just computing you map this integral to a one-dimensional integral field theory Schwinger-like integral of the physical string of states. The physical states, this DM, these are signed, positive for bosons and negative for fermions, and these two quantities, the field theory computation and the string theory computation, somehow are related. And you can see from here that whenever you send the cutoff to infinity, so it means that you are taking in considerations you sum over all the string states, then the result is actually this sum is 0 and omega is finite. Of course, if omega is finite. Now, we can discuss later, I don't know.
Is there any relation of these properties with models that have, with string models that have the Atkin-Lerner symmetry that was postulated by them?
There's no relation? Okay.
No, it's just normal string theory. Okay, further questions? Arguments? All right, so we'll close it there. Thank you very much.
Well, It was a wonderful morning. Thank you very much for these excellent talks. Now it's time for lunch. It's a 4 minutes walk. You just follow the locals. And we resume, I suppose, 2:30, maybe a little bit later because of the, the questions. But it was nice. Thank you. So.
Before starting with the talks, I would like to ask everybody to silence their phones. You don't have to switch them off or even put them into flight mode, but it would be nice if you switched off their ring sound at least. Okay, the first talk of the afternoon session is Kaiser Shafi. He will tell us about topological defects, inflation, and gravitational waves. Oops. This thing is moving. This thing is okay. 25 plus 5.
Well, thanks very much, and I would like to thank the organizers for this kind invitation to come to Ioannina, especially beautiful part of Greece. It's always a pleasure to be in Greece. And so this talk is going to be about just a sort of kind of a summary with hopefully one or two interesting results about topological defects. These include monopoles, if you like, magnetic monopoles, cosmic strings, things that are known in condensed matter physics in one form or another, walls, domain walls, or composites made out of these. For instance, you could have monopoles connected to strings. And the reason all these guys have become interesting, especially cosmic strings, is because it's been known for a long time that cosmic strings, if they are sufficiently heavy, when they make loops, they decay, if they are local strings, by emitting gravitational radiation. And of course, the discovery of gravitational waves a few years ago has provided a great deal of impetus. So it's exciting to see a lot of young people involved in looking at how one can test some of these theories using gravitational waves. And then, of course, as far as inflation is concerned, I'll touch on inflation. For this talk, I'm neutral regarding SUSY or non-SUSY. Topological defects exist whether you have a supersymmetric theory or not. As far as inflation is concerned, I have some preference for supersymmetry because it gives, I think, more interesting, compelling models of inflation, and I'll give an example. And then gravitational waves by looking at a specific example, just as a unified theory, if you like, with axions and other dark matter candidates in principle, how one can also get, wave gravitational strings out of it. Yeah. So this is Dirac. 90 years ago last year, he put forward the hypothesis that if you have a magnetic monopole in your theory, then electric charge quantization happens. He used quantum mechanics to show that result. So often I'll use Eg divided by 4 pi equals n over 2. And the way one can think about it is that you have a monopole, so at the origin, let's say, so you should use 2 vector potentials in the northern hemisphere and the southern hemisphere on the equatorial circle. Oh, there's a pointer here, actually, right? And this is the pointer. Is there a pointer that works? Is it this button here? Excuse me, sorry. Is it this button?
I think it's this one, it's the middle one.
Oh, this one, okay. Yeah, so if the two should differ by a gauge transformation. In general, of course, we know the unbroken subgroup is not really U1 electromagnetism, but SU3 cross U1 electromagnetism. So we should look at pi 1 of not U1, but presumably SU3 cross U1, and so on. That can make a little difference as far as magnetic charges are concerned, compatible with the Dirac quantization condition. Anyway, this is the way we use. So on the equator, the two should give the same physics, so they can only differ by a gauge transformation. That's proportional to the magnetic charge, and so that's how you get quantization of electric charge. Now, of course, the excitement came in the 1970s when 't Hooft and Polyakov took a toy model, essentially SU2 broken to U1 electromagnetism, and then use some ansatz to show that you have they found a spherically symmetric configuration to which has a finite energy by imposing suitable conditions that sufficiently far away from the monopole, you get into the vacuum, and they gave the configuration. So the rule is you define your monopole in a bigger theory, look for an SU2 group and break it to some suitable U1. In this case, this U1 is just electromagnetism. That's why it's a toy model. Essentially, the monopole mass typically is proportional to the symmetry breaking scale multiplied by the fine structure constant alpha. And there's a size or something for these monopoles. Now, all grand unified theories. Grand unified theory, I mean a theory with one single gauge coupling constant, such as SU5 or SO10. They predict the monopole. It doesn't matter how you break this theory, SUSY or not, they will always have one magnetic monopole, a super heavy monopole, it's grand unified, which carries 1 unit of Dirac charge, even though you have quarks in the theory, and you might think the charge might be 3 times, but the monopole, this particular monopole, always carries 1 unit of Dirac charge, plus some color magnetic fields. And if the symmetry breaking goes via some intermediate steps, then you could have some intermediate mass monopoles. Then it becomes interesting, because still they are very heavy, whether you could make these monopoles in the early universe and they could survive inflation. So for this talk, there's no attempt to produce gut monopoles, which are super heavy, but I'll give an example where you could make an intermediate mass monopole, for instance. Now, if the standard model is embedded in symmetries such as Patti-Salam or SU3 cube, these are not grand unified theories because there are 3 different gauge coupling constants and so on. If you don't impose unification of the gauge couplings, then these guys do have monopoles. We know that. And these monopoles actually could be light. So the fact that we still haven't seen SUSY means we should be open to the possibility that these things are broken at low scales because they don't require gauge coupling unifications. And so these monopoles could actually be produced perhaps in high energy colliders. One of the motivations for studying monopoles is there is the experiment, the Atlas and CMS look for monopoles, but also there's a dedicated detector metal that looks for magnetic monopoles and hopefully will look for high energy, because it's not easy to make light monopoles even with these theories. So the reason we have monopoles in SU5, of course, is because they are embedded, and it's not a global direct product of the standard model. There are some intersections, topologically speaking, and so the SU3 in 3 points, the U1 electromagnetics meets the circle, and which allows the monopole to carry 1 unit of Dirac charge rather than 3, because in the presence of quarks, you might think that the unit should be 3 times the Dirac charge. And the way one sees it is, these are not direct products, but sloppily written here. The electric charge generator of SU5 is this thing, right? So if I do a 6 pi rotation, not 2 pi like Dirac did, but 6 pi, then I can get back to the identity element, of course. But so if I do a 2 pi rotation, it takes me to this element, right? This is in the SU2 domain, it's an identity, but in the SU3 space, it's not. Now I can do a U1 hypercharge rotation, of course. And by doing, say, this hypercharge rotation, I can return to the identity element. And this is the reason why, right? I just have to do 1/3 of the way rather than going through the whole U1 circle. Right, in the previous example, we saw pi 1 of U1 we looked at, that the way Dirac did. Now it should be SU3 cross U1, and we are mapping pi 1 into SU3 cross U1. So that's why you can have 1 unit of charge for the monopole, but the monopole, we say, carries also Dirac, the color magnetic charge. But of course, the color magnetic charge is screened beyond the QCD scale, and so then you don't have quarks outside there beyond the QCD scale, and so the monopole doesn't have to carry 3 units of charge anymore. And so, this is a picture of a gut monopole, but it doesn't matter. If you go to SO10, things can become a little more interesting, because now it's called spin 10, really. In non-SUSY case, we often break SO10 through intermediate steps just to get the gauge coupling working, unification, and so on. But the monopole is always there. The gut monopole doesn't matter how you break it. And if you look at this, so this is the second homotopy group. You take a sphere and map it into the vacuum manifold, which is like pi 1 of H, like our old example, the first example. And if you have pi 1 of G over H, then you can get cosmic strings, actually, stable. And so it doesn't matter how you break SO10, provided you use tensor representations, you will always get stable cosmic strings. So that depends on how you break it. You can get monopoles connected to strings also, depending on how you break it, but if you break SO10, no matter which chain you use to the standard model, SU3 cross U1 at the end, you'll always get a topologically stable string. And of course, monopoles also there. And this Z2 symmetry in a non-SUSY context you could use for making dark matter candidate, so stabilized by a gauge symmetry, which is perhaps a little more compelling than having an arbitrary Z2 symmetry imposed. So if I just look at this model, then it has monopoles. The monopole actually carries 2 units of charge and must carry color, therefore. This monopole carries color. And in fact, in principle, this has exotic states also, this particular theory, which you can look for. So if I break SO10 via this to this step, then there are two sets of monopoles. There's the monopole which comes here, and then which is the gut monopole, and then you make lighter monopoles here, which are similar to the monopoles here. So therefore, and E6 is similar. There's a gut monopole, and then. So of course, why is that important? Well, if you find the magnetic monopole and you can measure its charge, then of course it tells you about the underlying gauge symmetry. And if you can measure its mass, then it tells you a lot about the symmetry breaking scale. So this is why monopole searches are important. And one way to see that the monopole in this 422 model carries 2 units of charge is to break this to SU3 cross U1. So you have a monopole. You break SU2 right to U1 right, you have a monopole. That's like a 't Hooft-Polyakov monopole, right? But that's not U1 electromagnetism. And then, of course, if you break again there, so there's a red monopole and a blue monopole. We know that if you come directly here, there's a magnetic monopole, as I said. And therefore, the red and the blue can combine to make a monopole with 2 units of charge and also color. Of course, in this case now, there's a rich structure. In cosmology, in the early universe, if this was the breaking chain, you could make red, anti-red. You can combine red and blue in different ways and make necklaces and so on. And so this is something people will study, and some people have tried. And these things could also emit. These structures are complicated, interesting structures that you can find. Similarly, you could look at trinification, SU3 cube. You can break in steps. You can sort of decompose, right, if you like, decomposing that monopole. And you can find that this monopole carries 3 units. Now SU3 color plays no role, essentially. So the monopole has to carry 3 units of direct charge. And of course, these monopoles, of course, they're heavy or intermediate mass or light, it doesn't matter. They are going to be produced in the early universe. In some cases, depends on if it's a symmetry breaking scale, 100 TeV, like Pati Salam or something, then you'll make these monopoles. And Kibble and others have shown a long time ago that you make too many of these guys. Too much of a good thing. Assuming that you don't make 1 monopole per Hubble volume, but 1 monopole per this Ginzburg length or something, So then you make almost as many more than the number of monopoles. The number of baryons to photon is only 10 to the minus 9 or 10. This is 10 to the minus 2, maybe 10 to the minus 4 or so. So too many, especially because they're heavy. So you have to do something about it, and you use inflation to try to resolve that. So all these theories that make monopoles should address this question. And I'm not saying that for low-scale theories like Pati Salam, trinification, I have a model to show. It's not so easy to make, how to take care. But as I mentioned earlier, these are not truly unified, and you can really try to make as light. In a paper with Anil and Digesh, not so long ago, Digesh Raut, we said that for trinification, if the scale is a few TeV, let's say 10 TeV, then the monopole is about 100 TeV, right? If you can take experiments into account. Now, Pati Salam model, we used to say it was about 1,000 TeV because of the leptoquark, but there's a paper by Volkas et al., not so long, about a year ago, I think, in which they claim by adding new vector-like particles, you can break this symmetry at a few TeV, in which case these monopoles really become very interesting, 50 TeV or 40 TeV perhaps. If it's 2 TeV, maybe 20 TeV, right? And these are really topologically stable monopoles. Notice that in these theories, such as if you have a group like this, you see, the minimum electric charge is 1/6. So of course, that explains why the monopole carries 2 units of charge, because you need 3 of these quarks to make a charge 1/2 particle. So in principle, you also predict states which can be looked for. We don't know the mass, vector-like presumably, which are mesons and baryons, color singlets, of course, carrying fractional electric charge. E/2 is always there because you can have an object 1, 2, 1 or something like that. So therefore, that tells you why the monopole is 2 units of charge and things like that. But because of the 1/6 states, it also carries color. So this is the story of monopoles. I think these are the models which are really interesting from the point of view of an experiment like MEDAL, for instance, or LHC colliders, because these are topologically stable monopoles and can be made light. One should test them, whether, these are plausible models of extensions of the standard model. Presumably, non-supersymmetric is good enough. And this is an experiment, so I won't have time to talk about it, but they put a limit of about 75, let's say close to 100 GeV. So the simplest one I know is about 50 TeV or something, topologically stable monopole, with a charge of 2 units or 3 units. So this is really the kind of experiment you need, but scaled up by a couple of orders of magnitude. So strings and domain walls also arise. For instance, strings form. I mean, you can take a U1 and break it, U1 B minus L, and have strings. But when Kibble and I and George Lazaridis tried to look for string, we said, take a grand unified theory, can you find it? And that's how we found topologically stable strings in guts, actually. In those days, people were looking for gut strings maybe to make delta T over T. We now know that it should come from inflation, presumably. But of course, strings also come from U1. U1 breaks, and then eventually they become boundaries of domain walls. And these strings actually are superconducting. So have we taken that into account in recent work? Another thing worth thinking about. And in the Exion case, they are necessarily superconducting. Of course, you can also have walls bounded by strings, which is actually, as I said, always the case in Exion models. And in fact, if you look at this chain, let's say SO10 broken through a 422 model, this one makes a string actually, but it's connected to C parity. There's a C symmetry which interchanges left and right and conjugates the representation. But of course, if you get the 126 has to get a web, then this thing gets connected to domain wall. And so this 126 breaks the C parity, and these are the walls bounded by strings in this model. And people have thought, recently there are some papers thinking about how to maybe use them in making primordial black holes and structures like that. And these things have been seen actually in, went too quickly. They have been seen in superfluid helium, although I don't understand this paper. It's from 2019 in superfluid helium transition, going from the normal phase to another phase to make like a string-like object, and then this breaking makes like wall-like objects, a string connected to walls in superfluid helium 3b. So for inflation, as I said, that's where I have some preference for supersymmetry, because apart from giving a decent model, you want to perhaps also explain where the inflaton field comes from. And so a simple model, there's no time to discuss these things now. But currently, we know that the Hubble, this is 2018 actually, not the latest perhaps, but basically the spectral index versus Hubble tells us the scale, Hubble parameter should be in this ballpark or below, right? 10 to the 14 GeV or below. And that's what I meant when I said that if the monopoles are lighter, intermediate mass, then they could survive some inflation or undergo only a certain number of E-foldings rather than all 30, 60, 40, 50, 60 E-foldings. So this one, if you like, is a simple model, almost like a U1. As a simple example, you can think of, you want to break SUSY U1 B minus L and think of global symmetry, right? So you want to write down a Higgs potential to see if that inflates. You write down a superpotential. You can make it unique because of the properties of SUSY, impose an R symmetry. Because if you put mass term for the S, the singlet, then of course you have to take care of the coefficients and so on. And so now we want to explain inflation not as some random phi to the n field, but it's a field that breaks, let's say, U1 symmetry. In this case, what happens is that the phi field will break at the end of inflation, and S is the one that drives inflation. That's the simplest model you can write down. And so basically at tree level you have a potential. It's global supersymmetry. So of course today the minimum SUSY is unbroken, S is 0, and you have this symmetry, gauge symmetry is broken. In the early universe you have to do the opposite. So yeah, the symmetry is restored, if you like, and S is away from 0, so you can drive inflation. And this model then basically is the simplest thing that we wrote down with Gia Diwali and Bob Schaefer a long time ago. Basically, it has tree level plus quantum corrections. It ignores the soft SUSY breaking terms. And so if you work it out, it says that the spectral index is 0.98, just the tree level term plus the radiative corrections. And the scale is predicted to be in this ballpark, 10 to the 15 GeV. So this is okay for something like U1 B minus L. And B minus L is broken at the end. Now, to fix that, we know now for several years that spectral index is more like 0.97, in that between 9.6 and 9.7. So we need to do some corrections. There are at least two ways. We first employed with Steve King and Ma Becerro-Gil, we employed a non-minimal Kähler potential. Just add one more term, and that can take care of it. Or you can go back to the minimal model and include the soft SUSY breaking term. This is not quite the soft mass term, because it's connected to this particular term, this m squared, which we know is the gut scale. So therefore, this term can be important. So the interplay between these two things can basically move you to the right spectral index of the type you need. Here's this paper. So just add this term kappa s, s dagger, and this kappa s, if you like, of order in some limit where this, say, if you ignore the radiative correction, then the spectral index is just 1 minus 2 kappa s or something. And if kappa s is 0.02 or something, then you get the right spectral index. Thank you. Yeah. 5 minutes left, so I will speed up a little bit. Of course, this thing has been extended. So G breaks to H means what? Well, I mean, so we want to apply it. This is the simplest thing with cosmic strings, but you want to apply it, let's say, to some of these more realistic models. This is SUSY now, because this is where we can have a nice, well-motivated model and control quantum corrections and so on. And in fact, the more general case is a very rich, actually, structure. So the question is, what is the prediction? What are we saying for this model? Because this is a realistic model with parameters, it's not just a phi field and you draw a line or a point. It's a full model. You can do leptogenesis, baryogenesis, and things like that. This is the way one of the students I asked summarized this essentially. This is the way, you see, if you look at Planck data, starting with WMAP 5 or 9, they tell you that this model is, they call it spontaneously broken soft SUSY model, and they give you this green line, which is correct. If you just take quantum corrections, radiative corrections plus the 3 level, the spectral index is 0.98. But for many years, we know that by taking a non-minimal term, you can bring the thing along this brown line, essentially, with R being practically 0. Now you can ask ourselves, I want to do it for guts, where the guts symmetry breaking scale is not 10 to the 15, but 10 to the 16 GeV. Then in that case, you have to use non-minimal Kähler terms. And at the end of the day, if you do all that stuff, so it tells you with non-minimal Kähler, you can go up to 0.03 for R. This is if you have soft SUSY, minimal Kähler, you are along this line, essentially practically 0. And then this is the one, this is the first paper, and it's 0.98, but doesn't mean the class of models is excluded. This is actually the range of prediction for this class of models. I think I have about 2-3 minutes left, so let me see what else can I do. There's another one that Nobuchika, there's another way to turn it around. Forget the second term since there's no time, but if you go back to this superpotential, you could of course implement something different. You can try to do non-minimal quartic inflation with this kind of thing that Nobuchika and I did, and if you require, in this case, you see, we are using this superpotential differently. You want to do non-minimal Kähler in this supersymmetric theory, and if you require that the reheat temperature, let's say, is for the gravitino constraint is 10 to the 6 GeV, then you can in fact find predictions of this type that you might, so in this region. And then so you can predict the symmetry breaking scale also of the theory. It lies in a certain range. R is observable for this case. So it's just treating it somewhat differently, this particular model. I think there's no time to do that. This is an example of how monopoles could survive. Intermediate scale monopoles could survive inflation. The inflaton field is running down to its minimum, and it brings along this phase transition that makes intermediate mass monopoles. They undergo, let's say, 20 E-foldings rather than 60 or something, and then they may have an observable number or something. Since time is really run out, I would say that you can apply it, construct models of a non-supersymmetric model, realistic models which have a range of structure, cosmic strings, axionic strings, new matter fields, because you want to solve, let's say, the axion domain wall problem and things like that, which unfortunately I don't have time to go into because my time is 0. Thank you.
Thanks also for keeping time.
Yeah.
Do we have questions? They are in the back.
Nikos. Yeah, Nikos.
Thank you for the... Sorry. Yeah. Can you hear me?
Not...
No.
Yeah. Normally you have a good voice.
You
By the way, since the monopoles, your intermediate mass monopoles of the low scale ones survive inflation, do you expect that they could affect the electroweak phase transition? And does this put restriction on their numbers available, or you can avoid this problem?
Yeah, you mean the intermediate scale 10 to the 9 or 10 GeV monopole?
No, the lower.
Oh, the lower bound. You mean, let's say 10 TeV. Yeah, 10 TeV is, you break the 4-2-2 symmetry to the standard model. I don't see any impact on the electroweak phase transition. But people have studied that, by the way. People have studied that the 4-2-2 breaking is strongly first order, may give rise to gravity waves. That's a different question, yeah. And how that is connected to the monopoles themselves is something we have been thinking about, yeah. This is an important point, yeah. It's important, yeah, thank you, yeah.
Thank you. There was another question in the back.
Just a comment. Thank you for this nice talk. One way to reduce the spectral index for the minimal supergravity model the 0.98 that you have shown, is to consider a subsequent period of late inflation, a combination of fast roll and thermal inflation, for example, which lasts a total of about 25 EFOLs or something like that, fixes the problem without introducing any non-minimal Keller potential or anything like that. I don't know if you were aware of this.
I think I'm aware of it. Thank you, yeah. Thank you, yeah.
One more at the back.
So I have a question about the SO10 breaking chance. You mentioned that in SO10 breaking chance, no matter what, it has monopoles. But the intermediate scale is usually set where the U1 B-L or SU2 right breaking occur. So even though you do not insist a gauge unification, if you want to address the right-handed physics, especially the neutrino mass by seesaw, or unless you use some other ways, the breaking scale is usually expected to be 10 to 10 to 14 GeV. So this is purely from the right-handed physics scenarios. So how would this affect the phenomenology of the monopoles and the cosmic strings? Is this still survives the inflations?
You mean you are saying, can I break some of these models at 110 TeV and still get neutrino physics working and so on?
Yes.
No, that I think is a model building question that I have not addressed, yeah. To construct a realistic model remains to be seen, but some work has been done, but I don't know whether there's a complete model available.
Okay, thank you.
Yeah.
There's a question in front here.
I think there's one here from Apostolus there.
He was first.
Oh, okay. Sorry. Yeah, go ahead.
When you discussed topological defect production from gut scale topological defects, you seem to assume that the gut symmetry is restored in the early universe.
No, I didn't actually discuss gut scale monopole as such, but suppose there's a field phi. Suppose the mass of the gut field is phi squared, chi squared. Chi is the gut breaking field and phi is the inflaton. So as phi grows from the origin, then the SU5 symmetry breaks. That would be one way to make a gut monopole. I don't have to assume that it's coming from temperature. Yeah. That would be a model for making primordial monopoles, if you like. Yeah.
Can you use the microphone, please?
Oh, yeah. Oh, you should use the mic. Yeah.
Restart the question.
Yeah.
So the point is that the early universe could not have been hotter than about 210 to the 14 GeV.
Right.
If you just look at two-body scattering rates in a QCD plasma and compare with the Hubble rate.
Right.
So you never reach the temperature necessary to restore a gut symmetry.
Right.
However, my question was, how would you make topological defects in such a situation? And your answer is that you could do it by the kind of...
Yeah, I could start with the cold universe with just the potential energy of a field phi. Yeah, I need this extra coupling, and then The field phi helps break the gut symmetry. You undergo 60 foldings for the gut monopole, and then the intermediate monopole may go 20 foldings or something. Eventually, you reheat to some temperature.
Well, that's the point.
Yeah, I don't have to assume that the temperature was 10 to the 16 GeV.
But could you predict the number density in that case? Could you
Right.
predict the relic abundance in
Yeah.
a convoluted model like that?
Yeah, so let me just show that. Predict is a bit strong, the statement, but what I mean is I can control a little bit.
Can you say 1 per horizon, some rough number there?
Where's that? Just a moment. Sorry about it. I have to find this thing. I apologize. You see here, for instance, this tells you, I'm not assuming 1 per horizon. I'm just saying the phase transition is happening, how many foldings you have, and so therefore it's the first term, sorry, this first term is the Ginzburg kind of thing that you have, and then there's an exponential dilution from the number of e-foldings, and this is where the field is oscillating and so on. So in that sense, one can estimate. Predict is a bit strong, but one can estimate depending on the mass. But by the same token, the gut monopole would be. But I didn't have to assume that the temperature was 10 to the 16 GeV. Yeah, sure.
I can trust it.
Yeah, the first is a comment, I think, for topological defects. I think the Goldstone modes play an important role about the superconductivity or not, which one needs to include them. That's what we have seen recently. So the dynamics is much more complicated than the one you're...
For the monopoles, you said?
Or no, for the domain walls. On the monopoles, I don't know. There might be also a problem there that you need to take into account the Goldstone degrees of freedom. But for topological defects, we have seen that they play an important role. The interface, the domain wall could be C or CP violating. You could have that kind of phenomena. The other thing which I like to also comment or ask you, you are, maybe I understand there is a lot of experimental activity and interest about low-scale monopoles, but all these models, of course, to produce at colliders is not sufficient to have the energy to produce the monopoles. You need to have the corresponding coherence to get the monopoles out of the colliders. And so I'm not so sure when you are saying that you are producing monopoles at colliders, what you exactly mean by that.
I think maybe since John and Nick are here, they are on the metal collaboration. They can make a comment. They are trying to make this more complicated configuration. That's my understanding. Not just point-like. Huh?
If I may say, from Schwinger mechanism, you produce them from the vacuum. So you don't need the coherence. What you need from collision, yes. So yeah, thanks. Thanks, guys.
It's open, yeah, now it's okay. From Schwinger mechanism, if you produce you don't need the coherence. The only problem at the moment is that unfortunately the limits are very low from the metal. As Kaiser said, it's 75 GeV. So you need the next generation to arrive at the 10 TeV, 20 TeV. It's not clear whether it would be achievable in colliders at the moment. But to produce them from collision, then yes, because they are suppressed by 10 to the e to the minus 1 over alpha, 4 pi over alpha, alpha the fine structure constant. You need some coherent, a huge macroscopic thing but not for Schwinger.
And Dick, what kind of mass will you reach in the next 5 years, let's say?
Up to, they claim they could reach under certain conditions 500-600 GeV. Yeah. If they manipulate. The problem is theoretical. It's how you approximate, how you do approximately your calculations so as to calculate the Schwinger effect, the magnetic monopole Schwinger effect, of course, not the 600. Yeah. Okay. 600 GeV for FCC. That's what Vaso says. Nice. So, future collider, circular collider.
I think we have to move on. Thank you again for your talk. And the next speaker is Konstantinos Pallis, and he will talk on some dark matter.
Okay.
You said, he said the wrong name, right? I'm wrong. Anyway, I forgive him.
Sorry.
Because I pack him in my car in the morning. So anyway. So, thanks, Manuel. Thanks for the organizer for the invitation. So I'm going to talk about dark matter in SUGRA model. In particular, I'm going to discuss a little bit the neutralino dark matter scenario in the simplest supersymmetric model, the CMSSR or SUGRA, if you like, although it's not really the same. This is the, let me say, the first and the oldest scenario, the most also well studied. Then, I'll discuss the gravitino dark matter scenario, especially I'll give an emphasis in a calculation we presented 1 year ago in the gravitino thermal density and phenomenological, let me say, consequences of this calculation. And last but not least, I'll discuss the new possibility that the dark matter can be primordial black hole, which are calculated in the context of supergravity model. So, let's start from the neutralino. As I said, the neutralino is the most well-studied supersymmetric dark matter scenario, both of course theoretically and experimentally. The initial motivation, probably all of you know this, it was the so-called twin miracle. This is an old story, so we have studied this scenario in many SUSY models like CMSSM and SUGRA, when you relax the unification of Higgs sector, and then if you relax many other unification of the fermions, then you have the so-called PMSSM scenario. The correct prediction for the neutralino Rayleigh density can be achieved in particular regions of the parameter space, the so-called coannihilation regions, and you have mainly three kinds of coannihilation regions. You have the stop coannihilation region, the STAU was the first one, and also Gaussian, means coannihilation with neutralino and Sargino. Then you have the focus point region, which is the border between the allowed region and the no electroweak symmetry bearing region. And also you have some region which is related with the enhanced cross-section through the A Higgs resonant cross-section. Okay, so I'm going to present very preliminary result, but okay, hopefully we'll have this calculation done. We are revisiting the neutralino dark matter region, the CMSSM. We are using as a constraint indirect data, mainly from neutrinos, fluxes from ice cube, and also concerning the gamma fluxes, we are using Fermi-Lat data from dwarf spheroidal satellites, which are supposed to be very good, let me say, sources from gammas, and they are mainly made out of the dark matter. This is a work in progress, and soon you'll see results. So, in some first figures, so for tangent beta 5 and trilinear coupling 0, there is a region where these red points you'll see in the rest figures are points that can be excluded, actually, are constrained from the ice cube data that they have collected up to now. But okay, although these are relevant to the ice cube data, the Higgs mass in this part of the parameter space is very low, it's below 120, so this region is already excluded, if you like, by the Higgs mass. This also happens for values of tangent beta up to, going fast, up to 55. In 55, though, there is a region very close to, I mean, it's a part of the focus point region, is a region which is the so-called well-tempered neutralino region, where these points, the red points there, are excluded, are constrained by the neutrino data, and the Higgs mass is very close to 100, it's almost 125. So our plan is to study in details this region, and mainly to see how this region can be, let me say, constrained by direct data, let me say, cross-section, the direct data from the neutralino. So this is, as I said, a work in progress. We'll see what is going to happen. The other thing I want to say is that, as a result, almost, is that in none of these regions, it appears that the direct constraints from the dwarfs is playing any particular role. So only the neutrino data can give us some, let me say, some information with respect to indirect searches. The same for bigger values of tangent beta. This region is okay, but still the Higgs mass there is small. So, some recap from neutralinos before going to the new scenario. Neutralino is, as I said, the very well studied case, especially in the CMSSM. The preliminary results of our study is that, okay, from the direct constraints, which is gamma, and from spheroidal neutrino, from the sun, only the neutrinos will be important. For large values of the tangent beta, it appears that there are regions which are compatible with the bound for the Higgs mass, which is the most important bound in this, if you forget about G-2 and all this stuff in this study. And more work is needed in order to combine these regions with direct dark matter searches. Okay, if you want to get rid of the direct, anti-direct constraints altogether in the context of supersymmetry, supergravity, gravitino is the ideal candidate. Because gravitino, since it interacts only gravitationally, it's not susceptible to these constraints, either direct or anti-direct. Gravitino is the superparticle graviton, the spin 3/2, is a classic free zine. Let's call it a dark matter candidate. It's free zine because it produces thermally out of the equilibrium with the rest of the plasma. And there is many sources for the gravitino, many ways to produce it. You can produce non-thermally from the inflaton decays, for example. Can be produced through the decays of unstable particles, like decays of next to the lightest supersymmetrical particle in the gravitino dark matter scenario. But of course, then in this case, one has to be careful with other constraints, like the BBN constraints, to see what part of the scenario are compatible with the BBN constraints. In any case, the calculation of the gravitino thermal rate is an important ingredient for these scenarios. So, it's a difficult calculation. The first try was Ellis Kimnanopoulos, 1984. Soon after, it was Moroi, Muriyama, 93, 94. In the beginning, the idea was to go in the effective theory of the light gravitinos, and in this case, they are considered only the 1/2 Goldstein components. Then, soon after, they took into account also the pure gravitino components in the so-called Bradin-Pisarski-Yan method. But then, still in this method, you have to go, as we'll discuss later, in the so-called HTL approximation, this is the so-called hard thermal loop approximation, and which somehow restricts the theoretical application of this calculation. An important improvement happens by Strumy and Griskov in 2007, where they went beyond the HTL approximation, the hard thermal loop approximation. More or less, we have followed the framework of these guys, which is very clever, actually, framework. We repeat the calculation, we corrected some errors from the previous calculation, but more importantly, we provide provide the people with the proper parameterization of this result. This was a calculation that appears last year, and we are thinking, or even now we are working in an improvement of this calculation, and the result will be appear soon. So let's discuss what we have done. In the context of this so-called Bradin-Yana prescription, which is valid as soon as the coupling constant is much smaller than 1, one assumes an intermediate scale for the momenta, let's call it K star, and the calculation is broken in two pieces, the so-called hard part, which is the calculation of the 2-to-2 processes that produces gravitino, and the soft part, and the soft part is really the imaginary part of the gravitino self-energy. So, with this way, at the end of the day, the final result does not depend on the K, on this intermediate scale, K star, and this is the classic result from Pradl, the Stefan, which was the last they calculated, they performed this calculation in this framework. But as I said, it's a really useful analytical result, but it is valid only if G, the coupling constant, is much smaller than 1. This condition, of course, is not realistic because, for example, if you consider that G is G3, G3 is not much smaller than 1, especially for any temperature in the plasma. Okay, so if you want to go as Rizkov-Strumia proposed beyond the H-tail approximation, one has to calculate the full one-loop gravitino self-energy beyond the hard thermal approximation, and also to calculate the subtract part. I'll discuss later I will explain later what is the subtract part for the 2-to-2 processes. So this is exactly the idea. The idea is the following. Okay, this is for one particular production process, gluon to gluino gravitino amplitude. This is the amplitude, square amplitude. If you you can see easily that it is related with this graph. If you cut it there, this is just the square of this. This square is really the calculation of this graph. This graph here is a part of the so-called D graph, which is this graph of the gravitino self-energy. Be careful that these thick lines here is the resump thermal propagators, both for gluino and also for the gluon. So which means that this loop here is, let me say, part of this thick line, right? So this, really this graph is a part of this graph, which means that if you want to calculate the gravitino thermal rate density, the thermal production rate, you have to subtract out of these D graphs the square of these guys. So if you do this thing, this is what is left is really the so-called subtract part. And you see, this was, let me say, the original 10 classical, let's say classical, original 2-to-2 gravitino production processes. And you see that this result from the subtract part are this result. It's important, let me say, advantage with this calculation. These 2-to-2 graphs, without calculate the subtract part, you see that some of them, they carry infinite divergence. This, for example, this one, you see there is a t in the denominator. T can be 0 in the massless limit. And you have, of course, to take gravitino as let me say, as, in this case, as very light. So, but in the subtract part, these infrared divergences are not present. So the result by construction is infrared finite, but on the other hand, of course, it's yet dependent. So this is one of the things that we're thinking that we can improve in the future. Anyhow, this is the formula we're using for the gravitino thermal production. We are taking properly into account all the statistical factors without beyond the Boltzmann approximation. And this is the calculation for the previous one. For the subtract part, this is the easy part, and this is the calculation for the gravitino self-energy. This is a complicated result. At the end of the day, this integral has to be calculated numerically and has to take properly into account the so-called spectral function, both for the scalar particles and the fermions, let's say the gauge boson and the fermions. Okay, if you do this thing, this is the result. Of course, the result depends on the gauge group. We have put, this is the parameterization of the result in the same form like the Pradler result in order to be to have it, let me say, in a handy form. And this is the result for the SU3, the SU2, and U1. The black line is the total result, and this is the comparison with the result of Risko-Strumia. So our result is a little bit smaller by almost 10%. Now, if you take the result and calculate the thermal abundance without, let me say, of course, using, let me say, standard normalization and all this stuff, this is the abundance you get. These numbers, these lines, for particular values of M1/2 are compatible with a Rayleigh density point 12, so we don't consider any other mechanism of the gravitino production. And we see that if you say that, okay, let's say that the reheating temperature is 10 to the 10, for example, and M1/2 is 750, which is more or less the bound from the LHC. Now, the gravitino supposed to be the value which is compatible with this, let me say, Rayleigh density for the gravitino. For the gravitino is almost 550. For smallest value of the reheating temperature, the value of gravitino mass can be higher, can go up to the 3 TeVs. And these are more or less the conclusion, the recap for the gravitinos. As I said, gravitino is a natural dark matter content in sugra, and of course can be thermally produced. There is also thermal production. And this line here is the, let me say, the summary of what I said, that for values around 750 for M1/2 and the heat temperature 10 to the 9, we get that the gravitino mass is almost 550 GeV. All right. As I said, there is a new possibility in sugra that dark matter can be in the form of primordial black holes that are produced, let me say, in sugra scenario. The motivation was really the detection of the gravitational waves from black hole emerging as measured by Virgo Laiko. Then we studied the possibility that if you are starting from a simple potential, like something like, let me say, the Zumino, which is compatible with the Starobinsky, which is equivalent to Starobinsky scenario, and make some modification either to the color potential or to the superpotential, we saw that primordial black holes and gravitational waves can be produced in the context of the scenario. An important point is that if you use the so-called inflection point, which means inflection point is the potential, so to create inflection point, and the inflection point is related to the significant enhancement in the power spectrum. At this inflection point, the slow roll approximation is not working, fails. So one has to solve numerically the Muon-Sasaki equation of the perturbations. We have done these things. Of course, more details today for Ioannis Stamou, my student, talk in the parallel session, and a few days later by Nick Mavromatos in this session. So what is the idea? You start from this color potential and the Vezumino superpotential. You follow the standard procedure for this T and T star fields in the real direction. The imaginary part of Phi is set to 0. And doing this transformation, you end up with this potential, which is the Starobinsky potential. And for particular ratio of this lambda over me, which is 1/3, this is actually the word from Nanopoulos, Olive, and Ellis Nanopoulos Olive, you get the Starobinsky potential. What we have done in this superpotential, we added an extra term. And this, let me say, scenario is deformed. You produce an inflection point by this term, which is still, this model is non-scale model. And our scenario is compatible
with all the cosmological constraints, both in R and S plane. You see the lines, which are between 60 and 50 folds. But you have an enhancement in the power spectrum. You see this is the enhancement. It's about 9 orders of magnitude, this is enhancement. The dashed line is the numeric, the slow roll approximation. You see it's important to calculate numerically to solve numerically the perturbation equation, the solid line, because you are missing maybe a few orders of magnitudes. And if you do this in this plane of the primordial black hole mass and the abundance of the primordial black hole, you can get easily 10–20% of the dark matter in the form of primordial black holes. Actually, this is an old figure. If you, in a new analysis, we have seen that can go up to the 80–90% of this thing. What is the disadvantage of this scenario? The disadvantage is the following. In order to achieve this, the extra parameter, okay, if you are able to thanks, Stefan, if you are able to let me say, to explain why this term is here, there is an extra problem that you have to explain the amount of the fine-tuning of this parameter. Although we have seen that in variation of scenario, like Kazar discussed with the hybrid inflation, this fine-tuning is much smaller. So this is the disadvantage of the scenario, that it is fine-tuned. One advantage is that the gravitational waves that are produced in the context of this scenario can be detected at future interferometer like LISA, the LIGO, etc. So, recap for the primordial black holes. By modifying the color potential or the superpotential, in this talk I just show examples for motivation of the color potential. Gravitational waves and primordial black holes, which is, let me say, the dark matter in this candidate in this scenario, can be produced. The disadvantage is the tuning, the fine-tuning of the parameters. But, okay, as I said, the gravitational waves are also produced, and this can be detected in the future interferometer, anograph, LISA, and LIGO. Summary. Okay, we present scenario for neutralino, gravitino, and primordial black holes, dark matter in various Sugra models. Okay, the classical, let's say the oldest, and let's say call it classical candidates, which is the neutralino, there is a work in progress to update the scenario, direct and constraints in the scenario. Gravitino, then the other classical also candidate for dark matter in Sugra. We have reported progress in the thermal production of the gravitino. And as I said, last but not least, primordial black holes can be a dark matter candidate in this scenario, but by modifying either color or superpotential, with the disadvantage that the new terms that are added and the parameters that are related to these new terms are highly fine-tuned. Thank you very much.
Perfectly in time. We have time for questions in front here.
Presentation. So I just have two curiosities. So one point is that, so when you're tuning your first order scalar perturbations near the inflection point, so you're boosting your first order scalar perturbations, right? And then you're inducing the second order scalar, second order tensor perturbations, and that's how you get the gravitational wave. So these are the second order tensor perturbations sourced by first order scalar perturbations, right? Yes. So do you also excite non-Gaussianities as well?
No, it's not Gaussianities. And actually, what we are doing, you speak about gravitational waves. The techniques we are using. Yeah, sorry. So, thanks, Manuel. So the way we are calculating the gravitational wave density is the standard technique, which means that we are relating the gravitational waves by products of the scalar power spectrum. You see, because this the vacuum excitation value of 6 zeta can be related with the product of two expectation values of zeta zeta, which is the product of two scalar power spectrum. So we don't really calculate the gravitational wave density from the perturbation of the tensor perturbation. If we are doing this, actually this is smaller than the term we're discussing here. This is the standard result in bibliography.
Okay.
Any other questions? In the back there.
The primordial black holes that you produce, do they have a monochromatic mass function, meaning that corresponds to the modes that exit at the inflection point, or do they have an extended mass function?
No, in this particular scenario are mainly monochromatic. In other scenarios we have studied are not really, I mean, it's really a wide spectrum. For example, we study hybrid SUSY scenario, where, the spectrum is not really monochromatic, it's a wide spectrum. So you take contribution from many frequencies. But in this model, it's almost monochromatic.
Any other questions? I don't see any, so let's thank Vasilis again.
Okay, thanks.
Don't go away yet, we have a word from our sponsor.
Thank you. Just an announcement about the parallel sessions. So the flavor physics session will take place here in the auditorium. The cosmology session will be on the ground floor downstairs. And the SUSY phenomenology session will be just next door out of, when we exit this door of the auditorium, will just be the next room here. Thank you.
Ένα, δύο, ένα. Ένα, δύο.
Και για πήγαινε πίσω εκεί.
Και θα διαλέξω από εδώ.
Λοιπόν,
θα διαλέξω. Τα flavor αυτά δεν είναι.
Θα σε πάω σε άλλο parallel session. Εντάξει.
Cool. All right, hi, I'm Andrew Mogan, and as you just heard, I'm going to be talking to you about Microboon's first results in its investigation of the mini-boon low-energy excess, which is what, you might ask. That's this plot over here on the right. So this is showing a couple of sort of anomalies, outstanding anomalies in the short baseline neutrino oscillation physics field, where on the left here you have this plot from the LSND experiment, where their expected backgrounds are in the red and green histograms, and what they measured is quite a bit above that. And on the right is the mini-boon plot, the so-called mini-boon low-energy excess, or LEE, where at energies below something like 500 MeV, you see this big excess of your neutrino-like events. And one possible explanation for this is evidence for sterile neutrino oscillations. There are many other explanations, but that's one that's been posited that we'll hear a bit more about later. So, talking more about mini-boon specifically here, it's a mineral oil Cherenkov detector, which all you need to know about that is basically it means you can't see protons and you have difficulties distinguishing electrons from photons. So in a Cherenkov detector, an electron shower looks like this. It makes sort of a fuzzy ring on this array of photomultiplier tubes that you have lining the inside of your detector. And a photon shower will look kind of similar, where your photon pair converts into an E plus, E minus pair. So ideally what you would see is sort of two overlapping rings, but that are still distinct. However, what happens a lot of the time is that you get this collimated pair production, so your rings overlap, and so then it gets really tricky to distinguish electrons from photons. All of which is to say that the LEE is believed to be either photon-like or electron-like in nature, primarily one or the other. So this is where the Microboon experiment comes in. One of Microboon's main goals is to investigate the mini-boon low-energy excess and to explain what's causing it. So this is a bird's eye view of the neutrino campus at Fermilab. If you go to Fermilab or have been yourself, you'll probably find yourself working in this building here. And over here, you'll see there's two different neutrino beam lines. This is the booster neutrino beam line in the red dashed curve, mean energy of about 700 MeV. And the blue line here is the NUMI beam line, something like 2 GeV on average. And Microboon sits right here. It's actually at the intersection of the two beam lines. So for Microboon, the BNB, the booster neutrino beam, is on axis, and the NUMI beam line is off axis. It kind of comes at it from an angle over here. And this is a picture of the Microboon cryostat being lowered into the liquid argon testing facility, where it still is to this day, as far as I know at least. Okay, so Microboon is a liquid argon time projection chamber. So remember, mini-boon was a mineral oil Cherenkov detector, and now we're looking at a different type of detector technology. So the idea here is you get a big tank of liquid argon, and you shoot a bunch of neutrinos at it, and every now and then one of those neutrinos will interact with the argon atoms, and this produces charged particles, and as those charged particles traverse the detector, they liberate ionization electrons and scintillation photons. The photons get collected by an array of photomultiplier tubes. Those are behind the anode readout wires. They're not pictured here, but they exist. And the ionization electrons get drifted toward the anode readout wires under the influence of an applied electric field. And the idea is that by having multiple readout wire planes, in this case we have 3, and by looking at the induced signals from the ionization electrons and from the scintillation photons, we can use all that to stitch together a 3-dimensional reconstruction of neutrino interactions, which looks something like this. This is a 2D projection, of course, but you get the idea. So you can think of this as like a top-down view of a neutrino interaction in Microboon, where your neutrino beam comes in from left to right. You can't see the neutrinos themselves. What you do see is the interaction vertex here, with a bunch of stuff coming out of it. Usually in liquid argon detectors, we talk about tracks and showers. So tracks are these sort of narrow, straight bits. These tend to be either protons, muons, or pions in Microboon energies. And then the showers, the electromagnetic showers, are where your electrons and photons are. So these are the things that we're really interested in for our purposes. So again, I mentioned that the mini-boon low-energy excess is going to be either probably either electron-like or photon-like in nature. Mini-boon couldn't distinguish electrons from photons, but we can, for the most part, because there are two different ways that we can use to separate electron showers from photon showers. One is based on the conversion distance. This is how far the thing travels before it showers. So in the case of photons, the photon propagates invisibly, something like a few centimeters usually, before the pair production actually occurs. So what you see is a distinct gap between your interaction vertex and where your shower actually starts. That's shown over here on the left, where this is probably some sort of charged current pi naught decay. On the right, you see a candidate electron shower from the NUMI beam line. And again, in this case, you see that your electron shower, in this case, is attached to your vertex. So if you see a gap between vertex and shower start point, it's probably a photon. If it's attached, probably an electron. And the other way that we can tell them apart is based on the dEdx, that's energy deposition per unit length. So if you look at this quantity for showers, what you see is that usually your electron showers have an average dEdx of something like 2 MeV per centimeter. You can see that over here on the left. This is a plot from the NUMI beam line looking at charge current Nu-E interactions. So your electrons peak at about 2, and for photons, again, they pair convert, so you have an E plus E minus pair, so you expect that dEdx to be roughly twice that of electrons, and that is indeed what you see. Your peak is something about 3 or 4 here. So between conversion distance and dEdx, we can reliably separate electrons from photons, which leads us into actually investigating the mini-boon low-energy excess. So we have this one photon-like investigation, and we have 3 different electron searches to explain this low-energy excess. On the photon-like side of things, we're looking at NC delta radiative decays. That is, if I go back to the mini-boon plot real quick, that's this tan bit right here. You see that's delta to n gamma, where n is a nucleon, either proton or neutron. So on that side, we're looking at just a standard model process. This is a known thing. However, it has a very low branching ratio, less than 1%, compared to the much more common delta to n pi naught process. This is going to be, as we'll see, the largest background in this search by a lot. And what you expect is either 1 photon and 1 proton in the final state, like this, again with a detached shower from the vertex, or 1 photon and 0 protons, in which case you just see a lone shower off by itself. On the electron-like side of things, we have 3 different independent complementary searches. We're looking at 1e 1p events. They look like this. We have 1e xp events, meaning any number of protons, 0 or more. And then we have a 1e and anything, 1ex. Could be protons, muons, whatever. So what we're looking at is different topologies and reconstruction algorithms for each of these searches with just a single electron in the final state. So starting with the photon-like side of things, again, we're looking at just a standard model process here where you have a delta resonance that decays into a nucleon, either a proton or a neutron, and a single photon. So this is your main signature that you're looking for. So for this search, we use the Pandora pattern recognition framework for reconstruction. You can read about it in detail here. We used a BDT-based selection, a boosted decision tree, which is basically a thing that you can sort of think of as like automated selection cuts if you've never used them before. That's very simplistic, but you get the idea. You give them as input a bunch of kinematic variables like shower energies, track angles, dEdx, things like that. And then you train your BDTs on your different types of backgrounds and use them to separate signal from background, basically. So in this case, we actually have 5 different BDTs, all trained on different backgrounds. We have one for cosmic backgrounds. Microboon sits on the Earth's surface, so we have a lot of cosmic rays coming in all the time. We have one trained on CC Nu-E interactions, because that's a background in this case. We're looking for photon-like events. We actually have 2 trained on NC pi naughts because they're a huge background. Like over here on the right, that's the red histogram is NC pi naughts. And then we have one trained on other general beam, on-beam backgrounds. The NC pi naught, as I mentioned, is the largest background by a long shot. So we have a dedicated selection of 2 photon events to help constrain that background. So that's shown over here on the right. This is the reconstructed pi naught momentum for the 2 gamma selections. I'm told there's a very nice thesis written on this topic somewhere out there. And it turns out that in order to fully explain the mini-boon low-energy excess in terms of this delta to n gamma process, you would need pretty much just a flat factor of 3 across the board. It actually ends up being something like 3.18 to fully explain the mini-boon LEE. So if we select all these single photon events and we see, okay, what rate do we see? Does it line up with that? The result is it seems to not be a viable candidate as a sole explanation for the LEE. We actually disfavor that interpretation at 94.8% confidence. And you can see that down here on the bottom. So in each of these plots, left is unconstrained and right is constrained, meaning we apply the constraint from those 2 photon samples. And on the left is the 1 gamma 1p topology, and on the right is the 1 gamma 0p topology. And in both cases, you can see we're either at or below the standard model expectation, which is this horizontal black line here, where the low energy excess would be this dashed sort of orangey yellow line. So it seems like we favor the standard model here by quite a bit. In fact, we've placed an upper bound on that enhancement factor at 2.3 times the standard model rate at 90% confidence level. Remember, this would have to be 3.18 to explain the mini-boon low energy excess. And this is actually the most stringent limit to date on this, on the rate of this process on liquid argon. which the previous best was, I believe, by T to K, and ours improves that by a factor of, I believe, 50, some very large number. Okay, so it seems unlikely that the LEE is entirely photon-like, so what about the electron searches? I mentioned we have these three independent topologies, so let's just look at those in a bit more detail real quick. We have the 1E, 1P topology, which is targeting more CCQE-like interactions. This uses a deep learning reconstruction framework that you can read about here. So you see a candidate event down here at the bottom with your 1E, 1P, where basically the deep learning network tries to tag individual pixels in your image as either shower-like or track-like. So the shower-like bits are here in yellow, and you can see this bit here is track-like, as you'd expect. We also have the 1E XP, where X is any number of protons in your final state. Both of these are looking for no pions in the final state, I should mention. This uses the Pandora reconstruction framework, the same as in the single photon analysis. And here we actually treat our 0P and NP channels separately, where N is greater than 0. So we have a no proton channel and any number greater than 0 of protons. And you have an event display down here at the bottom, where in this case it's just a 1E, 1P. And finally, we have an inclusive selection. Anything with a single electron in the final states. This is 1E and X, where X is whatever else there is. This one uses what's called the wire cell reconstruction framework. Again, you can read about it in all its glorious detail here. And here's a simulated example of how this selection works. So you see, again, large cosmic background. I mentioned that micromoons on the surface, we have a lot of cosmics. And we're able to successfully pick out the 1E, 1P candidate here. And this also includes very robust charge and light matching. Remember, I mentioned we have PMTs earlier, so this is using all that information to correctly identify neutrino candidates. These are the selected neutrino energy spectra from each of the selections. So you're looking at a few different styles of histograms here. So just to clear this all up, in the top left we have the 1E 1P selection, top right is the 1EX, the inclusive one, and the bottom we have the 1E NP channel and the 1E 0P, where again N is greater than 0. And just to be clear, the signals are different colors in these histograms. That's a product of having independent analyses. They all pick their own histogram styles. So the signal for CC nu E events is the sort of a magenta-ish color here on the top left. Over here on the 1EX, it's the darker green, and on the bottom plots, it's going to be this sort of lime green color. And the takeaway here is that across the board, again, kind of like in the photon case, we are either at or below the expected standard model rate, more or less across the board, with this sort of one bin here being the outlier. So in each of these plots, it's important to note that the dashed red line is where you expect your LEE model to be. So if we were seeing a low energy excess, we expect it to look like this. And yeah, in each case, we're quite a bit below that. So this is sort of just a summary plot of what I just said, where if you actually split this up by individual channels and look at these individual energy ranges, usually 600 MeV or below. If you look at, in the LEE models in the solid red line here horizontally, and again, we're either at or below standard model in most cases, except the 1E 0P channel, where again, this one bin here is driving things way up. However, it's worth noting that this one bin is background dominated and not very sensitive here. So overall, the conclusion is that we reject the hypothesis that the LEE is solely due to CC nu E interactions at 97% confidence level. And in general, we disfavor just sort of generic low energy nu E events as the primary contributor to the excess here. Okay, so it seems like we don't see an excess in the CC nu E channels or the photon channels. What we can do here is still try to probe some beyond standard model physics, including looking for sterile neutrino states. So you have your three active neutrino flavors, and this is the idea that you would have one very high delta M squared state that doesn't interact through the weak force. So using the data from the 1EX selection for this, we do a 3+1 fit. You can read all about the details here in this public note. This is using 7 different channels. They're split between fully contained and partially contained, meaning fully contained within your detector, all the full track and the full shower and all that, and some that are partially contained. You split those up by CC nu E, CC nu mu, CC pi naught, and finally the NC pi naught channel is not split up in between fully contained and partially. Excuse me. I didn't mean to do anything if I did. I'll stand back. Okay. So if you do the fits in these channels, basically what you see is, again, I feel like I'm repeating myself at this point, pretty good agreement with the standard model. It turns out that we agree with the regular three-flavor oscillation model within about 1 sigma across the board. So no clear evidence for an additional sterile state at this point. However, we are still looking at improving our sensitivity to these sterile neutrino oscillations here. So this is our nu E disappearance sensitivity curve. The solid red line here is the main result where we look at our B&B data selection using runs 1 through 3 of microboon data. There are 5 runs in microboon. We're still working on processing and analyzing runs 4 and 5 right now, but for now this is the result here, and you can see that compared to some other results it could maybe use some improvement. A big part of this is because it turns out there's a degeneracy in sine squared theta 2,4 here, so what we can do to improve that is look at the possibility of including NUMI data. Remember, microboon is on 2 beam lines. This is one of the advantages here, is that by bringing in data from a different beam with different nu-E to nu-mu flux ratio, you can help to break this degeneracy and significantly improve your sensitivity. So to be clear, this magenta line here, which is the one for BNB and NUMI, is just a sensitivity curve. It's not the full data fit yet. That will hopefully be coming soon. And the NUMI appearance channel, it's mostly the same story. Thank you. It's mostly the same story. Our data fit looks something like this in the solid red, and you see it improves quite a bit when you include the NUMI data. So since I'm running a bit short on time, let's go ahead to the summary. So the point here is that microboon has looked into investigating the low energy excess. We've looked into the primary photon-like and electron-like hypotheses, looking at single photon channels and CC nu-E channels, and currently we don't see any obvious excess in any of those channels, which on the one hand means we don't know what's causing low energy excess yet. On the other hand, it means we have a lot of investigating to do, and this is a good chance for different exotic physics models to come into play, including the 3+1 sterile oscillation fit, although currently we don't see any obvious evidence of that, though we hope to improve the sensitivity in the future with NUMI data and improved systematics and things like that. And for more on this, you'll hear about, in Pavel's talk next, more exotic models that could maybe explain the mini-boon low energy excess. And on Thursday, you can see Xiao's plenary talk for a more general overview of microboon as a whole. Thank you very much.
Okay, questions?
Super clear.
Please.
So you're saying there are some analysis being done and presumably there will be new results. When do you think we will have enough data to be able to rule in, rule out sterile neutrino and then mixing, which is reasonable with the active neutrino?
That is a great question. I don't know if I could provide anything like super accurate, but I would guess, let's see, I'm trying to think of what what is the word I'm looking for? I'm trying to think of where we're at in terms of processing runs 4 and 5. I know it's underway. I would hope within the next year. Maybe that's too wide of a time frame.
Year. Wow.
I mean, that's a guess. I really don't know.
Thank you.
If there's no one else, we should maybe move on. Thank you. So now we hear from Pavel Gusowski about recent results and prospects for BSM searches in microboon.
Thank you very much for the opportunity to speak here, and thanks to Andrew for introducing microboon. I'm not going to spend a lot of time talking about our detector technology. I'll jump in and talk about recent results and prospects for BSM searches in microboon. As Andrew already mentioned, microboon is a Fermilab sitting on both the booster neutrino beam and the NUMI neutrino beam, and you can use these to do a lot of physics measurements. There's 4 prongs of attack for the experiment. As you've just heard from Andrew, investigating the mini-boon low energy excess. We'll hear on Thursday about our cross-section program and our R&D program from Xiao's plenary talk. But the focus of my talk today is more exotic physics than just the mini-boon low energy excess. In particular, I'll talk about some R&D for future searches. I'll then go on to some searches that we performed recently over the past couple of years, especially in the field of long-lived particles, heavy neutral leptons, and Higgs portal scalars. And I'll end up with some prospects for some near-future BSM searches, including beam-produced dark matter, and investigating sort of beyond the sterile neutrino BSM explanations of mini-boon, as Andrew already hinted at on his last slide. So moving quickly to some R&D effort that we've done to enable BSM searches in the future, and I'll begin with neutron-anti-neutron oscillation. This is a beyond the standard model a baryon number violating process. There are many different models that could predict NN bar oscillation, including certain models that forbid proton decay as well at the same time, which are interesting to look at. And this is where a neutron spontaneously oscillates into an anti-neutron and then promptly annihilates with another neutron or another proton inside the argon nucleus and produces a multi-hadron final state that we could pick up in our detector. I've just drawn an example Feynman diagram. This is an exhaustive list of different models. We could have, for example, new X1 or X2 scalars here that could mediate this process that themselves carry some baryon number. And what we're looking for, the signature is this sort of multi-pion, for example, final state, pi pluses, pi minuses, pi zeros, emanating in a star-like isotropic formation from the annihilation vertex. And unfortunately, because we're an on-surface detector, we have a lot of cosmic rays in our detector. We have to extract this type of signature outside of this cosmic ray background. And we've been developing techniques that can do this, demonstrate the feasibility of doing this type of search. Now, as we're a relatively small detector with a short exposure time, we're not sensitive. We don't have competitive sensitivity given current limits. But we are demonstrating the feasibility of this type of search, including using deep learning and machine learning techniques to really enhance our signal. And with our current sensitivity, we have a half-life of 3 × 10⁻25 years, a couple of orders of magnitude below the current limits. But again, we're doing this for June, essentially, to give them essentially the R&D to get that sort of analysis going in June as soon as possible. We've also been investigating lowering our hit reconstruction thresholds. We've managed to reconstruct these blips. I don't know how well it can show up on this projector, but we're looking for single isolated hits in our detector, essentially one wire and one time tick wide. We've managed to reduce the thresholds, lower the energy thresholds for reconstructing these hits by a factor of 3 compared to previous liquid argon TPC experiments. And using the reconstruction like this, this allows us to search for other BSM signatures. In particular, we're interested in seeing these blips along a straight line that can point back to the production point of the target a few hundred meters away from the detector. And this type of signature would be a signature of milli-charged particles that they don't really leave any ionization deposit except for single isolated, essentially delta rays, kicking out atomic electrons out of the argon, and that will produce these types of blips along a straight line that we are able to analyze and set competitive limits on these milli-charged particles. We haven't done this type of measurement yet, but look, we should have a competitive sensitivity. This blue line here is the ArgoNewt experiment, which is a tabletop-sized LAR-TPC, and we should be able to improve upon these limits in the near future. We've also been performing R&D to enhance our timing calibration and timing resolution to be able to resolve the beam structure in our PMT timing signals. What we're looking for is the 81 bunches of the beam spill that's delivered across 1.6 microseconds. This is the type of time structure we have before calibrating our PMT timing information. And then after, we're able to pick out all these bunch structure from the initial proton on target beam. And this is great for BSM signatures because sort of heavier than massless new physics should arrive slightly delayed with respect to the prompt relativistic neutrino signals. So if there's quite light new physics of order 10 MeV or so, this should arrive slightly delayed with respect to the neutrino beam. Slightly heavier new physics, up to a few hundred MeV, should arrive smeared out across the whole timing structure. But we can search for it in these sort of out-of-time windows where our neutrino background will be greatly reduced, and this will allow us to do signal versus background separation using timing. So again, we look forward to presenting some of these results in the near future. Moving on to some recent BSM searches that we've actually performed rather than R&D for future searches. I'll give you again an overview of the Fermilab neutrino beam lines. We have the booster neutrino beam. This is produced by 8 GeV protons hitting a fixed target and producing a spray of pions or kaons in the final state, which can decay either to neutrinos or to some BSM long-lived particles. We have a similar procedure for the NUMI beam. It's higher in energy of 120 GeV protons, which produce more kaons in your final state, which then again could also be decaying to new physics. These are very high intensity beams, 10 to the 21 POT of exposure, which is 2 or 3 orders of magnitude than our sort of nearest competitor at CERN, the NA62 experiment, doing similar types of searches with kaons, for example. Some example BSM processes that we can search for are, for example, dark matter production in the beam from neutral mesons, or HNL or new scalars produced in the beam from charged pions or charged kaons. And these are the processes that we've been looking for recently. I'll start with a general overview of the sort of portal mediators we've been searching for. We've searched for heavy neutral leptons or Higgs portal scalars. As I mentioned, these can be produced in pion or kaon decays. In particular, we're searching for sort of 100 MeV mass scale HNLs or scalars, so an order of magnitude or 2 below, for example, LHC searches for these particles. So it's complementary physics that we're searching for. We can search for these in the BNB beam or the NUMI beam. They provide complementary information as well. In the NUMI beam, we also have kaons that are produced at rest in the absorber of the NUMI beam, a few hundred meters away from the primary proton-on-target interaction point. So you have some kaons decaying at rest, and then scalars or HNLs can be produced here. If they're in two-body decay production modes, they'll be monoenergetic. And so they give you a very striking signal in microboon detector coming in at a very obtuse angle compared to other neutrinos or other new physics particles that could be coming in. So it's a great signature to look at. Starting with our heavy neutral lepton search, this was our first search. We've performed it roughly 2 years ago. So this has already been presented, I believe, at a previous SUSY conference. We look for these HNLs in slightly delayed window. As I mentioned, this is a 1.6 microsecond beam spill. This is an older analysis, so it's not looking at the fine timing structure. So we look beyond the end of the arrival of the prompt neutrino beams, and these HNLs, a few hundred MeV in mass, are slightly delayed with respect to the standard model neutrinos. And we look slightly beyond the end of the beam window to look for this delayed signature where this neutrino background is negligible. And we searched for these HNLs in there. We didn't see any evidence of them. And we set limits here, this blue line here, showing our limits, which is competitive or comparable to the NA62 limits at the time. There have been new NA62 limits since then. And yeah, so we're very comparable there to NA62. We do have a new publication out in the next couple of weeks, which extends our sensitivity further down about an order of magnitude in the U-mu4 squared, so U-mu4 squared parameter space. So I hope you look forward to seeing this publication in a few weeks. In terms of the Higgs portal scalars, apologize for this typo. So again, I mentioned we're looking for scalars that are produced in two-body decays of kaons occurring in this NUMI beam dump, which come into the detector slightly backwards with respect to the typical neutrino direction, which is going forwards and produces this sort of downstream spray of showers. So you can see the scalars will come in, and for our first search, we searched for electron-positron decay signatures of these scalars. In this simulation, you can see the electron and positron coming out in a sort of upstream going direction with quite a large opening angle. This is a BDT-based selection that we have. You can see here, for example, BDT of our background in this blue and gray background here. You can see our data points in black follow the background distribution pretty well. The signal-like BDT score distribution would be this green signal. You can see in our sort of signal-rich region, we do not see a significant excess of data over the background. In particular, we see one event in our signal region compared to two expected background-only events. And so we use this information to set a limit on Higgs portal scalars with masses below 200 MeV for this E plus E minus production mode. And we actually set the world's best limit, you can see here in the blue line, the world's best limit for masses close to the pi0 mass, 135 MeV, in this small narrow range where our nearest competitor, the NA62 experiment in red, actually loses sensitivity here due to them having a large pi0 background, which we do not. And so, so this is a world's best limit around here. This was only 10% of our NUMI dataset for these first results. We are going to have further search results to come in this E plus E minus mode, probably within the next year. We're also going to look at higher masses for the mu plus, mu minus modes and pi plus, pi minus modes. And again, this is a publication that will be out in the next few weeks, and we'll have a very good exclusion region around here. This plot is from the theorist's expected sensitivity, which we follow very closely. Theorists have also reinterpreted this results in a few other models. This group here reinterpreted our result in terms of HNLs, heavy neutral leptons, decaying to standard model neutrinos plus E minuses. And given this reinterpretation, they expect us to be sensitive, have world-leading sensitivity for heavy neutral leptons and masses below around 100 to maybe 30 MeV or so. This other group reinterpreted our results in terms of axions. So axions decaying to E plus E minuses. And again, there's a small region of the parameter space where we should have world-leading sensitivity in this sort of light gray region down here. So theorists are also very interested in our results as well. So finally, moving on to some near future. Scatter elastically or inelastically inside the detector. We'll be searching for these inelastic scattering signatures where a dark photon is radiated and produces an electron-positron in the final state coming from the dark fermion scattering of argon. This is the sensitivity that this group of theorists here in this publication expect us to have 10 events. And we do have our own sensitivity calculations using our full detector simulation, including reconstruction efficiency and backgrounds. Will be presented in a poster in a few weeks' time in ICHEP. It's quite similar to this type of line. And the results of this search should be out in the next coming year as well. We're also searching for the beyond sterile neutrino oscillation type of BSM signatures that could explain the mini-boon low energy excess. And Andrew already presented what mini-boon actually sees in their detector, either electron-like or photon-like showers. They could also be seeing fundamental production of electron-positron pairs directly sort of in the prompt, in the sort of hard scattering process itself. In the neutrino interaction, there could be new physics that produces electron-positron showers, which could be highly collimated or very asymmetric, where they end up looking like a single electromagnetic-like showers. Now, there have been quite a few models since around 2018, so it's very recent compared to the mini-boon low energy excess, which has been around since 2008, where they've started examining and building these models that can produce sort of E plus E minus signatures. As I mentioned, we've already been searching for E plus E minus production, in particular in this scalar decay mode that you can see here, or in this dark trident production of electron-positron pairs, which we're actively searching for. So now we've kind of turned our attention to these E plus E minus signatures inside microboon itself to kind of rule out or hopefully observe something that could explain mini-boon based on BSM E plus E minus production. I've given here a few example processes that could produce these E plus E minus signatures. I haven't covered all sorts of models that have come out yet. If you're interested in these models and you've built your models on your own and would you like us to search for these in microboon as well, you could contact us. you could contact us, and you can get bonus points as well if you've actually written a generator. That's been our main sort of stumbling block. We don't have generators to produce these models until a few months ago. I've just given you a few examples here. Again, it's a non-exhaustive list. You can have upscattering of neutrinos via heavy neutral leptons of carbon or argon, and decay back into a dark gauge boson, which itself decays to an electron-positron pair. You can have models involving dark Higgs or extended Higgs scalars or two Higgs doublet models, where you can have a very similar upscattering procedure, upscattering process, which again produces electron-positrons. You can also combine vectors and scalars and have this vector boson fusion type process, again producing electron-positrons in your final state. Or you can have upscattering of dark matter in the detector, again in this dark trident-like process, which produces electron-positrons, or a dark Primakov scattering process, which produces either a photon, or if you swap these two, an electron-positron in your final state. So we have begun investigating these. Andrew already showed this plot. He showed the single photon search, where they're essentially searching for E plus E minus production already. We could have evidence of some of these models already, and we're evaluating the efficiency of these models within this final state. But given the fact that there's been a few generators coming up on our radar since sort of March this year to directly produce these type of E plus E minus signatures, we have actually started developing our own simulation and reconstruction techniques to pick out these sort of E plus E minus production, direct production in the final state. So I hope to come back here maybe in the near future and present our exclusion or observation of these types of modes in the near future. So to summarize, microboon is not only a neutrino interaction experiment or oscillation or cross-section experiment, but has a strong BSM program too. There's been R&D efforts in terms of searching for an NN bar oscillation or searching for milli-charged particles or improving the timing reconstruction. We've searched for long-lived particles, namely heavy neutral leptons or Higgs portal scalars, and we have very competitive sensitivity to other experiments, especially at the LHC. We have more on their way soon, very soon, and we should have competitive sensitivity to sub-GeV dark matter as well, and I look forward to presenting these results. And finally, as I just mentioned, we're aiming to release our first results on these mini-boon targeted E plus E minus BSM searches in the coming year. Thank you very much.
Thanks a lot. Questions? Could you maybe comment once more on these models which predict neutron-antineutron oscillations?
Sure.
Show them on the first slide.
I showed one example. Oops. Yeah, I'm not a theorist, so maybe I won't be able to answer all your questions.
Yeah, so these are leptoquarks, is that correct?
These aren't leptoquarks, they don't carry lepton number. They carry just baryon number. There might be some models with leptoquarks, but they induce proton decay as well, so there's been more exclusions on them, I believe. Not really.
Maybe I'll So both you and, in principle, Dune will be using liquid argon, and Dune always mentions that they will be able to probe proton decay, right? Well, you are able to do this neutron-antineutron oscillations. So what's the difference? Why can't you do proton decay and because they never talk about neutron-antineutron oscillation that I know of.
They are actually, there have been sensitivity studies on NN bar as well. We are also very, again, we're not expecting to have any sort of competitive sensitivity to proton decay. We are doing some, so indirectly we're helping in a sense because we can search for kaon production or hyperon production, which have similar signatures to proton decay. So we can sort of examine backgrounds that we present there in neutrino-induced hyperon production, for example. But yeah, I'm not sure exactly why we've never actually searched for proton decay ourselves. It's been much more studied for Dune, so whereas NN bar is slightly more obtuse. Sorry?
I guess you just don't have a large enough target mass.
Exactly, yeah.
Okay, you have probably a too small target mass because the proton decay is at 10 to the power of 34 years approximately. You won't have a rate to
We'll probably have a similar sensitivity to this.
Yeah.
And way too low sensitivity reach.
Okay, there's one comment, then we should move on.
I remember there were some old models about, talking about light neutralinos, very light neutralinos, mainly in BINOS, that behave through our parity violating couplings. I don't know if you looked at
I don't think anyone on the experiment has looked at neutralinos or anything directly SUSY related. I'd be very interested in seeing those models. I'll probably look them up.
These models were saying that basically the neutralino mass is 0 and then no bound exists because it's mainly BINO and then you have RPVs.
Would they be produced in our beams maybe? Because
they have been proposed to explain an old Newteva anomaly.
Okay.
Very old.
Okay.
Just 20 years ago.
Mm-hmm. So our beams are very low energy compared to maybe LHC, so who knows? I'll be very interested in seeing that.
Okay, thanks a lot. We should maybe move on. Thanks again.
Version 2.
Okay, our next speaker is Juntaro Wada. Apologies if I didn't get that tone correct. Will be telling us about probing the L mu L tau gauge boson at the Muon A experiment.
Thank you for introduction. I'm Juntaro Wada, a PhD student in the University of Tokyo. So today I'd like to talk about the new gauge boson search at the Muon experiment. Today's talk is based on this paper. Okay, so first, let me explain what is Muon experiment. So as you know, the measured value of the Muon G-2 deviate from the value calculated in standard model. And the standard model calculation includes the QED contribution, electroweak contribution, and hadronic contribution. It is important that the largest error in the standard model prediction comes from this hadronic vacuum polarization contribution. And the Muon experiment is motivated by such a large error. In this experiment, the cross-section of the mu-E to mu-E scattering, this is T-channel scattering, can be measured precisely. And through such a precise measurement, the size of this hadronic contribution in the space-like momentum region is extracted. And using this information, we can determine this hadronic HVB contribution to the Muon G-2. So that is a brief overview of the Muon experiment. On the other hand, many theorists consider this discrepancy called Muon G-mass anomaly may be a sign of some new physics contribution. So now I have a question. So is it possible to search the BSM physics at the Muon experiment? As I said, Muon experiment aims at examining the warmed standard model contribution. However, if we can search the BSM physics at the same experiment, it sounds interesting. So today I'd like to discuss this possibility. And there are some models which can explain the Muon G-mass anomaly. But hereafter, I'd like to focus on the UMU gauge symmetric model, which I'll explain later. Okay, here is the outline for my today's talk. So today, first, I'd like to explain the Muon experiment in more detail. And second, UMU minus gauge symmetric model. And third, I'd like to discuss about new physics at Muon. Okay, so let me begin with the Muon experiment setup. So as I mentioned, Muon experiment aims at determining the HPP contribution by observing the mu into mu scattering. To do so, in this experiment, Muon with energy of 150 GeV collide with the electron at rest. So in other words, Muon experiment is a fixed target experiment with muon beam. So muon comes from the emitter beam line like this figure and scatter with the electron. After scattering, we can observe the scattering angles by tracker signature, and the energy of the electron is observed electron colorimeter. Okay, so next, let me briefly summarize the kinematics of the signal for Muon experiment. So here is the mu e to mu scattering, which is the signal for Muon experiment. But it's just 2 to 2 scattering, so we know the kinematics of this process very well. For example, we can easily derive the relationship between the energy of the scattering angle of electron and the muon scattering angle, like this figure. And of course, we can derive the relationship between muon scattering angle and the energy of electron like this. In the Muon experiment, this relation is useful to remove the background. Okay, so let's move on to the Ioannina minus the gauge symmetry, which we focused on. Okay, Ioannina minus the gauge symmetric model is one of the standard model extension. And here, this figure shows the charge assignment of this model. So we assign with +1 charges with the muon flavor particles, and -1 charges with tau flavor particle. And also we add new gauge boson, Z prime, to standard model. So that is minimal setup. And here, I listed some of the features of the mu minus the gauge symmetric model. One is that there is no electron direct interaction. As you can see, we do not assign with the charges with the electron flavor particle, so Z prime does not interact with electron. In contrast, we assign with the charges with neutrinos, so there are some discussions related to the neutrino sector in this model. For example, neutrino restorations and genesis. Okay, next let me explain the constraint on the parameter region in this model in the context of the Muon G-2. This figure shows the Muon G-2 favored region, which is green band, and the horizontal axis means the mass of Z prime. Axis means the coupling, and this shadow area means the experimental constraint. So in the region of the more than twice of muon mass, the possibility to explain the Muon G-2 was already excluded. For example, this constraint comes from the QQ bar to 4 mu process, and this constraint comes from the E minus E plus to 4 mu process. And on the left-hand side of this figure, this constraint comes from electron-neutron scattering. So in the context of the Muon G-2 anomaly, the mass of Z prime and the coupling should be around here. Okay, so then I'd like to discuss the new physics at Muon experiment. So when we consider the new physics at the Muon experiment, we can come up with simple 2 possibilities. For example, first possibility is the mu e to mu scattering. I mean, the new physics can affect this mu e signal process. And second possibility is that if new physics, I mean Z prime exists, we may be able to search the production of Z prime at Muon experiment. regarding first possibilities, there are some previous researches. For example, in this paper, the author discussed the heavy new physics and dark photon. And in this paper, the author considered the U mu minus tau gauge symmetric model. However, in summary, they conclude that the possible new physics effect in mu to mu scattering expect to lie below the muon sensitivity. So the new physics effect is small in this context. In contrast, there is no previous researches in the context of a second possibility. So we proposed to prove the L mu minus L tau gauge boson Z prime the muon experiment in this paper. Okay, so let me explain our proposal in more detail. So our signal is the mu Z prime, but as I mentioned, in the context of the muon G mass anomaly, the mass of the Z prime should be smaller than the twice of muon mass. So it means that Z prime cannot decay to muon pair, but can decay to neutrino pair. So our signal is mu E to mu E Z prime, and Z prime decays to neutrino pair. In order to search this process, we consider the invisible search. It means that, of course, we cannot detect Z prime directly, but we can somehow extract information Z prime from the observation value in the muon experiment. Of course, there are some backgrounds. For example, Bremsstrahlung, it should be one of the background process. And the electroweak process may be one of the background process. Okay, so in order to remove these backgrounds, we consider the following selection criteria: imposing the kinematic cut on the muon scattering angle and energy of electron. And we also impose the photon veto. Here we note that mu to mu scattering, which is originally a signal for the muon experiment, is one of the background in our proposal. However, as I said, we know the kinematics of this process very well, like this figure. So we can remove this background, imposing the kinematical cuts. In contrast, we cannot remove the electric process by imposing the kinematical cut because, for example, the kinematics of this process, here Z is not Z prime, Z is the standard model gauge boson. So kinematics of this process is same as our signal, so we cannot remove it by imposing the kinematical cut. So we evaluate all of the electric process, not only this process, in Monte Carlo simulations. So let me explain our strategy in more detail. So as I said, we know the kinematics of this process, like this curve. So we impose the following condition. Theta mu, this is the muon scattering angle, should be larger than 1.5 milliradian, and the energy of electron should be smaller than 25 GeV. Then, as you can see, we can distinguish signal from the elastic curve, this background. And regarding the electric process, for example, this one, as I said, we evaluate this the number of events of this process in Monte Carlo simulations, and we got 10 to minus 4 events. So it's negligibly small. And here, let me comment on the other background source, multiple scattering and nuclear scattering. This effect strongly depends on the experimental setup, and it's not fully fixed yet. But we expected this background should be well controlled, because if multiple scattering occur, then we should observe the kink or branch of the track. And if a nuclear scattering occur, then we should observe the track multiplicity. Okay, so lastly, let me show our result. Left figure shows the distribution of the energy of the signal event for the two parameters, mz prime equal to 100 MeV and mz prime 10 MeV. These parameters can explain the muon mass anomaly, and in both cases, as you can see, the large number of events remain after imposing the kinematical cut. Here, the shadow region means the kinematical cut. I mean, the energy of electron should be smaller than the 25 GeV. And here is the experimental cut. We assume the energy of electron larger than 1 GeV. On the right figure, this figure shows the contour of the number of events. So again, this band, the orange and yellow band, means the muon mass favorable region at the 2 sigma and 1 sigma level respectively. And this red star means the benchmark point used in left figure. So as seen in this figure, 10 to 3 events is expected around the muon mass favorable region. And for low mass region, order 1 event is obtained for Z prime. This is coupling of the this is coupling as a few times 10 to minus 5. Okay, so this is summary. So the muon collaboration intends to assess the hadronic vacuum polarization contribution to the muon G-2 via elastic mu E to mu E scattering. We show that the L mu minus L gauge boson Z prime can be searched for at the muon experiment by imposing kinematic cuts on muon scattering angle and the energy of electron. And also we impose the photon veto. So our result show that the muon experiment is also sensitive to the new physics, and therefore it can serve double purpose, searching the standard model contribution, and also we may find the Z prime in the future. So that's all. Thank you for listening.
Thank you so much.
Okay, thanks for the nice talk. Can you go back one slide, please? How long would it take you to actually get to this sensitivity? You say you get 1,000 events, but this is assuming a certain number of years of running?
We assume the, you mean luminosity? No?
Yeah.
We assume the 15 Fermi inverse, 3 years.
Hi. So I had a question that since this experiment runs to see the hadronic vacuum polarization contribution, and there is, as you said, a large uncertainty in the standard model. So we do not know the standard model expectations of this process very well. So while doing the BSM analysis, so is that error did you take into account that error from the hadronic part that might run in the loop?
Sorry, could you say again?
So since the hadronic part is not very well known, if there's a hadronic loop in the propagator, and as you said at the beginning, that's why like that's the whole reason to do this experiment. So while doing this analysis, how important is to take those hadronic contributions, which will also change, the angular distributions of the final state muon. And that's why they have so nice, angular precision in the experiment. So did you take those into account? So your standard model calculations, are they like LO calculations or are they like NLO calculations?
Sorry, I cannot hear your question clearly. Sorry.
So maybe I can use talk without the mic. So your standard model calculations, are they like LO calculations or do you take hadronic NLO effects as well?
So
leading order next to leading order.
In the Muon experiment?
No, for the standard model calculation of the hadronic.
Standard model calculation. So in the Muon experiment, they of course include next to leading order. I mean, in the calculation of the hadronic vacuum polarization. But still, in the white paper, they include, of course, the next lead order calculation. I mean, in the calculation of the hadronic vacuum polarization, but still largely exist. So that's why Muon experiment is proposed. And actually, our proposal is independent of the.
That's not my question. My question is, since the standard model expectation of this process is not very well understood because of the hadronic vacuum polarization tubes, and that's the whole reason this experiment ran. So, is it possible that what you interpret as new physics is basically like an artifact of that hadronic part of the calculation that we do not know very well how to do it? So that's why I asked whether when you say what is the standard model background, are you doing LO calculations or NLO calculations as well?
So in the context of astrology, it's
It's fine. We can sort of
discuss.
Yeah, okay. Yeah, we can discuss.
Yeah, then let's move on and think.
I'll try to make it fast. Since I have a non-COVID cough. It's a cough.
Okay, so now we hear from Joel, Jones Perez. Right, about the assessment of the dimension 5 seesaw partial impact on exotic HCBAs on non-pointing photon surges.
Okay, can you hear me? Yeah? Okay, thank you. So I'd like to begin by thanking the organizers for giving me the chance of giving this talk. So this is in the context of the seesaw model, which you probably know very well. This gives light neutrino masses by adding heavy sterile neutrinos with Majorana masses. Now the standard law says that if these guys are around the GeV scale, then the couplings are too small and you cannot test it. But that is not really correct, since you can enhance the mixings. If you have more than one heavy neutrino, then you do get the typical suppression of square root of m light over m heavy, but you get these additional parameters that allow you to enhance the coupling. So this is why people are searching for heavy neutrinos in these models, right? Because it does make sense. Now, this talk is not really about this. It's about the extension of the seesaw model with dimension 5 effective operators. Now, besides the Weinberg operator, if you go to dimension 5, you can add 2 extra operators. One that has got 2 Higgses and 2 steriles, and one that has got 2 steriles and a B mu nu. So the steriles will couple to the photon or to the Z. Now, in the previous case, the heavy neutrinos would have interactions through the active heavy mixing, right? So in this case, now the light neutrinos can feel these interactions through the light sterile mixing, okay, which is related to the other one. So in the following, I'll be focusing mostly on the dipole operator, right? So here, for this not to vanish, you need at least 2 sterile states, since it's an antisymmetric operator, and that's that. Okay, so first of all, what we're interested in this talk is searching for long-lived heavy neutrinos. So in order to figure out if these neutrinos are long-lived, you have to calculate the decay width, right? So first thing, when you turn on these new operators, you get a new decay channel. So the heavy can decay into a light and a photon, right? And this will go through this kind of coupling, which is a dipole coupling, then a sterile light mixing and a sterile heavy mixing, right? This has been done a long time ago, and it's been found that this decay will usually dominate. However, the three-body decays in the standard CISO also receive modifications. So we decided to calculate these modifications, and we found out that besides a typical Z, you also had a contribution from a virtual photon, giving you a structure like this one, right? Again, you have the mixing, sterile light, sterile, and sterile heavy. So with these two things in hand, we recalculated the branching ratios and the lifetimes. So with the branching ratios, this is the branching ratio of a heavy neutrino into a light and a photon, and this is one of the typical three-body decays that you can calculate. And what we find is that, of course, if the heavy neutrino is light, or if the coupling is very large, then of course the decay into a light neutrino and a photon will dominate. But if the neutrinos are heavy and the coupling is not that big, which is what one expects, then these branching ratios will not be 1. They will be low. And of course, these ones, the three-body decays will start to increase. So on the GeV regime, it is important to calculate the three-body decays besides the two-body decays. This is particularly important for checking the lifetime. So, for instance, this is the decay length, and this is the result for a coupling of 10 to the, I don't know if you can see this, 10 to the minus 2 GeV to the minus 1. And here we see a lifetime, a decay length between, let's say, 1 millimeter and 10 millimeters or so, and 100 millimeters. And of course, with a decreasing coupling, then the decay length starts to grow. Now, on gray, we are showing the lifetime that you would get if you only include the two-body decay, right? And you see that for the blue curve, which is a large coupling, then it's okay. You can assume that the two-body decays dominate. But as the coupling gets smaller, then the three-body decays start being important. And you can see that if you do not include the three-body decays, you can get an error of about like 3 orders of magnitude on your decay length, right? So it's important to include the three-body decays if you are on the GeV regime. Okay? Now, we also calculated the modification to these three-body decays. Then we found out that they were mild. Basically, they would lead to a modification of less than 10% on the decay length. So this is what you get if you calculate your decay length with the full calculation or using only the standard CISO three-body decays, right? And you see a modification of less than 10%. So this might be important if you actually observe these things at some point. Okay, so now we know what kind of decay lengths you have. Now let's put some constraints. So for heavy neutrinos on the GeV scale, you do not get a lot of constraints, right? Most of the astrophysical constraints go away, the cosmological constraints go away. Constraints on the dipole moments of the light neutrinos will also go away. The important one mainly comes from LEP. Okay, so LEP is sensitive to this process, E plus E minus, going to a heavy neutrino and a light neutrino, and then the heavy one will go to a light one and a photon. So it's a search for a photon and nothing else. LEP has put a constraint of 0.1 picobarns on this production cross-section, right? So, well, you can calculate this. You can assume, you can calculate this. We don't do that, but you can calculate it assuming an infinite detector, no cuts, no nothing, and you get a relatively simple expression for the cross-section. This part is what one finds usually on the literature, which assumes that the heavy neutrino is produced mainly through the dipole operator. But here we have included the production via the standard SISO coupling. So the standard SISO coupling is this one, which I have written it up here, which depends only on the mixing and not on the dipole. And of course you get an interference term. So this I've put just to display the typical dependence, but in reality, we do put the cuts. We assume that the detector is not infinite or anything. So these are this is one of our main results. These are the constraints on the dipole operator, on the dipole coefficient, coming from LEP. Not only on the GeV regime, we actually extrapolated down to the sub-GeV regime. We find that if there is no enhancement on the mixing, there are no constraints. The cross-section is not large enough. However, we can start enhancing, right? Here we have a 10 to the 3 enhancement with respect to the naive SISO expectation, 10 to the 5, 10 to the 6, up to 10 to the 9, right? So if we go to 10 to the 3, we get this curve. This curve is easy to understand, right? So if we go to the right, the mixing starts to decrease because it goes like square root of ml over mh. So as mh increases, the mixing decreases. So then your coupling needs to be larger to achieve the same production cross-section. So that explains this curve here, and this one is due to the lifetime. Right? So over here, the heavy neutrino starts escaping the detector, and you need a larger cross-section to produce enough neutrinos so that you will detect them. Now, if you keep enhancing the cross-section, you start getting these little, I don't know, horns or things, like this one. So this is due to the production process being dominated by the standard SISO. Okay, so this is why at some point the bound stops depending on alpha, right? So you get these vertical lines because the production is completely dominated by the standard SISO coupling. However, the decay again goes through the dipole, so you still get this cut on the lifetime at some point, right? Then if you keep increasing the enhancement, at some point your coupling is so small that the branching ratios start not being 100%. So you start getting these cuts over here, right? And then at some point you get to the 10 to the 9, and that's more or less where you reach the unitarity limit on the mixing, and you cannot exclude anything else. So this is more or less the typical exclusions that you would expect depending on the mixing that you have. Now, once we do this, we go to the final part of the talk where we focus on the non-pointing photons at Atlas. So what is a non-pointing photon? So this was discussed in the plenary, but just in case I'll repeat it. This is a case where you produce a long-lived particle, so it's produced in the primary vertex, then the long-lived particle starts propagating, and then it'll decay into a photon in this direction. Then the experiment extrapolates back and realizes it doesn't come from the primary vertex. Okay? So that's a non-pointing photon. So this distance of closest approach between the extrapolated direction of the photon and the primary vertex is what you call delta Z gamma, right? So naively, delta Z gamma will be 0. And the other important variable is the arrival time of the photon, the relative arrival time of the photon. Now, as of now, the only published experimental paper on non-pointing photons are for 8 TeVs, right? And they are designed for very heavy, slow-moving, long-lived particles, right? So since we are on the lower GeV range, we don't expect this to be too sensitive, but it's good to try anyway. So what we decided to do is produce the 2 heavy neutrinos via an exotic Higgs decay. So what do you need to get this exotic Higgs decay? You need this 2 neutrino, 2 Higgs effective operator that I talked on my second slide, right? This is the other effective operator that you're allowed to have. It's not the dipole, right? So this is how we produce them, and then we make them decay via the dipole. And if you make an exclusion, you can actually say something about this coefficient. Now, the problem is that the photon cuts are too strong. So in this search, you require 2 photons with energies both above 50 GeV. Now, we are producing the Higgs via either gluon fusion or vector boson fusion, decaying this time into heavy neutrinos, having 50 GeV masses, right? So we get in one case 7,000 events, almost 1,000 events. But then you realize that after you put on the cuts, in one case less than 1% of the events remain. In the other one you get a little bit under 3% of events. So that's very few events. But that's not the worst part. The worst part is that then the signal regions are not optimal. So here the distribution of events for several heavy neutrino masses, for events passing the cuts. And there you see, this is a signal region, right? So nothing. And this is a signal region, so you're like really on the tail. So this is a problem, right? Because even if our photons pass the cuts, and they had a large T gamma, and they had a large delta Z gamma, which they do, they are usually assigned to either the background or the control regions. So this doesn't really work for the model. So we gave up on this. We're going to propose an alternative way of searching this, but then we found that somebody had already done it, right? We found a PhD thesis and some recent conference notes, okay, I'm about to finish, that looked for softer photons, triggering the Higgs production with an associated lepton. Okay, this is a biatlas, right? So we decided to recast this search, but since we're already working with BBF, we decided to keep our work with BBF, and we're currently implementing the trigger with the associated lepton. So with BBF, you see that the distribution is much better, right? So this is the signal region proposed by the new search, and we find that it's much, much better. So after putting all of the cuts, we get a much better number of events, and we can even populate their delta Z and T gamma bins. So these are the different delta Z categories. So this is a small delta Z, and it keeps increasing. Right? So this is our prediction. And for each delta Z category, you get different T gamma, right, with different delay times. And what we found was that for low delta Z and low T gamma, our model was really bad, right? But for large delta Z and for large T gamma, our number of events was quite comparable to what you found on the thesis, right? Now, we did this with vector boson fusion, which in principle implies smaller backgrounds. So we thought this result was very encouraging, right? So let me conclude. What we've done here is we have studied the type 1 CISO portal with dimension 5 operators, with features new interactions that involve the sterile states. The light neutrinos can participate via the mixing. These modify the branching ratios of the heavy neutrinos. These modify the lifetimes of these heavy neutrinos. And it is important not to neglect the three-body decays. Now, Lepton plays bounds, but only if there is enhancement. If you don't have enhancement, you have no bound. So if the heavy neutrino is long-lived, then you in principle can use the non-pointing photon searches, not the old ones, but the new ones. So we consider our findings encouraging. We recommend the experimental collaborations to take into account our proposed trigger. And we also beg you to please stay tuned for our recast featuring the associated Lepton trigger. Thank you very much. No cough.
You mentioned searches at LEP for your heavy neutrinos going to nu and gamma. But you also mentioned that, I mean, you get a dipole operator, so you get a virtual photon that could go to QQ bar or IL bar.
Yes.
So I think I missed, but I mean, there are searches for heavy neutrinos going in the GeV range, going to a neutrino and two charged leptons. Like, I think CMS is very sensitive.
Sure.
Are they not competitive with the search?
No, no, not really, because their branching ratios are still somewhat low, right? So they have a very diminished. I mean, so at this point here, yeah, that's where these other searches could matter, yeah, right? But still, their branching ratios are not that large, okay, right? So maybe for a 10 to the 9 enhancement or so, where the dipole operator goes under 10 to the -6, that might be the case. That the other ones could be relevant. We didn't look at that.
Okay.
Since we were actually surprised to be able to reach 10 to the -8, right? So yeah. Maybe it's a good idea to have a look at what are the branching ratios to these lepton channels. Yeah.
I mean, in the case of leptons, you can compare lep to CMS.
Yeah, exactly.
CMS wins down to GeV or so.
So here actually you have to look at the long-lived particle searches.
Yeah.
So that will have, let me see, the mixing there, they exclude a mixing down to 10 to the -6 or so. For neutrino masses up to 10 GeV. Up to 10 GeV. Yeah, it's like a little tongue in there. So it's up to 10 GeV.
Down to 2, no?
Sorry?
Down to 2 GeV or so.
Or so.
Or 3.
Yeah. So yeah, maybe we should have a look at this small region over here for these values where the branching ratio starts being cut off. Yeah, that's correct. We should have a look at that.
Okay.
Yeah. Thanks for the comment. Yeah.
question. So, what about 4-body decays? Because you said that 3-body decays, or say, like the mistake that you made could be a factor of 10 to the. Oh, sorry. So you said that if you neglect the 3-body decays, your result for the lifetime can be off by a factor of 10 to the 3, if I got that correctly.
Right.
Point,
So,
right?
so the statement is that, yeah. So if you only take into account 2-body decays, then in some regions, yeah, your decay length could be off by as much as 3 orders of magnitude.
Yeah. Yeah. I was just naively thinking then, if that error is so large, what about maybe 4-body decays? I guess then we would need to go to dimension 6. But did you ever think about
4-body decays? So that is, I mean, usually that 2-body decay wins due to the phase space, right? Because it is a suppressed channel, since it needs the extra mixing. But usually it, and it's I wouldn't know. I wouldn't expect it because you need more couplings, right? And the phase space is suppressed. So I wouldn't
I guess so too. Just wondering, since
expect that.
Yeah, difference here was so large between like, the 2.
Right,
yeah.
right. The thing is that, yeah, it's not, so here you see that the 2-body decays depend on mh cubed. The 3-body decays, not this one, but the other 3-body decays will depend on mh to the 5th. So at some point, when the mass is large enough, these other decays start being more important.
Okay.
I wouldn't know 4-body decays, what their behavior would be.
Okay.
But in principle, when you say 3-body decays, you're actually talking about multi-body decays, because you do the 3-body and then you assume that the quarks, you know, they become jets at this point, and it's actually a multi-body, which is estimated via the 3-body decays. That's what the QCD correction is for. Take into account the multi-body decays.
Thank you. Any other urgent question or comment? If not, let's thank our speaker again. And
thank you.
And we'll move on. Now we have Ulrike Fahrenholz telling us about searches for proton decay with Juno.
Let's see, which one is the laser? Sorry. Oops. Sorry. Guess. Okay, sorry. I clicked the wrong button. Okay, hi. I'm Ulrike Fahrenholz, and I'm a PhD student at the Technical University of Munich. And I will present you Juno's prospects on proton decay search today and a little bit of my efforts on that topic. So first, in the standard model, we all know baryon number is a global symmetry. So in the standard model, we describe it to be conserved. But due to several reasons, for example, the observed matter-antimatter imbalance in our universe, we impose beyond standard model theories, such as grand unified theories, where we have the coupling of the electroweak with the strong force. And in those, the baryon number is violated, and therefore we have possible decays of photon and so what we heard already of the neutron-antineutron oscillations. Those coupling happens at energy scales of 10 to the power of 16 GeV, which is an energy scale which we cannot produce usually in our experiments. So we test those grand unified theories by looking at effects such as the named ones, for example, the proton decay. The main proton decay channels, which are discussed usually, are first the proton into a pi0 and a positron, which is the leading mode in many non-SUSY guts, and its current limit has been imposed by Super-Kamiokande to be 1.4 10 to the power of 34 years with a 90% confidence limit. This is therefore the decay mode for the proton decay with the best degree of accuracy. Another very important proton decay mode, which is imposed mostly by SUSY guts, is the proton decay into a K plus and an antineutrino. And also here, the best limit was imposed by Super Kamiokande, but it is way less good than the first one. It is 5.9 10 to the power 33 years with 90% confidence level. As the proton decay lifetimes are at the order of a few 10 to the power of 34 years to be predicted, in this case it is that, in the other one it's 10 to the power 35. This is more than one order of magnitude away from our prediction. So what we want to do, we want to improve the limits by using liquid scintillator detectors, for example. So first I will explain to you the detection mechanism in Super Kamiokande, for example, so in water Cherenkov detectors, where we have kaon energies for the decay kaon which are below the Cherenkov limit. This means that our kaon is invisible in our detector. Water Cherenkov means we have mostly hydrogen and carbon. From the hydrogen events, then, we would only measure the decay products, mainly the muon, of the kaon. In case of the oxygen proton decay, we can also use a photon tagging technique on the excited nitrogen atom, which remains after the proton decay, and therefore improve the sensitivity by some measures, but still it is a little bit difficult to do that. In case of liquid scintillator detectors, we have proton decays where the kaon scintillates in the detector. Therefore, we can not only measure the decay products of the kaon, but also the kaon directly itself, as well as all decay products remaining. Juno is one of the largest liquid scintillator experiments ever proposed. It is right now being built in southern China and is an acronym for Yangmen Underground Neutrino Observatory. Its main goal is to detect the neutrino mass hierarchy by measuring electron antineutrinos from the two reactor sites at 53 kilometers away. Other physics goals involve precision measurements on oscillation parameters and detection of atmospheric, solar, geo, and reactor neutrinos. It also measures supernova neutrinos and aims to find the DSNB, the diffuse supernova neutrino background. It consists of a large water Cherenkov pool with an acrylic vessel inside. The acrylic vessel has a diameter of 34 meters and is filled with about 20 kiloton of liquid scintillator. Everything is held by a stainless steel structure, and there are about, you see, overall over 40,000 PMTs instrumented around that. Here you can see, for example, one of those PMT arrays. We have 20-inch PMTs and 3-inch PMTs arranged like that. Also, the water pool is instrumented with PMTs, so we can easily veto events happening in there. The liquid scintillator mixture is a different one, which you might know, for example, from Borexino. And Borexino is pseudocumene. In this case, we use linear alkylbenzene. Linear alkylbenzene is a molecule of a benzene ring with a tail made from carbohydrates. And therefore, our main target mass consists mainly of hydrogen and carbon. This means that we have two different decay kinematics for a proton decay happening in Juno. In case of a free proton decay, we have a free proton, meaning a hydrogen atom, decaying into the antineutrino and the kaon, which is a two-body decay and therefore has fixed energies. This means that the kaon in the end has a kinetic energy of about 105 MeV. In case of a bound proton decay, so a proton decaying from a carbon atom, we have not only the energy of the proton, but also the energy of the Fermi motion of the proton inside the nucleus, accounting into the decay products. As well, we have to take account for the binding energy, depending on which state this proton is in, when measuring our energies for the decay products. This means that in the end, for the K+, we have an energy range of 25 up to 207 MeV. In the overall, we can put together a signal in Juno for the proton decay. The overall signal consists, here you can see the hit time of the photon electrons created by the particles in Juno. So here's the kaon signal, but then we have a very short lifetime of the kaon of about 12 nanoseconds. then to the Muon signal, which is the first product, the main product with a 60% chance of the kaon. And in the end, one Michel electron way later, about 2.2 microseconds away, which we have then, therefore, a triple coincidence. So we have, to sum up, for all of those particles, pretty well-defined energies, which we can easily calculate. And we have a well-known time structure for this event. So we can do precise event selection on events like this. If we talk about an event and its signal, we need to talk about its backgrounds. The proton decays in the region of a few hundred MeV over all deposited energy in the liquid scintillator. There, one of the backgrounds is, of course, cosmic muons, but those we can easily veto by using the Water-Cherenkov pool around and the top tracker, which is also installed on top of Juno. The main background which we have is the atmospheric neutrino background. Here, atmospheric neutrinos can produce directly muons in the liquid scintillator, or they can produce kaons, which then decay. Those events need to be vetoed precisely. So I'm talking now about how do we select those events. First of all, we do a cut on the overall visible energy. And here you can see the background count, which we balance with our signal efficiency. So we do a cut on the total visible energy and on the fiducial volume of our detector. So we narrow now down how much energy is deposited in there. Afterwards, we tag that only exactly one Michel electron happened in there, because all possible events, not all, but most possible events of atmospheric neutrinos produce more than one Michel electron. So we tag only events with exactly one. Also, one of our main backgrounds can be fast neutrons. So we tag our neutron capture. If there happened a neutron capture, we know this wasn't a proton decay event. Then, in the end, what we leave is that we need an analysis of a time structure of our overall event. Here you can see a simulated time structure with the hit time and the count, where you have a first peak for the kaon and a second peak for the decay muon. If now the kaon doesn't live as long as we suppose, for example, here, which can happen, then both peaks smear into each other. That also happens when we estimate that our time resolution isn't as good as we want it to be. So if those two smear into each other, then we might not see both peaks perfectly. So what we have to do is we have to do a fit of those two peaks, and then look at the time difference happening between the two peaks. We look at how good the fit was, and we also look at the energy in each of those peaks, so the energies of the single particles, which are those 3 points in our plot here. In the end, we get right now a total signal efficiency of 31%. But there's development ongoing to improve this. Right now, our 10-year sensitivity is 8.34 10 to the power of 33 years at 90% confidence level, which is an improvement comparing to the Super Kamiokande experiment. Now I'm talking a little bit about what I'm doing for the proton decay search. As I already said, it's very important to know the kaon signal very well. The last cut I was talking about was the height of one of the peaks, so the energy imposed by one of the particles. In case of the kaon, the energy which we measure as distributed in light in the detector is related to the energy deposited as a specific energy loss by the Burke's formula, which you can see here. Here, the quenching factor, Kb, is for the kaon right now only estimated in our simulations. Quenching means the amount of deposited energy in the liquid scintillator which is not converted into light. Therefore, as we rely strongly on detecting the kaon, we want to measure the quenching factor Kb in this formula, and then easier have a pulse shape discrimination between the particles, for example, and determine exactly the energy of the kaons. For this, we developed a detector concept, but we had a problem because kaon beams at that energy are more or less hard to get because the kaon decays so fast. So what we want to do now is we want to measure the Kb for particles with higher mass, so protons, and particles with lower mass, such as muons and pions, and then we want to extrapolate the Berg's curve for kaons. So what we do is we look at the kaon energy, which is 105 MeV, and look for where the other particles have the same dE/dx, so the same specific energy loss in the scintillator. This means about 200 MeV for the protons and 20 to 30 MeV for muons and pions. Then we build a setup and try to measure the quenching factor for those particles where they have the same specific energy loss. The setup for the protons looks like this. We have a setup with a first liquid scintillator detector and a second plastic scintillator detector for time of flight measurements. We have the proton beam coming into our scintillator cell filled with a Juno liquid scintillator, where it travels the whole distance dx and deposits a certain energy, which is then converted into a light yield, which we measure by the PMT. Then, with the remaining energy the protons have, they fly a certain amount of meters, and we can do time of flight measurements with a very fast plastic scintillator to detect which remaining energy the protons have after the setup. Overall, we can put together with our Berg's law that we have measured everything we need except for the quenching factor, and so we can calculate it from that. For this setup, we are right now discussing with the proton irradiation facility of the Paul Scherrer Institute in Switzerland when we can go there and put it there. For muons and pions, the situation is a little bit more difficult as they are at very low energies for our dx values we want to measure. So at a reasonably large liquid scintillator cell, they are fully stopped. Therefore, this is a simpler setup, but more complex because we cannot produce as much data points as we can for the protons, where we can vary, for example, the liquid scintillator size. So what we do is we measure the full stop, and the energy deposited is now overall just the beam energy. Here also we are talking to the Paul Scherrer Institute about using the secondary beam lines for the beams. Here you can see our current state on the setup. We have a liquid scintillator cell, which is made from acrylic glass and is right now in production in several sizes, with open windows, which we will enclose with mylar foil, because when the particle goes in and out, we don't want to have it to lose too much energy in the walls of the setup. So we have an ultra-thin foil, which we will glue probably on those cells. And then within the filled cell, the particles can traverse the cell without losing too much energy in walls. Here, for that, we do material compatibility tests of this foil with liquid scintillator, because we don't want the materials we use in our detector to change our properties of the LAB, and in the end, we see a different scintillation effect, and we cannot measure the factor as well. We also are working on simulations of the whole setup. Right now, only the light collection efficiency and also the detection efficiency. But in the end, overall, we will have the whole setup simulated to get what we expect to measure. And for an outlook, I can show you right now what the state of the building of Juno is, because as I said, it's built right now. Last week, we had the news that the steel structure, this is a picture which is a little bit 2 months, I think, away. But last week they finished the steel structure, and right now they're in shipping of the acrylic parts of the detector, and the PMTs are finished with measuring. So to conclude, I can say that Juno aims to exceed Super-Kamiokandis' limit on the proton decay channel within 10 years of data taken, maybe faster, and that the kaon's quenching factor is crucial for measuring all of this, and that further research is ongoing on the quenching factor and measurements, but also on the improved analysis methods. If you want further information on the proton decay search with Juno, you can have a look at the Juno Yellow Book with the physics prospects, and on a white paper searches for baryon number violation in neutrino experiment by Deff et al. Also, there's soon to be published a Juno collaboration paper on the Monte Carlo simulation of the proton decay. Thank you.
Is there a difference between the free and bound proton decay modes for the different decay modes, so either into the kaons or the pion and electron?
Mainly not. So mainly these energies do not influence the decay mode itself. And as we don't have detected yet any proton decay mode, we're just checking this one, but the predictions don't change if they're bound or not bound.
Okay. So which mode offers the greatest sensitivity?
Right now, the mode offering the greatest sensitivity is the one into the pion and the positron. But this is way easier to measure in water Cherenkov detectors.
No, I mean, if the free or the bound decay.
Of course, the free one, because we have very distinct kinetic energies. For the bound decay, we have a large variety of possible kaon energies, which smears our sensitivity.
Okay.
Hi, I think you were already halfway answering the question that I was going to ask, that what properties of a detector determines whether it's more sensitive to the kaon channel or the pion channel? Like, for example, the Kamiokandis only look, I guess, for the, the pion channels. Like, why don't they look at the kaon channels? I mean,
they looked at the kaon channels. They used this tagging technique on the excitation of a nitrogen if an oxygen proton decayed, but the kaon doesn't make any light in the Cherenkov detector, so it's completely invisible. So you only measure the decay products of the kaon, which are decay products of decay products. So what we see in Juno, we see the kaon itself because it scintillates. So that makes it easier for us to measure this channel.
But will you also do an analysis for the pion channel, which might be competitive with, let's say, hyper-Kamiokande expectations?
I think probably there's also analysis generation on this ongoing. But yeah, we are mainly focused on that, as the other one is studied very well by now. But there are also smaller decay channels, decay modes, which are also possible, which are not as largely predicted as the two ones. For example, the supergravity proposes a channel into pi plus and an anti-muon. Anti-neutrino, sorry, and an anti-neutrino. You can also try to look at that.
Okay, thank you.
Thank you. This was a nice talk. My question is a bit tangential to your talk in the sense that you were talking about looking at this channel because it's more preferred in the many supersymmetric models. Is there a simple way to see why this one is preferred over the other one, over the pion channel in the supersymmetric theories? And secondly, that must depend presumably on the scale for SUSY breaking. If the SUSY breaking is at the GOT scale, then it's presumably the same before one. So what is the exact thing and why this?
I'm sorry, I'm not completely prepared to answer this question as I have a very experimentalist view on that.
Yeah, this was not directly related to you. So
I guess you can find it.
Okay, I think there's another one.
Thank you for a nice talk. Because currently I'm interested in some God model that will have some contribution to the channel that produce anti-muon. So I'm curious about the current or the proposed bonds about the proton decay into pion or kaon and anti-muon.
Sorry, I don't get what your question is.
Yeah, because I remember you said you are working on some proton decay into pion and anti-muon.
Yeah.
And so do you have estimate like proton lifetime that can be reached?
That can be right now reached?
Yeah.
So, as I said, we want to go up to over 10 to the power of 34 years confidence limit for the kaon mode. The pion mode is harder because the pion is a particle which happens way more often in our liquid scintillator. We have way more backgrounds which can induce events which look like that. So I cannot right now, that's not much of a concern for Juno right now, because also this channel is the one which is way more proposed, and therefore right now our main focus.
That's positron about anti-muon, is it the same? Or?
This one? That's kaon anti, this one, the upper one.
Muon, the second generation.
So, sorry, which one?
I mean,
none
here.
of that.
None
of
here.
that.
It's pion and the second generation Lepton. No.
That are secondary, like not so much of a branching ratio getting events. I have right now no numbers for that, but you can try to have a look into the white paper I showed you, because there are several experiments, and I think some of them also discuss those channels. Juno doesn't.
Okay. Yeah. Thank you.
There are no further questions. We thank our speaker and we can move on.
The one before the direction. Oh, that's the one before. Sorry.
Okay, now we're having Andrea Serafini about the role of Juno in leptonic unitarity testing. Please go ahead.
Yeah. Good afternoon, everyone. I'm Andrea Serafini, and I'm a postdoc at the University of Padua. And today I will show on behalf of the Juno collaboration the role that Juno will have in the next decade in the testing leptonic unitarity. So let me start from introduction of Juno. I hope to provide some complementary information to the one presented in the previous slide. So the Jiangmeng Underground Neutrino Observatory is a 20 kiloton multipurpose underground liquid scintillator, which is currently under construction in the Guangdong province in the south of China. And Juno is situated at a baseline of nearly 53 kilometers from two nuclear power plants in Yangjiang and Taishan. This is because this is the baseline that maximizes the sensitivity of Juno to the neutrino mass hierarchy. And Juno will also have a satellite experiment, a satellite detector called TAO, Taishan Antineutrino Observatory, which will measure the unoscillated flux next to one of the Taishan cores. The detector is currently under construction and is situated underground under an overburden of nearly 650 meters, which provides a good shielding against cosmic radiation. So this is Juno detector, and compared to present state-of-the-art technology, it will be a huge step forward, as the main requirements for its main aim, which is the determination of the neutrino mass ordering, it should have a high statistic, and this is why the active mass is huge, because it consists of 20 kilotons liquid scintillator containing an acrylic sphere, and this is one order of magnitude compared to present state-of-the-art technology. And also, it is required to have a high energy resolution, which should be lower than 3% at 1 MeV. And because of that, it is required to have a photo coverage higher than 75%. Also, all energy scale systematics are required to be below 1%, and because of that, Juno features a dual calorimetry system based on 70,000 large PMTs of 20 inches and a complementary calorimetry system based on these small PMTs, which provide a linear reference in order to correct for the nonlinearities of the large ones. So the main detection process of Juno is the inverse beta decay, which is a detection channel which is sensitive only to electron antineutrinos. In this detection process, the electron antineutrinos produced in the nuclear reaction in the nuclear core collides with the proton, producing in a final state a positron, which readily annihilates, producing two back-to-back gammas, representing a prompt signal. And then a neutron, which thermalizes and gets captured by a proton, producing a really distinct 2.2 MeV gamma. And the time and the space coincidence correlation between these prompt and delayed events is a strong handle against most of the backgrounds that we have. And so it is a really strong signature for the detection of these events. But again, I want just to stress that in this detection process, we are sensitive only to electron flavor antineutrinos. So, besides these reactor antineutrinos, Juno can detect also neutrinos and antineutrinos from several other sources. So, for example, atmospheric neutrinos, solar neutrinos, neutrinos and antineutrinos coming from supernova bursts, or also geoneutrinos, the antineutrinos coming from the balls of the Earth. So, if, in the case of the Sun supernova and the Earth, the neutrinos can be used as a probe in order to investigate the inner parts of these celestial bodies, today I'm most interested in these sources in which neutrinos are used as a probe to investigate the neutrino properties and oscillation, and in particular the antineutrinos coming from the reactors. So just a quick recap of neutrino oscillation. As you may know better than me, neutrino oscillates, and this is because there is no correspondence between the mass eigenstates and the flavor eigenstates. And this non-correspondence causes the flavor of neutrinos and antineutrinos to oscillate during the propagation. And the phase of this oscillation depends on the splitting between the mass eigenstates. Okay, there is a matrix that connects these mass and flavor eigenstates. It is, okay, and this is the Pontecorvo-Maki-Nakagawa-Sakata mixing matrix, which it is presumably unitary, and indeed in most of the parameterization is treated as a unitary matrix, but it is not guaranteed to be unitary. In order to test the unitarity of this matrix, this can be tested in a direct and indirect way, but in order to test it, we have at our disposal 12 different equations. But the most promising and the most easiest to measure with oscillation physics is the electron row unitarity, which means to measure and demonstrate the unitarity of the first row of this matrix. So, as I told you, the precision measurement of the neutrino mixing parameter is a powerful tool in order to test the unitarity of this matrix through the electron row unitarity. And since we have three different unknowns that are the three elements of the first row, we must require three independent constraints in order to test this unitarity. The first constraint comes from solar experiment, and in particular the SNO and the super K measurement help to constrain this term, which in the case of unitarity is related to this mixing parameter, and they managed to constrain this matrix term at 5% level. Then we have another piece of information coming from reactor experiments, and in particular from Dandoy, which provided a really strong constraint at 3% on the theta 1,3, and so to this matrix element. And finally, we have Juno, which will be sensitive to this term, which is proportionally mainly to theta 1,2, and that will be constrained with a precision better than 1%. And this is because in the minimal unitarity violation scheme, we can write the survival probability of electron flavor antineutrino in this way. And as you can see here, we have this term that we managed to constrain. So you may also notice that this term is exactly what measured by Dandoy. So we are sensitive to the same term, but the precision that we will reach will be of the order of 10%, and so worse than the current constraint given by Dandoy. So Juno has the main physics aim at determining the neutrino mass ordering, which is expected to be determined at with a significance of 3 sigma in 6 years of data taking. But it will also expect it to be the first experiment to simultaneously observe in the same spectrum both the fast and slow oscillation of these neutrinos. So 4 of these 6 different mixing parameters, the 2 mass splitting, the solar parameters and the atmospheric parameters. And in particular, for 3 of these 4 parameters to which we are sensitive, we will place a precision better than 1%. Here you can see a breakdown of the survival probability of these electron-favorable antineutrinos. And you can recognize the slow term, which rules the slow oscillation of the spectrum, and the fast term, depending on the atmospheric parameters, which basically rules this fast oscillation. In the figure here on the right, you can see, you can get a general understanding of the impact that these parameters have on the oscillation pattern. So the 2 mass splitting rules the period of the oscillation, while the 2 mixing angles, θ12 and θ13, regulate the amplitude of this oscillation. And this will be important when understanding the impact of systematics on our measurement. I also want to point out that the probability, the oscillation probability, does not depend on the CP violation phase, and also in θ23, and this means that for one side, we cannot measure this parameter, but at the same time, we are not sensitive to bias introduced by unknowns in this parameter, which are 2 of the less known parameters in the mixing, among the mixing parameters of neutrinos. So here you can see a projection of the precision that we will get for these 4 parameters to which we are sensitive as a function of the Juno data taking time. And as you can see, in less than 2 years, Juno is expected to improve the precision of 3 of these parameters to a precision better than 1%, which here is represented by this horizontal dashed line. And in 6 years, we will reach a precision of 0.5, 0.3, and 0.2% on these 3 parameters, which is basically a precision much higher than current state of the art, and also with respect to the constraint given by global fits. And in particular, the precision of θ12 will permit to constrain the unitarity of the PMNS, in particular of the first row at a 2% level when combined with the constraint given by solar experiments and reactor 1. But could also help in narrow down the parameter space for the neutrino double beta effective mass, which in the case of inverted hierarchy depends on the 2 mixing angle and 1 mass splitting, and also constrain the neutrino pass-up rule. So what are the challenges to the measurement of θ12? Well, here on the right you can see a breakdown on the impact of different systematics on our measurement. And besides statistics, of course, you can see that the systematics having the highest impact, the biggest impact, are the reactor correlated uncertainties and the detection efficiency. These are how to say, these are the parameters related to the rate and normalization of the spectrum, because as I told you before, θ12 is exactly the parameters which rules the amplitude of the oscillation. It makes sense that these 2 parameters, which of course modify the overall rate and normalization of the spectrum, have one of the highest impact on the measurement of θ12. And then we have backgrounds, which in which case we have some irreducible backgrounds. So, for example, the antineutrinos coming from G neutrinos, but we have also accidental background, lithium-helium, or in general cosmological background, which we can measure and constrain with independent measurement by looking at uncorrelated signals. So, just as a final remark, Juno will inaugurate an high precision era in the neutrino oscillation field. And besides the determination of the neutrino mass hierarchy in 6 years, Juno will enable a sub-percent precision on these 3 parameters. And in particular, the sub-percent precision on θ12 will help in providing another constraint to directly test the leptonic unitarity via the electron row unitarity. And together with solar reactor constraint, is expected to constrain it at a rough estimate of 2.5%. So since its first approval of the experiment in 2013, Juno has come a long way. The civil construction which started in 2015 ended at the end of last year, at the beginning of 2022. And now the detector construction started. Here you can see a picture of 2 weeks ago, I think, in which the steel structure has already been completed. And the detector construction is expected to end in 2023. And so that's when we expect to start collecting data, and we will see what we will measure. So thank you.
Any questions, comments? So when will we know for sure the neutrino mass hierarchies? You said you will know it at 3 sigma?
Yeah.
Oh, sorry. Yeah. Do you have any idea of when we will know for sure?
Now, projection expectation seems to suggest that we will measure it with the 3 for sigma significance in 6 years.
Okay.
And yeah, we'll see, because Juno is a peculiar experiment in which statistics and systematics uncertainty are more or less balanced. So also statistics have a huge impact beside the systematics have a huge impact besides statistics. So.
Okay, thanks. Any other question? If not, then we thank our speaker again and move on. Yeah, so speaker schedule for right now is not here.
Oh, I thought it was me.
No. So, that's me. In that.
Okay, yeah.
No, but the other one.
Yeah, the other one, the previous one.
For the one.
Yeah.
Oh, that's what I mean.
So I'll go. Yeah.
So we just
Great.
go ahead with Ioannina, who will tell us about explaining Lepton flavor non-universality and self-interacting dark matter with L mu minus L term.
Great, yeah, thanks for having me. Is this one? Both, all right. So this is a change of topic, really. It was already introduced this morning, but it bears repeating that the magnetic moment of the muon has been off for almost 20 years now, as first measured by Brookhaven, with a very unparalleled precision at the time. It differed by 3 to 3.5 sigma at the time from the standard model prediction, and because of that they moved the entire experiment to Fermilab to repeat the experiment, make improvements, and collect more statistics. And indeed they are doing that, and last year they finally released their first data run footage, which is kind of on par with Brookhaven's original precision, and it agrees with the Brookhaven result. And in the meantime, we've also recalculated the standard model prediction, and it turns out the difference is still there, and it's roughly at the 4.2 sigma level between experiment and theory. So the anomalous magnetic moment is anomalous, which is good for people like me who do model building and look for new physics. But it might be too early to be too excited, because it turns out in this case you don't have any reason to mistrust the experiments. But on the theory side, there are huge uncertainties in the contribution of hadrons to the standard model prediction. And lattice QCD people are still trying to figure out what the actual value of the vacuum polarization of the photon and the photon scattering contributions are. And it seems they still haven't really converged on one value. So there's still work that needs to be done. But hopefully in a couple of years we know for sure whether this is new physics or not. All right, I will take it as new physics and assume that this is the value that we need to explain, which means we need to add something to the theoretical side of this calculation, and since this is a loop process, we need to put new particles in the loop. There's no shortage of particles that you can do that with. Arguably the simplest one is to do what Schwinger did and calculate the contribution with a new vector boson. Obviously it needs to be new, because otherwise it would be part of the standard model prediction already. So a new vector boson coupled to muons like this, you can immediately calculate what kind of fine structure constant you need to explain the deviation, and you find that it doesn't work if this particle is massless, because it would contribute to too much radiation in the early universe. By now, we know enough about the early universe that you can't just put an extra degree of freedom in there, even if it only couples to muons with this kind of weak coupling that would explain the difference here. So it needs to be heavy, heavier than like 10 MeV to suppress these cosmological things. And even then, you're not in the clear necessarily. It all depends on what else this Z prime couples to. You cannot just couple the Z prime to the charged muons, because that would break SU2 invariance. It needs to at least couple to muon neutrinos, because they sit in a doublet. And even coupling to this muon current with the neutrinos in there isn't anomaly free, so you need to couple to something else in addition to cancel the anomalies, to make this a renormalizable model. So in order to figure out what is allowed to explain the muon magnetic moment with a new vector boson, you need to decide what else it couples to. And it turns out by now there aren't that many things it's allowed to couple to that you can do. First thing you can try is to couple it to electric charge or something like that, or B minus L, where you have a coupling to muons that is roughly as large as that to electrons. And that doesn't work anymore. This used to work 7 years ago, but since then we've learned enough about the electron coupling to exclude this preferred region for the G minus 2 anomaly. This is the kind of gauge coupling versus the gauge boson mass, and you want it to live in this black region. It's all excluded by other things now. And it's all excluded by the electron coupling of this vector boson. So what you need to do is suppress the electron coupling compared to the muon coupling if you want to explain G minus 2. That is possible, but it leads to another constraint that is a little bit more surprising. If you suppress the electron coupling, or let's just say we set it to 0, that also means you don't couple to electron neutrinos anymore, but you still couple to muon neutrinos. And that means neutrinos going through matter will interact differently with matter depending on what flavor they have. Electron neutrinos would not see this kind of force, but muon neutrinos would if this new Z prime also coupled to quarks. We already turned off the coupling to electrons, but it could still couple to quarks. And again, a couple of years ago this would have been fine, but by now we know enough about neutrino oscillations in matter to exclude the relevant region for G minus 2. Any model that couples to just muons and not electrons, and in addition to quarks, for example, to cancel these anomalies that you need in the model, would lead to non-standard neutrino interactions that completely exclude the region that you need for G minus 2. So by turning off the electron coupling, which we needed to do to live in the G minus 2 band, we are also forced to turn off the quark coupling, because otherwise neutrino oscillations exclude the entire thing. And that leaves only one thing you can do. You can couple to L mu minus L tau. This is the only anomaly-free combination of charges that you still have that doesn't violate all these constraints from neutrinos and from electron experiments. The tau uncoupling here is just needed there to cancel the anomalies, and since we don't know much about tauons, it doesn't really add any constraints. So this is a safe combination of charges. This was pointed out already a long, long time ago, 20 years ago, even 30 years ago, this model was proposed, L mu minus L tau, as Yontaro already introduced. By now, even that model, that looks so weakly constrained because you don't couple to any first-generation particles, even that model is now tightly constrained and pushed in a corner. As I said, on the left-hand side, if the Z prime mass is too light, you run into cosmology constraint. You want to live in the green band to explain G minus 2, and as you can see, everything above like 200 MeV is excluded by other experiments. Notably, neutrino trident production, this black line here, kills everything above like a couple of 100 MeV. And this comes from a constraint that was pointed out by Maxim Pospelov and others, where you scatter neutrinos on muons that you make in between the nucleons and the neutrinos. So this, even though there's not much statistics on this, is enough to exclude this entire region here. So you are forced to live in this small region between 10 and 200 MeV. Luckily, even though this is a very difficult to constrain region, since it is the last Z prime that could explain the G minus 2 anomaly, experimentalists have started to pay attention to this and have proposed many ways to test this region. And indeed, it will be tested at Bell 2, at Dune, at NA62. Now we learned that Muon E can also look at this. So Sooner or later, we will learn whether or not the Z prime of L mu minus L tau actually explains the G minus 2 anomaly. Notice that this is a difficult parameter region because below 200 MeV, the Z prime doesn't decay into muons anymore because it's not heavy enough. So it only decays into neutrinos, and that makes it very difficult to see. You only produce it from muons, which is already difficult, and then it only decays invisibly, which is doubly difficult. So it's all the more impressive that we're actually going to cover this region in the near future. All right, this is the last Z prime that can explain the G minus 2, and it is pushed into this corner here, where the Z prime decays invisibly, and you know pretty well what the mass and coupling range is. Let's assume that this is true. It looks like a weird symmetry. What else could it do? Is there any other reason why people should consider this symmetry? Or if we actually see it there, what else could it be connected to? And the most basic thing that L mu minus L tau does is it induces lepton flavor non-universality. Clearly, muons, electrons, and tauons interact differently now because they have different charges under this gauge symmetry. And as it happens, there are some anomalies in addition to G minus 2 that go by the name of lepton flavor non-universality. And these were already introduced this morning, but let me briefly remind you. One of these comes in B decays into kaons and 2 leptons. In the standard model, this arises at one loop like this, and you expect the ratio of these two couplings, these two branching ratios, to be of order 1, because in the standard model, the difference in masses here is completely irrelevant compared to the large B meson mass, and the couplings are gauge couplings, so they are the same. So in the standard model, you expect the same rate into muons and electrons. What LHCb sees is below 1, and significantly at the 2.5 to 3 sigma level. By itself, that would be interesting, but not spectacular. Interesting because even though this is a low sigma significance, this is a fairly clean observable, so you should pay attention to that. More importantly, if you do a fit to all B to S mu mu data, it turns out these things add up, and there are other anomalies in the, for example, angular distribution of these leptons that also add up in this direction. So doing a global fit to B to S data, you find that the standard model is disfavored, and you can increase the fit significantly by adding just one operator. For example, this one that has an S to B transition with a left-handed current and a left-handed muon current here, and since it's a dimension 6 operator, it needs to be suppressed by 2 powers of energy scale, and the right coefficient is roughly 35 TeV squared. This one operator is preferred at like 6 sigma, maybe even more depending on who you ask and what fit you look at. But this is an operator that is highly preferred by data. How do we get that operator? At tree level, there are 2 options. One is with a Z prime that couples to BS and to 2 muons, and the other one is with a leptoquark. Now, a Z prime coupling to muons sounds like this is ideal for L mu minus L tau, but it turns out you need this Z prime here to be heavier than 200 MeV if you wanted to explain these B meson anomalies. So I'm not going to go down this route because I want to keep the Z prime explanation to the muon magnetic moment. So let's look at leptoquarks, which have suddenly become everyone's favorite solution to all these B meson anomalies. And specifically, there's only one leptoquark that can actually do this at tree level, and that is the S3 leptoquark. I don't have enough room on this slide to cite everyone who worked on this, unfortunately, but this is a recent overview where they go into detail about this. So the S3 leptoquarks is the triplet under color, a triplet under SU2, and some hypercharge. It has this Lagrangian, which has indeed the leptoquark coupling, so a coupling to leptons and quarks. This is what you want. But due to the quantum numbers, you also have this diquark coupling, and that is terrible, because these two together induce proton decay. And that would be great for Ulrika over there, but as a model builder, that means this is bad, because I either need to push the S3 mass here to the gut scale to get rid of this, to satisfy the constraints, or, because I can't do that, I want this thing to be at the 35 TeV scale, I need to make these diquark couplings tiny, like 10 to the minus 18 tiny, to evade all these proton decays. That doesn't look too good. In addition, once I've done that, I also have to deal with lepton flavor violation just through these terms, but that is less of an issue. Still an issue, but not as bad as proton decay. And this is where L mu minus L tau can actually come in to help you. Let's charge this S3 leptoquark under muon number. Let's give this a muon number 1 that immediately forbids this diquark coupling. And in the leptoquark coupling, it forces the S3 to only couple to the muon doublet, not to electrons, not to tauons. And because of this, you automatically evade proton decay, it's just set to 0, and you don't have any lepton flavor violation anymore, because you only couple to muons. So that is enough to kill lepton flavor violation. The only thing that survives is the coupling of quarks to muons, which is exactly this process that you need for RK and RK star. So the only surviving things are exactly the ones that you want. You've eliminated all the things that you didn't like. And that's why a leptoquark charged under an L mu minus L tau symmetry actually works very well. It just strips away all the things that you don't want. All right, this is one of the B meson anomalies that hint at lepton flavor non-universality. There's another one also in B mesons in the charged lepton channel. B meson decays into Ds and taus relative to those into electrons and muons. Here, the ratio is not predicted to be 1 because the tau is so heavy that you feel the phase space effect, but still we can calculate the ratio here in the standard model very accurately because in this ratio many uncertainties fall out, so we know what this is. Experiments have measured both RD and RD star. This cross here is the standard model prediction. The red is the experimental average, and as you can see, it deviates at the level of 3 and a bit sigma. So again, significant enough for such a clean observable to pay attention to this. And in this case, what you need as an operator is something that changes a B quark into a C quark, and then something with tauons. Now the suppression is only 3 TeV that you need, because this is a process that happens at tree level in the standard model, so you don't need to compete with loops. That makes it a lot more difficult to get away with this, because 3 TeV isn't that high anymore in the LHC era. And again, the most prominent solution to this, the way to get this operator, is again leptoquarks. Either S1 or R2 do this at tree level, so this can work. But these have the same problem that the S3 leptoquark had for the RK star resolution. You again have basically the same Lagrangian. You have a coupling to quarks and lepton that you want, and you have a diquark coupling that you don't want. And we can do the exact same thing here. We take this S1 leptoquark and we give it tau number. Since we are now working with taus, we give it tau number. This forbids the diquark coupling and forces the S1 only to couple to taus, which is what you want. The only thing left over after you got rid of proton decay and lepton flavor violation is the diagram that explains RD and RD star. So we can do all of these things with L mu minus L tau, because it couples to muons and tauons. This weird combination of charges that we need, that we are forced to use for the G-2 anomaly, is actually ideal to also explain these B meson anomalies, because they happen to be in the muon and in the tauon channel. Weird coincidence that is kind of ideal for L mu minus L tau. All right, so we have explained the G-2 anomaly with the light Z prime, the RD and the RK anomalies with 2 leptoquarks charged under the symmetry. What else can we do? Everyone on HEP-PH will know that once you have a new particle, you try to make it dark matter. That doesn't work here because the Z prime just decays into neutrinos immediately. The leptoquarks are leptoquarks. They're not good dark matter. But at least we can make them mediators to dark matter, right? That always works. And the leptoquarks are not as interesting as a mediator to dark matter, but the Z prime turns out to be very interesting. I'm not the first one to point this out. People have studied L mu minus L tau charged dark matter for a long time. What this gains you, when you charge a new particle under this U1 gauge symmetry, you immediately have it stable, unless you pick the charge very, very badly. You have a stable particle that interacts with the standard model through the Z prime mediator. Since it's a U1 symmetry that stabilizes it, you could also have an asymmetry, and everything is just standard, like freeze out works very well. Since you don't couple to first generation particles, this dark matter doesn't have any direct detection constraints. Very good. As it happens, it actually does have some impact on neutron stars, which you can read about here, which I don't have time to explain, but that doesn't yet give any constraints. Since our Z prime mediator is light to explain G-2 between 10 MeV and 200 MeV, the dominant annihilation channel is dark matter into Z prime, and then the Z prime goes into neutrinos. That is a very bad indirect detection signal, so you don't get any constraints from that either. What you do get, what is good, is that the Z prime induces dark matter self-interactions. And since it's light, it actually induces very velocity-dependent self-interactions. And they can be used to resolve small-scale structure problems, like the core versus cusp problem. As has been pointed out a long time ago, this is a busy plot showing the self-interaction cross-section of dark matter as a function of the velocity. You want to live at small velocities on dwarf scales in this region. You want self-interaction cross-sections around 1 centimeter squared per gram. But at larger scales, at cluster scales, or at higher velocities, you want suppressed self-interaction cross-sections, roughly an order of magnitude less. And this is the kind of velocity dependence that you get in this model if the Z prime is light. This has been pointed out a long time ago, but as it happens, in most models where you do this, the Z prime gives you additional constraints from the CMB, etc., because in most models the Z prime couples to electrons or quarks or other things that you don't want to touch. In this case, for L mu minus L tau, you don't have to worry about any of these things. CMB is not affected because the Z prime only goes to neutrinos and you're safe. You can easily get these cross-sections, centimeters squared per gram on dwarf scales from this model. And this is a plot that shows this. This is the dark matter mass as a function of the Z prime mass here. You want to live in any of these colored bands. So sorry, everything below here, the black region is excluded by an effective, the cosmology bound that I said. But then you want to live in any of these colored regions. These are for scalars and fermionic dark matter, both symmetric and asymmetric. So one of these things is where you want to live. You get the right relic density and you get the right self-interaction cross-sections in this region. And as you can see, you're not allowed to make the Z prime mass arbitrarily heavy. In order to get this right velocity dependence, you need to have the Z prime light. And if you look at the numbers, you basically need it to be exactly in this G-2 preferred range. It needs to be between 10 MeV and a couple of hundred MeV. This is preferred by self-interacting dark matter constraints and happens to be the region where you can explain G-2. Completely unrelated, completely pointing in the same region of parameter space. And that brings me to my summary slide. L mu minus L tau, as weird as it sounds, is actually a very nice model to explain many things at once. You gauge it, and you don't need to add anything to the standard model to promote it to a gauge symmetry. This is the only symmetry, the only global symmetry of the standard model that you can just make a gauge symmetry. You don't need to cancel any anomalies anymore. You don't need to add more particles. It's just gauged. You do need to break it in the neutrino sector to get the right oscillation angles, but that is easy and doesn't introduce any additional constraints on what I talked about. To explain RD and RK, we add leptoquarks that we charge under this symmetry in such a way that we automatically eliminate proton decay and lepton flavor violation and only live within the parameter space that we want to live in for RD and RK. The Z prime itself, if it's light, can explain G-2, very good. And as it happens, you can add new particles that make it stable, dark matter, you get the right relic abundance, and this light Z prime introduces velocity-dependent self-interactions that perfectly resolve small-scale structure issues. All of this could be done individually with other gauge symmetries and other models, but only L mu minus L tau can do all of these things at the same time. So that makes it an interesting model to consider, and more importantly, we will in the next couple of years learn whether or not the Z prime explains G-2. So in a couple of years, either no one will be talking about L mu minus L tau, or everyone will be talking about it. So I thank you for your attention, and I'm happy to answer questions.
How does this explanation of the Hubble constant problem work?
Very good question. I didn't have time to talk about that. The constraint that I showed here from n effective comes from the, it's ineffective. It turns out to explain the Hubble tension, a little bit of ineffective can help you. So ineffective favored, this H0 favored region is exactly where you get a little bit of ineffective, just enough to ameliorate the Hubble tension. It's not a perfect explanation by any means, but it helps resolve this Hubble tension a little bit. So then you want to live at this 10 MeV band for the Z prime mass, which perfectly works with everything else.
Hi, I have a slight tangential question. So in one of your slides, you showed your paper, that dimension 9 paper, right? Dimension 9 proton decay paper in context of one of the anomalies.
I did not. I don't have a slide on that.
No, you referred that paper somewhere.
Did I? Oh yeah.
So these are dimension 9. If I remember the paper only, these are dimension operators. So you have like 6 workers, right?
Yes. All right. So. Yeah, I do understand the question. So the reason why I'm citing my paper here is that in that paper we had also introduced a flavor U1 symmetry, not this one, but a slightly different one, to get rid of the dimension 6 proton decay operators that this leptoquark would induce. But we added other leptoquarks to allow for the generation of a dimension 9 proton decay operator and a dimension 10 operator. Which then gives you completely different proton decay modes that are a little bit less severe and could still be visible even though you're explaining RK and RK star. If you don't add this extra leptoquark, then you don't get these proton decay operators. So in this context, adding this gauge symmetry on top of the S3 just completely gets rid of all proton decay operators. You could also get other proton decay operators beyond dimension 6, which is what this paper was about, but it doesn't happen automatically in this model.
So my confusion was that I just remember the operators there, the dimension 9 operators that you had tabulated. So you're saying the leptoquark, if I compute those operators, then those leptoquarks will sort of help in explaining RK and RK.
So for the dimension 9 or 10 operators, you need more than one leptoquark. One of them could be this one. But you need that other one to actually get that operator, which you can do, but you don't need to do. So here, I didn't add that leptoquark, because here I'm not talking about proton decay. Different talk, I would talk about that.
Thank you.
So could you go back to the slide where you talk about sevens, the coherent constraint? So is that it? No.
This one?
Yeah, right there. So there you claim that this excludes using B minus 3L mu. So can't you do the same but just make it coupled to, let's say, third generation quark families instead of just baryon? Because in that case, I think that you would be able to avoid that.
That's right, then you would avoid this constraint. The problem is if you don't couple to B but to individual quark generations, it's going to be much more difficult to get the right CKM mixing out of it. So it's a messy way to do it, and that's why I didn't include it here. You can do that, other people have done that. It's just a lot more work that I wasn't willing to get into here.
I see.
The simple gauge symmetries, like just coupling to the global symmetries of the standard model, only Muon tau works. If you go beyond that, if you're willing to generate CKM mixing angles from U1 symmetry breaking, then you can go to a much larger class of U1 symmetries.
So this has led me to another question. So what about the PMNS mixing here? Do you have any problem with that?
Right. As I said, we need to break the symmetry because we know from neutrino oscillations that Muon tau is broken. We've seen muon neutrinos convert into tau neutrinos, etc. But we can easily break this just in the right-handed neutrino sector, in which case the symmetry breaking doesn't affect anything else. It doesn't lead to any Lepton flavor violation or anything, and it still propagates via seesaw just to the left-handed neutrino mass matrix, and you get the right mixing angles. It doesn't complicate anything. It's basically the standard seesaw. It's very easy to do.
I see. Thank you very much.
Okay, now we have quoted Friede, who will tell us about the phenomenology of LNV and SMEP at dimension 7.
Yeah, so I will talk about Lepton number violation in 7-dimensional operators in the standard model effective field theory, and this is based on work that will be put on the archive soon, which is done in collaboration with Lucas Graf, Julia Hartz, and Shannon Hattie. So we all know that the standard model is not cannot be the complete. cannot be the complete description of nature. Two reasons that it cannot be are the baryon asymmetry, which we know is there from the cosmic microwave background and Big Bang nucleosynthesis, and then we also know that we have neutrino masses, which we know from the oscillations. And one phenomena that can be connected to both of these hints for new physics is lepton number violation. So the neutrinos can only have a mass in two different ways. So either they're Dirac particles, in which case they have a very small Yukawa coupling in comparison to the other particle fermions we know of order 10 to the minus 12, or they could be Majorana particles. And if they are Majorana, that implies that lepton number is not a conserved symmetry in nature. And if lepton number is not conserved, in the early universe, we could have lepton number violating interactions that could actually lead to a baryon asymmetry via the svalerons. So svalerons are baryon number and lepton number violating processes that are part of the Standard model, and they are very active in the early universe. So whatever mechanism that could generate the Majorana masses can induce a lepton number asymmetry, which the svalerons then make into a baryon number asymmetry, and that could explain the baryon symmetry of the universe. So any source of lepton number violation can give neutrino masses, and therefore the baryon asymmetry. So what we want to ask is if we can model independently study lepton number violation to simultaneously constrain a wide range of models to do this. And one framework that is often used is then the Standard model effective field theory, where we simply we have a Lagrangian with a series of operators with Wilson coefficients that contain all the new physics that we're ignorant about. And when studying lepton number violation, we only expand the Standard model Lagrangian with odd mass dimension operators, because lepton number violation only appears at odd mass dimensions. So we have a single operator at dimension 5, which looks like this. So you have two leptons and two Higgs doublets, which gives I'm showing the neutrino mass diagram here. And at tree level, you can only UV complete this operator in 3 different ways, and those are, of course, the 3 seesaw types. So either you have a heavy neutrino, or this new scalar, or a triplet fermion. And those are all the tree-level UV completions. So we can also ask if there are more complicated ways to get lepton number violation, and the next simplest step is simply to go up 1 dimension and look at 7-dimensional operators. So this is what we wanted to do. And when you go just 1 step up in the dimension, instead of having 1 operator, you have 12 operators. So it immediately becomes a lot more complicated. There are operators now with covariant derivatives and field strengths. And you have many operators that contain 4 fermion fields instead of 2. And this setup is then phenomenologically very rich compared to the 1-dimension 5 operator, because you have there are 26 different UV complete fields or UV fields that appear in tree-level UV completions instead of the 3 of the Weinberg operator, and they can combine in 56 different ways to generate all of these operators. And they also lead to neutrino masses. For example, here, if you have operators with 4 fermions, 2 of the fermions are the lepton doublets, and the other 2 fermions you can close in a loop to generate a radiative neutrino mass. And this extra loop suppresses the neutrino mass, which could explain why the neutrino mass is so low. So there are lots of operators, and we can then ask ourselves how we can see these experimentally. And to do that, there are many different search strategies. So perhaps the most famous one is neutrinoless double beta decay, which is also the most sensitive probe. And at dimension 7, lepton number violation, you have these what's called long-range contributions, where all the lepton number violation happens in one side of your diagram, so in one of the neutrons, and it talks to the other neutron via this neutrino, and the whole thing induces neutrinoless double beta decay. And it's a very sensitive probe, but it's only sensitive to the electron-flavored part of the operator, so it's still interesting to look at other probes also. And the currently most stringent limits on this neutrinoless double beta decay half-life was updated this year, by the Kamlan-Sen collaboration. So this red line here is where they're currently constraining, and on the y-axis you have the effective Majorana mass of the neutrino in the electron flavor, and they are currently constraining it down to below 50 milli-electron volts, so that's quite low. But like I said, this is only for the electron-flavored part of the dimension 7 operators. So we can also look at probes that constrain the muon flavor. There we have these lepton number violating muon decays, where you have a muon into an or a positron and 2 antineutrinos. And there have to be antineutrinos in order for this to violate lepton number. This now includes the mu flavor, but we're at dimension 7, we're only sensitive to a single operator, because there's only a single dimension 7 operator that contains 4 lepton fields like this. And the most stringent constraint comes from the Kalman collaboration in 2003 on the branching ratio, which has to be less than 10 to the minus 3. There's also mu minus to E plus conversion. So I think a more popular probe to look at is mu minus to E minus conversion, or mu plus to E plus conversion. But there's, in this experiment that look for this flavor violating muon to electron conversion, you can also look at the lepton number violating conversion by then converting 2 up-type quarks into 2 down-type quarks. However, because you have now 6 fermions, this operator is at dimension 9, and the corresponding constraints on dimension 7 operators is quite low. Yeah, so the currently most tight constraint on this ratio between the conversion into positron and the conversion into a muon neutrino is less than 10 to the minus 12, so that's quite a severe constraint. What you can also look at are these meson decays. So I'm taking kaons here as an example, but you can also look at lepton number violating B meson decays and D meson decays and so on. So I'm showing here 2 different probes. On the left, we have kaons decaying into a pi minus and 2 same sign charged leptons. So this obviously violates lepton number because you're creating 2 leptons. However, if you count the fermions, this is again a dimension 9 operator. But what's good about this meson decay in comparison to the one on the right is that here you have 2 leptons which you can observe actually experimentally in the final state. So you can also look at these rare meson decays where a kaon decays into a pion of the same charge as the kaon you had initially, and also 2 neutrinos. And this is lepton number violating if you have neutrino-neutrino. So there's a standard model mode that corresponds to this, where you have neutrino-antineutrino, which is of course not lepton number violating. And you cannot determine the flavor here of the neutrinos. So I said that the muon sector experiments constrain the muon part of the operator, but here you have no handle on the flavor part, so you must take them as a universal probe of any flavor content of the operator. And experimentally, the NA62 collaboration looks for both of these modes. So this purely BSM mode they have not found. They've constrained it to be the branching ratio to be less than 10 to the minus 11. This mode, however, there's a standard model mode, like I said, with neutrino-antineutrino, and they have found this very recently, close to the standard model expectation. However, the error bars are still quite large. And if there is also a lepton number violating mode, it could increase the observed branching ratio. So then what you observe should be the sum of the lepton number violating mode and the standard model mode. So because there is still a difference within the error bars of the expectation and the experiment, then there is room for lepton number violating here also. And precisely the difference between the standard model expectation and the observed mode is what sets the limit on the scale of new physics that's possible in these operators. Finally, you can also look for lepton number violation at the LHC. So I think the most famous way to do this is to look for this diagram, which is called the Kyung-Semyonowicz process, where 2 protons interact via a WR, and this WR decays via a right-handed neutrino into same sign dilepton plus dijet. So the whole process is two protons into 2 leptons of the same sign, either muons or electrons, and 2 jets. And at the Atlas, or the Atlas collaboration, are probing this kind of diagram for right-handed neutrino masses between 5 and 50 GeV for the then couplings above 10 to the minus 5. And recently there was a paper also suggesting another type of search where you have vector boson fusion of two same sign W bosons that interact via a neutrino exchange where you have insertion of the dimension 5 operator here in the neutrino, and that leads to the same type of signal as the Kuhn-Ioannina process. You have proton-proton into same sign dilepton plus dijet. And this then probes the dimension 5 operator. And the constraint they get on the muon flavor of this operator. So they can look for both electrons. So they can see both the electron-flavored and the muon-flavored part of this operator. And the muon-flavored part they constrain to be less than 10.8 GeV. And if you remember about the neutrino stable beta decay, they constrain that to less than 50 milli-electron volts. So that gives you an idea of how much more sensitive the neutrino stable beta decay is. Yet still this is then, because it's on the muon flavor, it's still a competitive probe of lepton annihilation. And this Kuhn-Ioannina process, if you integrate out all your fields in here, it becomes a dimension 9 operator. So it's not directly constrained by the dimension 7 operators. If you choose only to integrate out your WRs, then you're no longer in the standard model effective field theory because you have a light sterile neutrino. So it has to be studied in a different kind of formalism than what we used here. Now, so then there weren't any dedicated dimension 7 searches, or dimension 7 lepton number violation searches for the LHC. So therefore, that's what we decided to look at. And it turns out that out of the 12 operators you get at dimension 7, 9 of them can give you the same kind of signal that we had in the previous 2 searches. So you have proton-proton into same sign dilepton plus dijet. So as some, I can't show you all 9 operators here, so I'm showing you some examples. Here is one operator with that has a quark doublet and a singlet uptight quark. And via these 2 different topologies, it leads to this same sign dilepton plus dijet process. And also you have this one operator with 4 fermions and 1 covariant derivative, which can become a W, and by this diagram you get the same kind of process. And because it's the same signal, like proton-proton, same sign, proton-proton into same sign dilepton plus dijet, you can reduce the old searches to constrain the scale of new physics also in the dimension 7 operators. And to do this, we calculated the cross-sections for all these diagrams using MadGraph for some new physics scale, and then use the fact that they have not seen any events so far in the dedicated searches, and this puts a limit then on the scale of new physics that is possible. And it turns out that the scale of new physics that's constrained at 95% confidence level is, for the 4 fermion operators, it's around 0.7, 0.8 TeV. And for some of the operators, the constraint is lower. For one of the operators, the constraint is currently at above 2 TeV. And we also then looked at how would this situation improve at the FCC. And this you see here in the second column. So at the FCC, these 4 fermion operators would be probed at around 5 TeV, while this one operator you could probe at almost 30 TeV. And this offers then constraints both in the electron-flavored part and the muon-flavored part of the operators, as opposed to neutrino stable beta decay. And they all scale with the scale of new physics to the power 1/6. So they have, for every order of magnitude you change in your scale of lepton number violation, the cross-section increases by 6 orders of magnitude, so it's very sensitive to this scale. Now, the LHC is often good at looking at, or it's mostly used to look at UV models, so we also compared how would our EFT operator compare with some simplified model extension. So again, the same QU operator, you can see it in the solid line here, the effective constraint you would get. Comparing it to a simplified model with one mediator, we see that for the region of parameter space that we consider, we slightly underestimate the constraint for low masses, mediator masses, so you have mediator mass on the x-axis and the constraint on the y-axis. But then for high masses, we get exactly the same kind of result. And this is then choosing the mediator mass and couplings to match as close as we can with the scale of new physics. And the red region here we don't consider because in order to use an EFT setup, the momentum scales involved have to be lower than the mass that you consider. So we can't go as far down as we want in the mass. Then if we compare all the probes, we see that neutrino stable beta decay is still the most sensitive probes for most operators. It's the blue one here. And what we find is that the LHC actually offers the most sensitive constraints in the muon flavored part of these dimension 7 operators for many of them. For 2 of the operators, this is not true because they induce these rare K decays where you have 2 neutrinos in the final state. So there you're also sensitive to the muon flavored part. So for 2 operators, the rare K decays are the most sensitive probes for the muon flavored Wilson coefficients, but for many of the operators, the LHC is actually the most sensitive probe. So to conclude, we know that neutrino masses can be connected to leptogenesis via lepton number violation. And dimension 7 lepton number violation offers the second simplest solution to realize lepton number violation on an effective level. And what we find is that the most stringent muon sector constraints on these operators come from colliders. So thank you.
Thanks. Question?
So the standard in the standard picture, I guess one typically wants the neutrino mass itself to be dominated by dimension 5 operators. But suppose that coefficient happened to be 0 for some model reason, then there would be some dimension 7 contribution to the neutrino masses. So my question is there something interesting you can obtain about the dimension 7 operators in general that differs depending on where most of the neutrino mass itself comes from?
Yeah, so the number of UV completions of the dimension 7 operators far outweigh the dimension 5 operators, like you say. So if it happens that none of the CISA particles exist, it could be that the dimension 7 operators instead give the neutrino mass. So I have an example here of this operator that we looked at, the QU operator. If you just combine the different external fields in all possible ways, you get all the possible tree-level UV completions of this operator. And it turns out to be this list here. So you have actually the CISA particle appearing again, and then one that has the same quantum numbers as the Higgs, and okay, you have all 3 CISA particles actually, but then you have also these vector-like quarks and some leptoquarks and so on. And the way that you can combine these is in this table here. So the way you read this is that if you have the vector-like quark Q7 and the leptoquark U1, you generate topology 2, which is this one, and that's the topology you get for the neutrino mass. So you can make tables like this for all 12 of the operators, and then you get a complete list of all your possible UV completions. So if it then, all the fields you get in this way, if it happens that also none of these are realized in nature, then you could instead look to dimension 9, in which case you get a lot more operators and a lot more UV fields. So, yeah.
So in your table that you got the bounds,
yep.
let me understand. So, here you assume, I guess, the Wilson coefficients to be of order 1, right? So you.
Yeah. So
what do you mean by lambda is just a c equals 1, and then translate this to a bound.
Yeah. So in the EFT language, you of course have the c over lambda usually, where c. You can think of C as collecting all the couplings and lambda collecting all the masses. But what we take here is that C is 1. Yes.
Okay. So my question is, some of these operators have derivatives, no?
Yeah.
So you expect the scale, so you expect to have some unitarity violation at some point for those operators. They scale with the their cross section will scale like S. So I don't know if these unitarity bounds are better than these ones.
If they're lower than these ones, you mean?
Yes, if they're lower than these.
So I think we have not looked into that. Yeah, so I wouldn't be able to answer. Yeah.
Thank you for the nice talk. I have 2 questions. The first one, why you exactly focus on dimension 7, not, for example, from dimension 5 to dimension 8, all dimensions?
I mean, the lower the dimension of an operator, generally speaking, the more stringent any experimental constraint will be on the scale of new physics. And you can simply see that by which power the scale appears in your Lagrangian. So the cross section of some process is what will set the experimental constraints, generally speaking. And the cross section is proportional to the square of its terms that appear in the Lagrangian. And if you square the first term, your cross section is proportional to 1 over lambda squared. So any experimental constraint you will have to take the square root of that in order to get this constraint on the lambda. And for dimension 7, you will have to take the power 1 over 6 between the cross section and the scale. So generally speaking, the higher you go in the dimension, the less sensitive your experiments will be to the scale of new physics. So that's why, because there has been so much literature on the 5-dimensional operator, we chose to look at the second simplest step.
Thank you. The other question is, I imagine that the LHC puts constraints on the Wilson coefficients at high energy, right?
At high energy, yeah.
Okay, so I think you should, I would expect to see some running from high scale to low scale. So you use the evolution matrix, which is which relates to the high scale to the low scale, and the running of RGEs of Wilson coefficients, right?
So there are different runnings here. You can either, so standard model effective field theory is only defined above the electric symmetry breaking scale because you're using the full standard model symmetry. And if you run from the scale at the LHC down to this scale, the running is very, very small. So we have looked into it and confirmed that the running is extremely small, such that we can neglect it. But then when you want to compare the LHC to low-scale probes like neutrinoless double beta decay, for example, then you also have QCD running on in the low-energy effective field theory, and that can affect things. And so we take that running into account, but not the running of the dimension 7 Smith operators.
Okay, thank you so much.
Yeah.
Okay, thanks a lot.
Thank you.
Let's move on to our last speaker. So the last speaker for today is Merlin Reichert, who tells about the anapole moment of Majorano fermions and implications for direct detection of neutralino dark matter.
Okay, hi. Okay, so I'm going to present a work which has been done in collaboration with my supervisor Alejandro Ibarra and a collaborator Rio Nagai. So okay, as one part of this long title suggested, or suggests, dark matter is relevant. That's why I will briefly talk about dark matter. And that's actually where we got this idea for this whole work. Then I will briefly talk about, I will talk about the anapole moment, so what it is, where it comes from. I will present direct detection limits on dark matter, which interacts via the anapole moment, and then I will apply these, I will show model-independent results, and then I will apply these model-independent results to the anapole moment of the lightest neutralino in both simplified models of the MSSM and within the full phenomenological MSSM. So, as I said, I will briefly talk about dark matter. So, as you probably all know, there's many evidence out there that we have an additional type of matter in the universe. For example, the rotational curves of galaxies do not match the standard calculation. Also, the movement of galaxy clusters needs additional non-baryonic matter to be explained. Large-scale structures also need this additional source of gravity. And also in the CMB, of course, we have imprints of dark matter. So in total nowadays we know that roughly 30% of the energy budget in our universe is made out of dark matter. So of course it's a very relevant question to modern physics to figure out what it is. So how are we looking for dark matter? Roughly speaking, we are looking for dark matter in 3 different types of experiments. For example, if we look at direct production at colliders or at direct and indirect detection experiments. Here I will focus on direct detection experiments. So these are experiments where we look at scattering events between an incoming dark matter particle and a target. This target then leaves some recoil signature in the detector, which we measure, and we can use to constrain models. So in this context, the experiment and theory are connected via the so-called scattering rate here on the left-hand side, which takes input from particle physics. So here's the differential cross-section, which describes the interaction between the dark matter particle and the target, in this case a nucleus. And then, of course, we have the mass of the dark matter. And then we have information from astrophysics, so information about the local density and the velocity distribution. However, here I will only talk about the particle physics input, which is given in terms of this cross-section, which is model-dependent, of course, because we don't know what dark matter is, so we have to come up with a model. And concretely speaking, I will talk about this diagram. So we have dark matter, which is denoted by chi, which interacts with a standard model photon, which then couples to the target. So, for example, the nucleus or electrons, but I will only talk about nuclei from now on. So, okay, the dark matter is, of course, not charged, so this coupling has to be an effective coupling. So, from a theoretical point of view, we have to, or the goal is to calculate this diagram. And from an experimental point of view, of course, like if we have this diagram here, we can calculate the amplitude, we can calculate the differential cross-section, and then we can use the experimental data from direct detection experiments to constrain a dark matter model. So that's the general setup. So the goal is to compare direct detection limits with model predictions for this coupling. Okay, but what are we actually talking about? So here I just wrote a cryptic mu. In fact, we can parameterize this mu using our Lorentz decomposition, and we can make this ansatz containing 4 different form factors. So here we have a charge form factor, the anapole form factor, magnetic dipole form factor, and the electric dipole form factor. Then in the zero momentum limit, so if we take an on-shell photon, these form factors reduce to the static electromagnetic quantities. So here we have the charge. For the charge form factor, we have the anapole moment and both dipole moments. And now the crucial point is, if we take this chi, so in this context our dark matter candidate to be Majorana, all of these moments or form factors actually vanish apart from the anapole moment. That's why the anapole moment is relevant. And also I want to note that the anapole moment violates separately P and C, which will be important later on. So okay, now we know that if we take an anapole, a Majorana fermion, then this interaction here is just given by the anapole moment. That means that we can just use direct detection data to constrain this anapole moment. And this is shown in this plot. So the x-axis is the dark matter mass, the y-axis is the anapole moment, and I show 4 different exclusion curves from direct detection experiments. So in green the dark green one shows the limit from xenon 1 ton the light green one is the future sensitivity of xenon NT, and then there are constraints also from super CDMS and CREST 3. And I want you to focus on the region around 100 GeV, where xenon NT will probe values for this unipole moment of roughly 10 to the minus 6 in some units. So 10 to the minus 6 is important. Okay, so back to this picture. Now we discuss the left side. So we know that in the near future, we will be able to test values down to 10 to the minus 6. So now we can discuss the right-hand side. So what are our predictions for this coupling? So this is an effective coupling, so let's calculate it at one loop order, right? So if we take this model-independent interaction Lagrangian, where we couple this chi, so this is now a general Majorana fermion, doesn't have to be the dark matter candidate. If you take this and couple it to a charged scalar and a charged Dirac fermion, where we parameterize the interaction via these couplings CLCR, we can draw these diagrams and we can calculate these diagrams and extract the contribution to the unipole moment. So this will give us something that I will call the scalar contribution, and actually this has been already calculated in the past. So this is, technically speaking, nothing new. However, another option is that we include a vector interaction. So this is something we did. As far as I know, we are the first people who did this. And well, the approach is very similar. We take this model-independent interaction vertex. We can draw these diagrams, but also for reasons of consistency, we also have to include the gallstones in this calculation. Now, if you do this calculation similar than here, then you will actually notice. Okay, first of all, I will call this the vector contribution. So if you try to do this computation using the standard Feynman rules, you will actually find that these diagrams, especially due to the fact that here's a triple gauge vertex, is actually divergent and gauge dependent. So clearly, this setup here cannot be a proper physical quantity. This was already noticed in the 80s, actually, for the neutrinos, where it was found out that the neutrino charge radius is, as here, not physically properly defined. And actually there was a solution, or a proposed solution in around 2000, so 20 years ago, which, where the approach is as follows. That is, we work in the background field method. So we replace all of these standard model photons by background field photons, and then we work in the Feynman gauge of the background field gauge. This basically projects us onto our, this projects these diagrams onto a gauge-independent setup, more or less. So there are many works on this, and especially if you're interested in this, you can have a look at this review here. Okay, so now we have a scalar contribution and a Goldstone, and a vector contribution. So I can show you, or I will show you now the results of these two contributions. So this is the vector, the scalar contribution. Here the four different plots are basically the same. The only difference is a different mass for the Majorana mass. So for example, the top right subplot here has a mass of 100 GeV. The x-axis is the scalar mass in units of this m chi, and then the y-axis is the absolute value of the unipole moment. And here, and the different colors correspond to different masses of the fermion in the loop. So here the point is just that if the scalar is in the vicinity of the Majorana fermion, so if we are approaching here 1, then we have a huge enhancement and we can easily reach values of 10 to the minus 6. And this is of course the same for all of these subplots. Then this is the result for the vector contribution. Actually not really, because the Goldstone loops are not included here, because they are model dependent. However, the behavior is very similar. So again, if we look close to the case where the so if they are mass degenerate, then again we have a enhancement, which is significant, and we can easily reach again 10 to the minus 6. However, here for this plot and for the previous plot, I took very naive values for these couplings. So I took 1 to 1 and 1 to 0. This is of course not really realistic. So let's now talk about a more realistic scenario, that is the MSSM. So how is the unipole moment of the lightest neutralino generated? As I mentioned before, the unipole moment breaks parity. So we are looking at couplings where this CL does not equal CR, or alternatively, where these vector couplings are not identical. And it turns out that the interactions of this lightest neutralino with the S fermions satisfies the first condition, so this will generate an anapole moment. However, there's also another contribution which is due to these VLs, which arise if the lightest neutralino and the chargino have non-trivial mixings. So in total, we have two possibilities to enhance the anapole moment of the lightest neutralino. One is if we have light fermions in the low energy spectrum. In this case, the anapole moment will be generated by the scalar contribution. Then the second option is if we have mixing in this electrovigino sector. In this case, the anapole moment will be generated by the vector contribution if all of the scalars are sufficiently heavy, of course. Okay, technically there's also a Higgs contribution, but for the discussion of the simplified models, they are not that relevant. So here I show you a scatter plot for a pure bino. So we don't have any vector contribution. And here the anapole moment is only generated by the tau Stau loop. We also apply constraints from Lab and from Atlas, which explains this shape in the top left corner. And here, interestingly, so if we look around 100 GeV, we find values of, let's say, 10 to the minus 9 to 10 to the minus 6, which sounds nice. Then the second simplified model I'm talking about now is a bino-hexino, mixed neutralino. So here we decouple all the scalars from the theory, so we only have neutralinos and charginos, basically. Yeah. So here the behavior looks a little different than for the left plot. So for example, if you look at the bino-like points, these are the red points, we see that there seems to be a maximum. And that is due to the fact that if we work in this bino-hexino limit and we have a bino-like point, that means that also the mu parameter is very large, on top of the very large bino mass. So that means that all the charginos which contribute are very heavy, and this leads to a constant anapole moment with respect to the LSP neutralino mass. Then in contrast to this, we have these hexino points, in which case the lightest neutralino and the lightest chargino are almost mass degenerate, so we have a similar behavior than here for the left plot. And I don't know if you can see it, but there are some pink points up here, which correspond to the mixed cases. So here we can see that the anapole moment is actually the largest if this mixing is large. Okay, so these were like now two very simplified models where we decoupled all the other physics from the theory. In the MSSM, of course, more stuff can go on and stuff can combine and so on. So here I show a scatter plot in the full 19-dimensional PMSSM, where I include constraints from Lab, from Z to invisible decays, from the Higgs sector, from LHC, and from flavor physics. However, no constraints on dark matter are included. So here the relevant point is just that for some reasonable choice of the MSSM parameters, which satisfies like a reasonable amount of constraints, we actually can generate anapole moment values which reach 10 to the minus 6. And usually are found maybe between 10 to the minus 8 or 10 to the minus 9 and 10 to the minus 6. So it's not that far off from the direct detection constraints. However, as I said, no dark matter constraints are applied. So this brings me to my summary. So in this work, we calculated two model-independent contributions, the scalar contribution and the vector contribution, of which the latter is novel. Then, in the context of the simplified models, I showed you that for the scalar contribution, it is possible to reach values of 10 to the minus 6 in these units, while the vector contribution is usually limited to 10 to the minus 8. However, if all the scalars are very heavy, for example in split SUSY, then this is the vector contribution is the only contribution which is present. That's why it might be relevant. So to summarize these 2 points, in the MSSM, both of these contributions could be relevant, which depends, of course, on the low energy spectrum. And also, as I mentioned a couple of times already, the direct detection limits have not been applied yet, and in fact, they are only applicable for a subset of the shown points. So more work has to be done to, I guess, understand more how the anapole moment actually, or what it actually means for direct detection within the MSSM, because of course you have more contributions in the MSSM. You don't have a pure anapole interaction with the targets. Yeah.
Thanks.
Could you go back to the slide where you first talked about the vectors, the vector contribution?
This one?
Yeah, so I guess my question has to do with a very long and confused literature on this subject. And so, I mean, as you stated, the initial authors who considered this claimed that that the anapole moment was unphysical, gauge dependent, etc. Is there something you can point to in those original papers and say this is why they got it wrong?
Oh yeah, sure. So, okay, as I very briefly mentioned, the problem is the triple gauge vertex,
the triple gauge vertex,
which is gauge dependent. So I have a backup slide. 1 second. Okay, so this picture. So what we are actually interested in is this diagram, right? So we're looking at a 2-to-2 process. And naively speaking, or what I did naively was, I was just looking at this interaction vertex. But this is not entirely correct, because I can also have vector-like terms in box diagrams. And exactly these vertex-like terms from this box diagram are the contributions which cancel the gauge dependency of this vertex here. So technically speaking, one also should include this box, and then can define all the a new vertex using all of the vertex-like terms to define a properly physically defined vertex. And this is what is the purpose of this pinch technique. And then it just turns out that this pinch technique is equivalent to the background field method in the Feynman gauge.
Okay, but I mean, would you still say that the anapole moment itself is a universal property of the particle, or now would you say, well, it depends on exactly the source of the virtual photon?
I would tend to say that it's a universal quantity. But yeah.
Well, this is I mean, I'll be talking about something related to this in the plenary sessions on Wednesday, and I've been trying to figure out what exactly to say about this point.
Yeah, like that's kind of the crucial point about this whole calculation. That's
Right.
true.
Okay, but now I understand. I mean, you have a particular model for where the virtual photon comes from, and so within that context,
yeah,
you can do the whole calculation, and now
exactly.
it makes sense.
Yeah. So, for example, in the standard model, so where the problem originated, yeah, like you know the box diagram, you can directly extract the correct the correct part which you need to add here, and you can directly see that these parts cancel, the gauge-dependent parts.
Right.
And in this context, so like if we look for the MSSM, I mean we have to have here, okay, I guess W, chargino, and then here I think you have the neutrino, so the partner of the okay. For the electron, you would have to have a neutrino here, and I'm confident that it also works for the MSSM, okay. But I don't know if it works well for every BSM model.
Well, but yeah, that's a separate point. But here, again, the virtual photon is coming from some heavy nucleus in that sense there. And so it's a very specific model for where the virtual photon is coming from.
I don't think it should matter. Like, maybe what matters is the momentum scale involved with this photon. Because technically speaking, we define the moments in the zero momentum limit, which might not be realistic if you look, for example, at colliders or something, where the center of mass energy is maybe larger than the particles in the loop. Or, for example, if you look at direct detection, so this was, for example, discussed in here in this paper by Kopp and collaborators. So, for example, if we, so here in this loop, for example, if we have the selectron and then the fermion is the electron. So we have 500 keV masses in the loop, but the typical momentum transfer for direct detection experiments is roughly 50 MeV or 80 MeV, something like this. So technically speaking, then the unipole moment is not even defined. But there is some way how you can still calculate it, and the correction is of order 1. So like qualitatively speaking, the approach is still fine for the interpretation of direct detection experiments.
Sure. Yeah, so I mean, just to, not to belabor this, but I mean, just if you wanted to ask, here's my point particle with an anipole moment, and suppose I have it interacting with some static electric magnetic fields and some currents, which I'm not telling you where they come from. Well, classically there would be some interaction energy, but the question is how would you compute that? You'd have to model where those currents come from, et cetera, et cetera. All right. But thanks.
Okay, someone else? If not, then we thank our last speaker again and conclude for today, I guess.